Ever wondered how data can speak for itself? Now imagine turning a mountain of numbers into decisions that shape the future. Statistics for data science is your ticket to doing just that. In this course, you will learn how to unlock the power of data and use statistics to make smarter, data-driven choices. So whether you're new to data science or looking to sharpen your skills, we have got you covered. We will kick things off with the basics of statistics, dive into Python, and show you how to use this powerful tool to work with data. You'll also get hands-on experience with large language models, the cutting-edge technology that's changing the way we analyze and interpret data. And by the end of this course, you will not just understand the theory behind statistics, but also how to apply it to solve real-world problems. And don't worry, we'll also cover those tricky data science interview questions so that you can walk into your next interview with confidence. Now, before we move on, just a quick information. Imagine transforming your career with one of the hottest skills today. Data Science and Generative AI ranked one as the #1 data science program by Economic Times. The professional certificate in data science and generative AI from Purdue University and Simplilearn equips you with hands-on learning with Python, machine learning, deep learning, and generative AI tools like ChatGPT. With masterclasses from Purdue faculty and IBM experts, plus real-world projects, this 6-month program opened doors to high-demand roles across the industries. You can boost your career with Purdue's world-class training. So what are you waiting for? Hurry up and enroll now, and you can find the link below.
Learning objectives. Welcome to Math Refresher, Probability and Statistics. In this lesson, we are going to explain the concepts of statistics and probability, describe conditional probability, define the chain rule of probability, discuss the measure of variance, identify the types of Gaussian distribution. Basic of statistics and probability. Probability and statistics. Data science relies heavily on estimates and predictions. A significant portion of data science is made up of evaluations and forecast. Statistical methods are used to make estimates for further analysis. Probability theory is helpful for making predictions. Statistical methods are highly dependent on probability theory, and all probability and statistics are dependent on data. Data is information acquired for reference or research via observations, facts, and measurements. Data is a set of facts structured in the form that computers can interpret, such as numbers, words, estimations, and views. Importance of data. Data aids in seeing more about the information by identifying possible connections between two features. Data assists in the detection of distortion by uncovering hidden patterns. Based on prior information patterns, data may be utilized to anticipate the future or predict the current state of affairs. Also, data aids in determining whether two pieces of information have any instance in common or not. Types of data. Data might be quantitative. That is data that can be measured or counted in numbers. Or it may be qualitative, which is data which is generally divided into groups, or in simpler words, which cannot be counted or measured in numbers. Let's consider an example. A customer information data of a bank may contain quantitative and qualitative data. Consider this snapshot where we have customer ID, surname, geography, gender, age, balance, has CR card, is active member. Amongst these variables, we can see surname is mostly qualitative as it cannot be counted and measured in numbers. Geography and gender are also qualitative as they cannot be counted in numbers and are mostly groups. Has CR card, that is, has credit card, and is active member, although are containing numerical in form. But these are categorical. That means these have been divided into groups of 1 and 0 that represent yes and no as an answer. Hence, these two variables are also qualitative. Customer ID is again, although a numerical data. However, the significance or intuition behind customer ID is categorical. Hence, it may be kept in the qualitative data also. However, age and balance. These are numerical information which have been measured or counted, and numerical operations can be performed on them. Hence, these are under quantitative data categories. Introduction to descriptive statistics. Descriptive statistics. A descriptive measurement is a summary measure that quantitatively portrays the most important features of a set of data, allowing for a better comprehension of the information. Data can be measured as different levels. The levels of measurement describe the nature of information stored in the data assigned to the variables. Qualitative data can be measured as nominal or ordinal. Quantitative data can be measured in terms of interval and ratio type. Nominal data. The data is categorized using names, labels, or qualities. For example, brand name, zip code, and gender. Ordinal data can be arranged in order or ranked and can be compared. Examples include grades, star reviews, position and race, and date. Interval data is the data that is ordered and has meaningful differences between the data points. Example, temperature in Celsius and year of birth. Ratio data is similar to the interval level with the added property of inherent zero. Mathematical calculations can be performed on both interval as well as ratio data. For example, height, age, and weight. Population versus sample. Before analyzing the data, it's important to figure out if it's from a population or a sample. Population is a collection of all available items as well as each unit in our study. Sample is a subset of the population that contains only a few units of the population. Population data is used for study when the data pool is very small and can give all the required information. Samples are collected randomly and represent the entire population in the best possible way. Measures of central tendency. The central tendency is a single value that aids in the description of the data by determining its center position. Measures of central tendency are sometimes known as summary statistics or measures of central location. The most popular measurements of central tendency are mean, median, and mode. The normal distribution is a bell-shaped, symmetrical distribution in which mean, median, and mode all are equal. The curve over here shows the bell-shaped curve or the normal distribution of variable x. The point over here that is x1 is the point which represents the mean, median, and mode of this distribution. Mean. Mean is calculated by dividing the sum of all data values by the total number of data values. It gets affected when there are unusual or extreme values. It is sensitive to the outliers. Mean can be calculated as summation over all the values of x in a collection divided by the size of the collection. For example, we have a collection where we have values as 7, 3, 4, 1, 6, and 7. We find out the sum of these values, which is 28, and there are a total of 6 values. So 28 divided by 6 gives us a mean value of 4.66. Median. It is the middle value in the set of the data that has been sorted in ascending order. It is a better alternative to mean, since it is less impacted by outliers and skewness. It is closer to the actual central value. Median is calculated differently for different sizes of data. Differentiated as if the total number of values is odd, or if the total number of values is even, if the size of the data is odd. For example, in this case, we have 5 elements. After sorting, whatever middle value we get. That means n plus 1 by 2th term in this case. 5 plus 1 divided by 2. That is the 3rd term, which is 4 is the median value. In case when the total number of values is even like here, there are 6 values. The average or the mean of the 2 central values is considered as the median. In this case, the median is the mean of 6 and 4, which is 5. Mode. Mode represents the most common value in the dataset. it is not at all affected by extreme observations. It is the best measure of central tendency for highly skewed or non-normal distribution. Mode for categorical data is determined by estimating the frequencies for each categories, and then the category with the highest frequency is considered to be mode. Like in this case, 7 has the highest frequency, hence 7 becomes the mode value. However, in case of continuous data or quantitative data, the calculation of mode is slightly different. The first step in calculation of mode is dividing the data into classes which are equal with, then getting the frequency of data points lying within that range of classes, and finally selecting the class with the highest frequency. Using the range of that class and the frequencies, we can get the final mode value. Using the formula L plus Fm minus F1 multiplied to H divided by Fm minus F1 plus Fm minus F2. Here L is the lower limit or the lower observation of the mode class. H is the size of the mode class. Fm is the frequency of the mode class. F1 is the frequency of the class proceeding to mode. And F2 is the frequency of the class succeeding to mode. This gives us the final mode value. Mean versus expectation. Now let's talk about mean versus expectation. So in general, we use the expected value or expectation when we want to calculate the mean of a probability distribution that represents the average value we expect to occur before collecting any data. And mean, on the other hand, mean is basically used when we want to calculate the average value of a given sample. This represents the average value of raw data that we may have already collected. We can understand this by using a simple example. Now, to calculate the expected value of this probability distribution, we can use a specific formula from the previous discussion. This is going to be the expected value, where x is going to be the data value, and this px is the probability of value. For example, we could calculate the expected value for this probability distribution to be as shown. So here, it will be 1.45 goals. So this represents the expected number of goals that the team will score in any given game. And then if you talk about calculating mean, so we typically calculate the mean after we have actually collected raw data. For example, suppose we record the number of goals that a soccer team will score in 15 different games. Now to calculate the mean number of goals scored per game, we can use the following formula, where sum of x is basically the sum of all the goals divided by n and the number of records, or we can say the sample size. It is as shown on the screen. So this represents the mean number of goals scored per game by the team. Measures of asymmetry. The difference between the three distinct curves can be studied in this image. The central curve is the normal or no skewness curve. Here mean, median, and mode all lie on the same point. This normal curve is symmetrical about its mean, median, and mode. That means the left-hand side of the curve is a mirror image of the right-hand side of the curve. However, in case of negatively skewed data, the tail is elongated on the left-hand side, and the mean is smaller than the mode and the median values, or is on the left-hand side of the mode, hence indicating that the outliers are in the negative direction. On the other hand, in case of positively skewed, the data is concentrated on the left-hand side of the curve, while the tail is elongated or longer on the right-hand side of the curve. The mean is greater than the mode and median, or is on the right-hand side of the mode and median, indicating that the outliers are in the positive direction. Let's consider an example. The graph here shows the global income distribution for the year 2013, and a projection for 2035. If we see the global income distribution statistics for 2003, it is highly right-skewed. We can observe in the previous graph that in 2003, the mean of $3,451 was higher than the median of $1,090. The global income is definitely not evenly distributed. The majority of people make less than $2,000 each year, while only a small percentage of the population earns more than $14,000. Measures of variability. Measures of variability. Dispersion. The measure of central tendencies provide a single value that addresses the full worth. However, the central tendency cannot depict the viewpoint entirely. The metric of dispersion helps us focus on the inconsistency in the data spread. Measures of dispersion describe the spread of the data. The range, interquartile range, standard deviation, and variance are examples of dispersion measures. Range. The range of distribution is the difference between the largest and the smallest amount of data. The range, for example, does not include all of a series' positive aspects. It concentrates on the most shocking aspects and ignores that aren't considered critical. For example, for a set 13, 33, 45, 67, 70, the range is 57. That is, the maximum of this, which is 70 minus the minimum over here, which is 13. Variance. Variance is the average of all squared deviations. It is defined as the sum of squared distance between each point and the mean or the dispersion around the mean. The standard deviation is used as variance suffers from a unit difference. Variance can be computed as sigma square summation over x minus mu square, divided by n, where mu is the mean of the data, x is the individual data point, and n is the size of the data. This representation is for a population data. For a sample data, variance can be computed as x minus x bar whole square summation over it divided by n minus 1. Here x bar is the mean of these sample data, and n is the sample size. The units of values and variance are not equal, so another variability measure is used. Standard deviation. Standard deviation is a statistical term used to measure the amount of variability or dispersion around a mean. The standard deviation is calculated as the square root of variance. It depicts the concentration of the data around the mean of the dataset. Standard deviation, as indicated previously, can be computed as square root of variance. For a population data, standard deviation sigma can be computed as square root of summation over xi minus mu whole square divided by n, where mu is the mean of the data, xi are the data points, and n is the size. Let's consider an example. Let's find out the mean, variance, and standard deviation for this data. The data values are 3, 5, 6, 9, and 10. To find out the mean, we first find the sum of all these data values. that is 33, and divide it by the count, which is 5. We get the mean of 6.6. To compute the variance, we start by computing the deviation. That is x minus the mean of x. Here 3 is one of the values of the data, and 6.6 is the mean. So 3 minus 6.6 square, and we do that to find out sum of all the deviations divided by the count, which is 5. We end up getting an overall variance of 6.64. Standard deviation, as we know, is measured at square root of variance. That is square root of 6.64, which amounts to 2.576. Measures of relationship. Measures of relationship. Covariance. Covariance is the measure of joint variability of two variables. It measures the direction of the relationship between the variables. It determines if one variable will cause the other to alter in the same way. Covariance between variable x and y can be computed as summation over the product of xi minus x bar and yi minus y bar the whole divided by n minus 1. Here x bar and y bar are the mean of x and y respectively. The value of covariance can range from minus infinity to a plus infinity. Correlation. Correlation is normalized covariance. It measures the strength of association between two variables. The most common measure for correlation is the Pearson correlation coefficient. Correlation between two variables, x and y, can be measured with respect to covariance as covariance between x and y divided by the standard deviation of x and standard deviation of y. The value of correlation ranges from a -1 to +1. Types of correlation. Correlation can be either a positive correlation, zero correlation, or a negative correlation. The first picture over here represents a perfect positive correlation, wherein a straight line with a positive slope is representing the relationship between the two variables. Zero correlation means that the line representing the relationship between the two variables is horizontal to the x-axis. Perfect negative correlation can be represented by a straight line with a negative slope. Correlation equals to 1 implies a positive relationship. That is when one variable increases, the other variable also increases. A correlation value of -1 implies a negative relationship. That is when one variable increases, the other decreases. The correlation coefficient of 0 shows that the variables are completely independent of each other. Let's consider an example. Here, we have two variables, height and weight. To compute the correlation between height and weight, we use the correlation formula as covariance of x and y divided by standard deviation of x and standard deviation of y. Here height is the x variable and weight is the y variable. First, to compute covariance, we compute the x minus x bar and y minus y bar values, and then the product of them. We then compute x minus x bar square and y minus y bar square values to compute the standard deviations of height and weight respectively. Correlation, as we know, has been defined as covariance of x and I and y divided by standard deviations of x and y. This can also be represented as summation over x minus x bar multiplied to y minus y bar divided by square root of summation over sum of squared deviations. That is x minus x bar square, multiplied to square root of summation over y minus y bar whole square. That is sum of square deviations for y. Now, let's find out values to put into this formula. First, we find out the overall sum of height to get the mean of height, which is 5.14. Similarly, we get the sum of weight to get the mean of weight as 50. We now get the summation over x minus x bar, multiplied to y minus y bar to get the numerator for the formula. Then we compute x minus x bar square summation and y minus y bar square. That is sum of squared deviation of x and y respectively. Now we put in the values in this final correlation formula to get a correlation value of 0.889. This indicates that height and weight have a positive relationship. It is evident that as height grows, weight also increases. In this module, we will be talking about expectation and variance. So the expected value, or we can say mean of a given variable, that we can denote by x is a discrete random variable where it is a weighted average of the possible values that x can take, and each value is going to be according to the probability of that specific event occurring. So usually the expected value of x is denoted by a simple formula where we can define the expectation based on the x parameter, which is going to be the sum of each possible outcome multiplied by the probability of the outcome occurring. So in more concrete terms, the expectation is what we would expect the outcome of an experiment to be on average. We can take an example for the coin. If a coin is being tossed 10 times, then one is most likely to get 5 heads and 5 tails. Same logic can be discussed if we talk about another example of rolling a die. So there are 6 possible outcomes when you roll a die. 1, 2, 3, 4, 5, 6. And each of these has a probability of 1 by 6 of occurring. So we can say that the expectation is going to be 1 multiplied by the probability of that happening, which is going to be 1 by 6, plus 2 by 6, plus 3 by 6, plus 4 by 6, plus 5 by 6, plus 6 by 6, and that is going to give us 3.5 as an output. The expected value is 3.5. So if you think about it, 3.5 is halfway between the possible values that I can take. And this is what we should have expected. Next, we talk about the concept of variance. So variance of a random variable allows us to know something about the spread of the possible values of the variable. So for a discrete random variable x, the variances of x is going to be denoted by using a simple formula that is going to be var x equals ex minus m, the whole square where m is basically the expected value of the expectation of x. So this is more like a standard deviation of x, which can also be represented by using this formula. So the variance does not behave in the same way as expectation when we multiply and add constants to random variables. So now there are 2 different types of variance that we can have a fair understanding on. First of all, we have low variance, and then we have high variance. So low variance simply means that there is a small variation in the production of the target function, with changes in the training data set, and at the same time, high variance, as we can see here. High variance shows a large variation in prediction of the target function, with changes in the training data set. So a model that shows high variance learns a lot and performs well with the training data set. And it does not generalize well with the unseen data set. And that's why, as a result, such a model gives good results with training data set, but shows high error rates on the test data set. And since the high variance a model learns too much from the data set, it leads to an overfitting of the model. So model with high variance will be having a couple of issues, like it may lead to overfitting, or it may also lead to increase in model complexities. Next, we have skewness. So skewness in simple terms is basically a measure of asymmetry of a distribution. So distribution is asymmetrical when its left and right sides are not the mirror images. Right now, this is a mirrored image, and a distribution can have right positive, or we can say negative, or it can have zero skewness. So right skewed in this scenario is basically the distribution is longer on the right side of its peak. And a left skew distribution is going to be, we can say, where it is longer on the left side. So we can see we have this one as a part of right side. It is more elongated towards the right side, and this one is more elongated towards the left side. So we can think of skewness in terms of tails. A tail is long tapering and the end of a distribution. So it simply indicates that they are observations at one end of the distribution, but that they are relatively infrequent. So a right skew distribution has a long tail on the right side, as you can see here, so the number supports observed. Let's say we have a data on a per year basis. So again, we can have a more skewness towards the right side, where data is being dropping as we continue to increase the number of years. For example, we may have a high sales towards the beginning of year, suppose in 2022. But again, as we proceed to 2023, second half we are seeing the dip in performance. So that is rightly skewed. And same way, let's suppose if we started with the sales figure, it was really less in suppose 2002. But again, as we proceeded to 2023 now, our sales have been gradually increasing. So it's more like skew towards the left section as a part of negative skew. Next, we have kurtosis. So kurtosis is basically a measure of the tailedness of a distribution. So tailedness is how often the outliers occur, and acts as kurtosis is the tailedness of the distribution related to a normal distribution. So a distribution with medium kurtosis is called as mesokurtic. A distribution with low kurtosis like this one. This is called as the platykurtic, and then distribution with high kurtosis like this one. This is called as the leptokurtic. So tails here, they are tapering ends on either side of a distribution like this. So they represent the probability or the frequency of values that are extremely high or extremely low to the mean. In other words, tails here represents how often the outliers occur. So there are three types of kurtosis. We have platykurtic, which is negative, leptokurtic, which is a positive towards the upper end, and then we have mesokurtic, which is a normal distribution. So mesokurtic is the medium tail. So normal distributions, they have a kurtosis of 3. So any distribution with a kurtosis of a prox value of 3 is going to be mesokurtic, and kurtosis is described in terms of excess kurtosis, which is kurtosis minus 3. And since normal distribution, they have a kurtosis of 3-axis kurtosis, makes comparing a distribution kurtosis to a normal distribution even easier. Introduction to probability. Probability theory. Probability is a measure of the likelihood that an event will occur. Let's consider an example of coin toss, where the chances of getting heads on a coin are 1 by 2 or 50%. The probability of each given event is between 0 and 1, both inclusive. Sum of an event's cumulative probability cannot be greater than 1. Hence, the probability of an event x lies between 0 and 1. This means that the integral of probability of distribution over x equals to 1. Conditional probability. Conditional probability of any event A is defined as the probability of occurrence of A, given that event B has previously occurred. Condition probability of event A given B can be estimated as probability of A intersection B, that is, probability of both A and B happening together, divided by the probability of B. It is also written as that probability of A intersection B equals to probability of A given B multiplied to probability of B. Let's consider an example. In a coin, we are doing a two-coin flip. Coin 1 gets heads, and tails in subsequent flips, while coin 2 gets tails, heads, and tails in the subsequent flips. Now the probability that coin 1 will get a head is 2 out of 4, while the probability that coin 2 will get heads is again 2 out of 4. The probability that both coin 1 and coin 2 will have a heads is just 1 out of the 4 flips. Hence, the probability that coin 1 will get heads, given that coin 2 is already heads, can be computed as probability of coin 1 edge intersection coin 2 edge, that is 1 by 4 divided by probability of coin 2 edge. That's a given that is 2 by 4, which is going to be 0.5 or 50% based. Bayes theorem. Bayes' theorem calculates the conditional probability of an event based on its prior probabilities. Basically, Bayes' theorem incorporates the prior probability distribution to predict the posterior probabilities. Bayes' theorem for conditional probability can be expressed as probability of A given B equals probability of B given A, divided by probability of B multiplied to probability of A. Bayes' theorem allows updating the probability values by using new information or evidence. Here, probability of A is known as prior probability. That is the probability of event before any new data is collected. Probability of A given B is known as the posterior probability. It is the revised probability of an event occurring after taking into consideration the new information. Probability of B given A is known as the likelihood, and probability of B is probability of observing an evidence. Bayes model. An example. Consider an example for calculating the likelihood of having diabetes based on frequency of fast food consumption. Here is the observed data. Let's say the fast food audience is 20%. Diabetes prevalence is 10%. And 5% is fast food and diabetes. The chances of diabetes given fast food, that is the conditional probability of D given B, can be calculated as probability of diabetes and fast food together divided by probability of fast food. That means 5% divided by 20%. That equals 25%. Define an analysis can state eating fast food increases the chance of having diabetes by 25%. The multiplication rule of probability. If events A and B are statistically independent and probability of A intersection B can be given as probability of A given B multiplied to probability of B. However, probability of A intersection B is also given as probability of A multiplied to probability of B. Here, probability of A given B equals to probability of A when we assume that probability of B is non-zero. Similarly, probability of B equals probability of B given A, assuming probability of A is non-zero. Chain rule of probability. Joint probability distributions over many random variables can be reduced into conditional distributions over a single variable. It can be expressed as probability of x1, x2, so on until xn equals probability of x1 intersection probability of xi, given probability of x1 till xi minus 1. For example, the joint probability of A, B, and C can be given as probability of A given B. C multiplied to probability of B given C multiply to probability of C. Logistic sigmoid. The logistics function is a type of sigmoid function that aims to predict the class to which a particular sample belongs. Its outcome is discrete binary value, a probability between 0 and 1. The logistics sigmoid is a useful function that follows the yes curve. It saturates when the input is very large or very small. Logistic sigmoid is expressed as sigma of x equals 1 upon 1 plus e to the power minus x. The logistic sigmoid can be expressed as sigmoid function of x is given as 1 upon 1 plus e to the power minus x, where e is the Euler's number. Gaussian distribution. The Gaussian distribution is a type of distribution in which data tends to cluster around a central value with little or no bias to the left or right. It is often referred to as normal distribution. In absence of prior information, the normal distribution is frequently a fair assumption in machine learning. Equation. The formula for calculating Gaussian distribution is described as the normal distribution of x. That is the function of x given mean as mu and variance is sigma square can be calculated as 1 upon sigma square root of 2 pi e to the power minus half x minus mu divided by sigma whole square, where mu is the mean or peak value, which also is the expected value of x. Sigma is the standard deviation, sigma square is the variance. A standard normal distribution has a mean of 0 and a standard deviation of 1. Gaussian distribution can be univariate, which describes the distribution of a single variable x. It can also be multivariate, where it can just use to describe the distribution of several variables. It is represented in 3D of ND formats. Law of large numbers. Now let's talk about law of large numbers. The law of large numbers states that an observed sample average from a large sample will be close to the true population average, and that it will get closer in the larger sample. So the law of large number does not guarantee that a given sample, spatially a small sample, will reflect the true population characteristics, or that a sample does not reflect the true population will be balanced by a subsequent sample. This is for the law of large numbers to express the relationship between scale and growth rate. So there are multiple examples through which we can understand, and it is widely used in statistical analysis in working with the central limit theorem in terms of the business growth. So there are multiple real-time setup in which these are going to be used. So if you talk about tossing a coin, so tossing a coin in a number of times will give us two different type of outcomes. The result will spread evenly between head and tails, and the expected average value is going to be half. That means 50 times tails and 30 times heads. But again, if you toss a coin 1,000 times, then the result can be in different manners, because out of 1,000, let's say 850 times it has been head and only 150 times it has been tails, and so on. So that's why the possibility of one event occurring is going to be changed in large sample sets as compared to a small sample sets, as in let's say 10 times. So the number of heads and tails unbalanced for lower number of trials, so we can see it is unbalanced. But again, as soon as we toss more number of coins, more leans towards the balance value, or we can see the observed averages. Next, we have p-value. So p-value is basically a number calculated from the statistical test that describes how likely we are to have found a particular set of observations if the null hypothesis were true. So p-values are used in hypothesis testing to help decide whether to reject the null hypothesis. And the smaller the p-value, the more likely we are to reject the null hypothesis. So we have a term called as null hypothesis. So all statistical tests, they have null hypothesis. So for most tests, the null hypothesis is that there is no relationship between our variables of n first, or that there is no difference among groups. For example, in a two-tailed t-test, the non-hypothesis is that the difference between two groups is going to be 0. So p-value is going to tell us how likely it is that our data could have occurred under the null hypothesis. It is done by calculating the likelihood of a test statistic, which is the number calculated by a statistical test using our data. So p-value tell us how often we would expect to see a test statistic as extreme or more extreme than one calculated by a statistical test if the null hypothesis of the test was true. So there are multiple limitations as well. So first one is the results can be significant, but again, they may not be practical as we have compared. It can be based on multiple hypotheses for a game for the healthcare test. If the test is going to be positive or not, it may show even values of the effect of a variable, but not the magnitude in real life. What exactly is going to be the application of a drug test being failed in pharma company? Therefore, it is recommended to use confidence and levels in addition to the p-values to quantify, or we can say to give a solid figure to the reserve, which we are going to get. The p-values, they are interpreted as supporting, or we can say refuting, the alternative hypothesis. So p-value can only tell you whether or not the null hypothesis is supported. It cannot tell us whether our alternative hypothesis is true or why. So the risk of rejecting the null hypothesis is often higher than the p-value. So especially when we are looking at a single study or when using small sample sizes. So this is because the smaller frame of reference, the greater are the chance that as we stumble across a statistically significant pattern completely by accident. Key takeaways. Key takeaways. Probability and statistics structure the premise of the data. The data helps in anticipating the future or gauging in view of the past patterns of information. The central tendency is a single value that helps to describe the data by identifying these central positions. The mean, median, and mode are the measures of central tendencies. The distribution where the data tends to be around a central value with a lack of bias or minimal bias towards the left or right is called as Gaussian distribution.
Mathematics for machine learning. My name is Richard Kirshner with the Simplilearn team. That's Get Certified, Get Ahead. We're going to cover mathematics for machine learning. So today's agenda is going to cover data and its types. Then we're going to dive into linear algebra and its concepts, calculus, statistics for machine learning, probability for machine learning, hands-on demos. And of course, thrown in there in the middle is going to be your matrices and a few other things to go along with all this. Data and its types. Data denotes the individual pieces of factual information collected from various sources. It is stored, processed, and later used for analysis. And so we see here just a huge grouping of information, a lot of text stuff, money, dollar signs, numbers, and then you have your performing analytics to drive insights. And hopefully you have a nice your shareholders gathered at the meeting and you're able to explain it in something they can understand. So we talk about types of data. We have, in our types of data, we have a qualitative, categorical. And you think nominal or ordinal. And then you have your quantitative or numerical, which is discrete or continuous. And let's look a little closer at those data types. Vocabulary, always people's favorite is the vocabulary words. Okay, not mine. But let's dive into this, what we mean by nominal. Nominal, they are used to label our variables without providing any measurable value. Country, gender, race, hair, color, etc. It's something that you either mark true or false. This is a label. It's on or off. Either they have a red hat on or they do not. So a lot of times when you're thinking nominal data labels, think of it as a true-false kind of setup. And we look at ordinal. This is categorical data with a set order or a scale to it. And you can think of salary range as a great one. Movie ratings, etc. You can see here the salary range. If you have 10,000 to 20,000, number of employees earning that rate is 150. 20,000 to 30,000, 100, and so forth. Some of the terms you'll hear is bucket. This is where you have 10 different buckets and you want to separate it into something that makes sense into those 10 buckets. And so when we start talking about ordinal, a lot of times when you get down to the brass bones, again, we're talking true false. So if you're a member of the 10 to 20K range, so forth. Those would each be either part of that group or you're not. But now we're talking about buckets and we want to count how many people are in that bucket. Quantitative numerical data falls into two classes, discrete or continuous. And so data with a final set of values which can be categorized. Class strength, questions answered correctly, and runs hit in cricket. A lot of times when you see this, you can think integer, and a very restricted integer, i.e. you can only have 100 questions on a test, so it's very discrete. I only have 100 different values that it can attain. So usually you're talking about integers, but within a very small range. They don't have an open end or anything like that. So discrete is very solid, simple to count, set number. Continuous, on the other hand, continuous data can take any numerical value within a range. So water pressure, weight of a person, etc. Usually we start thinking about float values where they can get phenomenally small in what they're worth. And there's a whole series of values that falls right between discrete and continuous. You can think of the stock market. You have dollar amounts. It's still discrete, but it starts to get complicated enough when you have jump in the stock market from $525.33 to $580.67. There's a lot of point values in there. It'd still be called discrete, but you start looking at it as almost continuous because it does have such a variance in it. Now, we talk about we went over nominal and ordinal, almost true-false charts, and we looked at quantitative and numerical data, which we're starting to get into numbers. Discrete, you can usually, a lot of times discrete could be put into true-false, but usually it's not. So we want to address this stuff, and the first thing we want to look at is the very basic, which is your algebra. So we're going to take a look at linear algebra. You can remember back when your Euclidean geometry. We have a line. Well, let's go through this. We have a linear algebra is the domain of mathematics concerning linear equations and their representations in vector spaces and through matrices. I told you we're going to talk about matrices. So a linear equation is simply 2x plus 4y minus 3z equals 10. Very linear. 10x plus 12.4y equals z. And now you can actually solve these two equations by combining them. And that's where we're talking about a linear equation. In the vectors, we have a plus b equals c. Now we're starting to look at a direction. And these values usually think of an x, y, z plot. So each one is a direction. And the actual distance of like a triangle, AB, is c. And then your matrix can describe all kinds of things. I find matrices confuse a lot of people, not because they're particularly difficult, but because of the magnitude and the different things they're used for. And a matrix is a chart, or think of a spreadsheet, but you have your rows and your columns. And you'll see here we have A times B equals C. Very important to know your counts. So depending on how the math is being done, what you're using it for, making sure you have the same rows and number of columns or a single number. There's all kinds of things that play in that can make matrices confusing. But really it has a lot more to do with what domain you're working in. Are you adding in multiple polynomials where you have like ax squared plus by plus, you start to see that it can be very confusing versus a very straightforward matrix. And let's just go a little deeper into these, because these are such primary. This is what we're here to talk about, is these different mathematical computations that come up. So when we're looking at linear equations, let's dig deeper into that one. An equation having a maximum order of 1 is called a linear equation. So it's linear because when you look at this, we have ax plus b equals c, which is a 1 variable. We have two variable ax plus by equals c, ax plus by plus cz equals d, and so forth. But all of these are to the power of 1. You don't see x squared. You don't see x cubed. So when we're talking about linear equations, that's what we're talking about. In their addition, if you have already dived into, say, neural networks, you should recognize this ax plus by plus cz setup plus the intercept, which is basically your neural network, each node adding up all the different inputs. And we can drill down into that. Most common formula is your y equals mx plus c. So you have your y equals the m, which is your slope, your x value plus c, which is your y-intercept. They kind of labeled it wrong here. Threw me for a loop. But the c would be your y-intercept. So when you set x equal to 0, y equals c. And that's your y-intercept right there. And they just had reversed value of y when x equals 0. It equals the y-intercept, which is c. And your slope gradient line, which is your m. So you get your y equals 2x plus 3. And there's lots of easy ways to compute this. This is why we always start with the most basic one when we're solving one of these problems. And then, of course, one of the most important takeaways is the slope gradient of the line. So the slope is very important, that m value. In this case, we went ahead and solved this. If you have y equals 2x plus 3, you can see how it has a nice line graph here on the right. So, matrices. A matrix refers to a rectangular representation of an array of numbers arranged in columns and rows. So we're talking m rows by n columns. Here, A11 denotes the element of the first row in the first column. Similarly, A12, and it's really pronounced A11 in this particular setup. So it's row 1, column 1. A12 is A row 1, column 2. First row and second column, and so on. And there's a lot of ways to denote this. I've seen these as like a capital letter A, smaller case a for the top row. Or, I mean, you can see where they can go all kinds of different directions as far as the value. You just take a moment to realize there needs to be some designation as far as what row it's in and what column it's in. And we have our basic operations. We have addition. So when you think about addition, you have two matrices of 2 by 2, and you just add each individual number in that matrix. And then when you get to the bottom, you have, in this case, the solution is 12. 10 plus 2 is 12. 5 plus 3 is 8, and so on. And the same thing with subtraction. Now, again, you're counting matrices. You want to check your dimensions of the matrix. The shape. You'll see shape come up a lot in programming. So when we're talking about dimensions, we're talking about the shape. If the two shapes are equal, this is what happens when you add them together or subtract them. And we have multiplication. When you look at the multiplication, you end up with a very slightly different setup going. Now, if we look at our last one, we're like, why? This always gets to me when we get to matrices, because they don't really say why you multiply matrices. My first thought is 1 times 2, 4 times 3. But if you look at this, we get 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5. 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. If you're looking at these matrices, think of this more as an equation. And so we have, if you remember, when we back up here for our multiple line equations, let's just go back up a couple slides where we were looking at 2 variable. So this is a 2 variable equation, ax plus by equals c. And this is a way to make it very quick to solve these variables, and that's why you have the matrix, and that's why you do the multiplication the way they do. And this is the dot product of 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. And it gives us a nice little 14, 23, 21, and 33 over here, which then can be used and reduced down to a simple formula as far as solving the variables as you have enough inputs. And then in matrix operations, when you're dealing with a lot of matrices, now keep in mind, multiplying matrices is different than finding the product of 2 matrices. Okay? So when we're talking about multiplication, we're talking about solving for equations. When you're finding the product, you are just finding 1 times 2. Keep that in mind, because that does come up. I've had that come up a number of times where I am altering data and I get confused as to what I'm doing with it. Transpose, flipping the matrix over its diagonal. Comes up all the time, where you still have 12, but instead of it being 12, 8, it's now 12, 14, 8, 21. You're just flipping the columns and the rows. And then, of course, you can do an inverse, changing the signs of the values across this main diagonal. And you can see here we have the inverse a to the minus 1, and it ends up with, instead of 12, 8, 14, 12, it's now minus 22, minus 12. Vectors. Vector just means we have a value and a direction. And we have down 4 numbers here on our vector. In mathematics, a one-dimensional matrix is called a vector. So if you have your x plot and you have a single value, that value is along the x-axis and it's a single dimension. If you have 2 dimensions, you can think about putting them on a graph. You might have x and you might have y, and each value denotes a direction. And then, of course, the actual distance is going to be the hypothesis of that triangle. And you can do that with 3 dimensionals, x, y, and z. And you can do it all the way to nth dimensions. So when they talk about the k-means for categorizing and how close data is together, they will compute that based on the Pythagorean theorem. So you would take the square of each value, add them all together, and find the square root, and that gives you a distance as far as where that point is, where that vector exists, or an actual point value. And then you can compare that point value to another one, and it makes a very easy comparison versus comparing 50 or 60 different numbers. And that brings us up to eigene vectors and eigene values. Eigene vectors, the vectors that don't change their span while transformation, and eigene values, the scalar values that are associated to the vectors. Conceptually, you can think of the vector as your picture. You have a picture, it's 2 dimensions, x and y. And so when you do those 2 dimensions and those 2 values, or whatever that value is, that is that point. But the values change when you skew it. And so if we take and we have a vector A, and that's a set value, B is you have A and B, which is your eigene vector. 2 is the eigene value. So we're altering all the values by 2. That means maybe we're stretching it out one direction, making it tall, if you're doing picture editing. That's one of the places this comes in. But you can see when you're transforming your different information, how you transform it is then your eigene value. And you can see here, vector after line transition, we have 3a. A is the eigene vector, 3 is the eigene value. So A doesn't change. That's whatever we started with. That's your original picture. And 3 is skewing it one direction, and maybe B is being skewed another direction. And so you have a nice tilted picture because you've altered it by the eigene values. So let's go ahead and pull up a demo on linear algebra. And to do this, I'm going to go through my trusted Anaconda into my Jupyter notebook, and we'll create a new notebook called linear algebra. Since we are working in Python, we're going to use our NumPy. I always import that as NP, our NumPy array. Probably the most popular module for doing matrices and things in. Given that this is part of a series, I'm not going to go too much into NumPy. We are going to go ahead and create 2 different variables, A for a NumPy array 10, 15, and B 29. We'll go ahead and run this, and you can see there's our 2 arrays, 10, 15, 29. And I went in and added a space there in between, so it's easier to read. And since it's the last line, we don't have to put the print statement on it unless you want. We can simply do A plus B. So when I run this, we have 10, 15, 29, and we get 30, 24, which is what you expect. 10 plus 20, 15 plus 9. You could almost look at this addition as being just adding up the columns on here coming down. And if we wanted to do it a different way, we could also do A dot T plus B dot T. Remember that T flips them. And so if we do that, we now get them, we now have 30, 24 going the other way. We could also do something kind of fun. There's a lot of different ways to do this. As far as a plus b, I can also do a plus b dot t. And you're going to see that that will come out the same, the 30, 24, whether I transpose a and b or transpose them both at the end. And likewise, we can very easily subtract two vectors. I can go a minus b. And we run that, and we get minus 10, 6. Now remember, this is the last line in this particular section, so I don't have to put the print around it. And just like we did before, we can transpose either the individual or we can transpose the main setup, and then we get a minus 10, 6 going the other way. Now, we didn't mention this in our notes, but you can also do a scalar multiplication. Let me just put down scalar so you can remember that. And what we're talking about here is I have this array here, u, and if I go a times u, we'll take the value 2, we'll multiply it by every value in here. So 2 times 30 is 60, 2 times 15. And just like we did before, this happens a lot because when you're doing matrices, you do need to flip them. You get 60, 30 coming this way. So in NumPy, we have what they call dot product. And with this is in a two-dimensional vectors. It is the equivalent to matrix multiplication. And remember, we were talking about matrix multiplication, where it is the, well, let's walk through it. We'll go ahead and start by defining two NumPy arrays. We'll have 10, 20, 25, 6, or our u and our v. And then we're going to go ahead and do, if we take the values, and if you remember correctly, an array like this would be 10 times 25 plus 20 times 6. We'll go ahead and print that. There we go. And then we'll go ahead and do the np dot of u comma v. And we'll find when we do this, we go ahead and run this, we're going to get 370, 370. So this is a strain multiplication where they use it to solve linear algebra when you have multiple numbers going across. And so this could be very complicated. We could have a whole string of different variables going in here. But for this, we get a nice value for our dot multiplication. And we did addition earlier, which was just your basic addition. And of course, the matrix, you can get very complicated on these, or in this case, we'll go ahead and do, let's create two complex matrices. This one is a matrix of 12, 10, 4, 6, 4, 31. We'll just print out A so you can see what that looks like. Here's print A. When we print A out, you can see that we have a 2 by 3 layer matrix for A. And we can also put together, always kind of fun when you're playing with print values, we could do something like this. We could go in here. There we go. We could print A, we have it end with equals A, run, and this kind of gives it a nice look. Here's your matrix. That's all this is. Comma n means it just tags it on the end. That's all that is doing on there. And then we can simply add in what is A plus B, and you should already guess, because this is the same as what we did before. There's no difference. When we do a simple vector addition, we have 12 plus 2 is 14, 10 plus 8 is 18, and so on. And just like we did the matrix addition, we can also do A minus B and do our matrix subtraction. And we look at this, we have what, 12 minus 2 is 10, 10 minus 8, where are we? Oh, there we go. 8 minus, confusing what I'm looking at. I should have reprinted out the original numbers. But we can see here 12 minus 2 is, of course, 10. 10 minus 8 is 2. 4 minus 46 is minus 42, and so forth. So same as the subtraction as before, we just call it matrix subtraction. It's identical. Now, if you remember up here, we had scalar addition, where we're adding just one number to a matrix. You can also do scalar multiplication. And so simply, if you have a single value A and you have B, which is your array, we can also do A times B. When we run that, you can see here we have 2 times 4 is 8, 5 times 4 is 20, and so forth. You're just multiplying the 4 across each one of these values. And this is an interesting one that comes up. A little bit of a brain teaser is matrix and vector multiplication. And so when we're looking at this, we are, just do a regular arrays. It doesn't necessarily have to be a NumPy array. We have A, which has our array of arrays, and B, which is a single array. And so we can, from here, do the dot AB, and this is going to return 2 values. And the first value is that, you could say it's like we're doing this array, B array, first with A and then with a second one. And so it splits it up. So you have a matrix of vector multiplication, and you can mix and match. When you get into really complicated back-end stuff, this becomes more common because you've got layers upon layers of data, and so you'll end up with a matrix and a set of vector matrices you want to multiply. Now, keep in mind that if you're doing data science, a lot of times you're not looking at this. This is what's going on behind the scenes. So if you're in the scikit looking at sklearn, where you're doing linear regression models, this is some of the math that's hidden behind the scenes that's going on. Other times, you might find yourself having to do part of this and manipulate the data around so it fits right, and then you go back in and you run it through the scikit. And if we can do, up here where we did a matrix and vector multiplication, we can also do matrix to matrix multiplication. And if we run this where we have the 2 matrices, you can see we have a very complicated array that, of course, comes out on there for our dot. And just to reiterate it, we have our transpose a matrix, which is your dot T. And so if we create a matrix A and then we do transpose it, you can see how it flips it from 5, 10, 15, 20, 25, 30 to 5, 15, 25, 10, 20, 30, rows and columns. And certainly with the math, this comes up a lot. It also comes up a lot with XY plotting. When you put it into PyPlot, you have one format where they're looking at pairs of numbers, and then they want all of X's and all Y's. So, the transpose is an important tool both for your math and for plotting and all kinds of things. Another tool that we didn't discuss is your identity matrix. And this one is more definition. The identity matrix, we have here one where we just did 2. So it comes down as 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. It creates a diagonal of 1. And what that is when you're doing your identities, you can be comparing all your different features to the different features and how they correlate. And of course, when you have feature 1 compared to feature 1 to itself, it is always 1, where usually it's between 0 and 1, depending on how well it correlates. So when we're talking about identity matrix, that's what we're talking about right here, is that you create this preset matrix and then you might adjust these numbers depending on what you're working with and what the domain is. And then another thing we can do to kind of wrap this up, we'll hit you with the most complicated piece of this puzzle here, is an inverse A matrix. And let's just go ahead and put the, it's a lengthy description. Let's go ahead and put the description. This is straight out of the website for NumPy. So given a square matrix A, here's our square matrix A, which is 2, 1, 0, 0, 1, 0, 1, 2, 1. Keep in mind, 3 by 3, it's square. It's got to be equal. It's going to return the matrix A inverse satisfying dot A inverse. So here's our matrix multiplication. And then, of course, it equals the dot, A inverse of A, with an identity shape of A dot shape 0. This is just reshaping the identity. That's a little complicated there. So we go and have here's our array. We'll go ahead and run this, and you can see what we end up with is we end up with an array 0.5 minus 0.5 and so forth, with our 2, 1, 1 going down, 2, 1, 0, 0, 1, 0, 1, 2, 1. Getting into a little deep on the math, understanding when you need this is probably is what's really important when you're doing data science versus handwriting this out and looking up the math and handwriting all the pieces out. You do need to know about the linear algorithm inverse of A. So if it comes up, you can easily pull it up, or at least remember where to look it up. We took a look at the algebra side of it. Let's go ahead and take a look at the calculus side of what's going on here with the machine learning. So calculus, oh my goodness, and differential equations, you got to throw that in there because that's all part of the bag of tricks, especially when you're doing large neural networks, but it also comes up in many other areas. The good news is most of it's already done for you in the back end. So when it comes up, you really do need to understand from the data science, not data analytics. Data analytics means you're digging deep into actually solving these math equations. And a neural network is just a giant differential equation. So when we talk about calculus, we're going to go ahead and understand it by talking about cars versus time and speed. So it helps to calculate the spontaneous rate of change. So suppose we plot a graph of the speed of a car with respect to time. So as you can see here, going down the highway, probably merged into the highway from an on-ramp. So I had to accelerate, so my speed went way up. Stuck in traffic, merged into the traffic opens up, and I accelerate again up to the speed limit, and maybe it peters off up there. So you can look at this as the speed versus time. I'm getting faster and faster because I'm continually accelerating, and if I hit the brakes, it'd go the other way. So the rate of change of speed with respect to time is nothing but acceleration. How fast are we accelerating? The acceleration is the area between the start point of x and the end point of delta x. So we can calculate a simple, if you had x and delta x, we could put a line there, and that slope of the line is our acceleration. Now, that's pretty easy when you're doing linear algebra, but I don't want to know it just for that line and those 2 points. I want to know it across the whole of what I'm working with. That's where we get into calculus. So when we talk about the distance between x and delta x, it has to be the smallest possible near to 0 in order to approximate the acceleration. So the idea is that instead of, if you ever took a basic calculus class, they would draw bars down here and you would divide this area up. Let's go back up a screen. You divide this area of this time period up into maybe 10 sections, and you'd use that and you could calculate the acceleration between each one of those 10 sections kind of thing. And then we just keep making that space smaller and smaller until delta x is almost infinitesimally small. And so we get a function of a equals a limit as h goes to 0 of a function of a plus h minus a function of a over h. And that is you're computing the slope of the line. We're just computing that slope under smaller and smaller and smaller samples. And that's what calculus is. Calculus is the integral. You can see down here we have our nice integral sign. Looks like a giant S. And that's what that means, is that we've taken this down to as small as we can for that sampling. So we're talking about calculus. We're finding the area under the slope is the main process in the integration. Similar, small intervals are made of the smallest possible length of x plus delta x, where delta x approaches almost an infinitesimally small space. And then it helps to find the overall acceleration by summing up all the lengths together. So we're summing up all the accelerations from the beginning to the end. And so here's our integral. We sum of a of x times d of x equals a plus c. That is our basic calculus here. So when we talk about multivariate calculus deals with functions that have multiple variables. And you can see here we start getting into some very complicated equations. Change in w over change of time equals change of w over change of z. The differential of z to dx, the differential of x to dt. It gets pretty complicated. And it really translates into the multivariate integration using double integrals. And so you have the sum of f of x of y of d of a equals the sum from C to D and A to B of f of x of y dx dy equals the sum of A to B, sum of C to D of f x of y dy dx. Understanding the very specifics of everything going on in here and actually doing the math is usually calculus 1, calculus 2, and differential equations. So you're talking about 3 full-length courses to dig into and solve these math equations. What we want to take from here is when we're talking about calculus, we're talking about summing of all these different slopes. And so we're still solving a linear expression. We're still solving y equals mx plus b. But we're doing this for infinitesimally small x's, and then we want to sum them up. That's what this integral sign means. The sum of a of x d of x equals a plus c. And when you see these very complicated multivariate differentiation using the chain rule, when we come in here and we have the change of w to the change of t equals the change of w dz, and so forth. That's what's going on here. That's what these means. We're basically looking for the area under the curve, which really comes to how is the change changing? Speed's going up. How is that changing? And then you end up with a multiple layer. So if I have 3 layers of neural networks, how is the third layer changing based on the second layer changing, which is based on the first layer changing? And you get the picture here that now we have a very complicated multivariate integration with integrals. The good news is we can solve this mathematically, and that's what we do when you do neural networks and reverse propagation. So the nice thing is that you don't have to solve this on paper unless you're data analysis and you're working on the back end of integrating these formulas and building the script to actually build them. So we talk about applications of calculus. It provides us the tools to build an accurate predictive model. So it's really behind the scenes. We want to guess at what the change of the change of the change is. That's a little goofy. I know. I just threw that out there. It's kind of a meta term. But if you can guess how things are going to change, then you can guess what the new numbers are. Multivariate calculus explains the change in our target variable in relation to the rate of change in the input variables. So there's our multiple variables going in there. If one variable is changing, how does it affect the other variable? And then in gradient descent, calculus is used to find the local and global maxima. And this is really big. We're actually going to have a whole section here on gradient descent because it is really, I mean, I talked about neural networks and how you can see how the different layers go in there, but gradient descent is one of the most key things for trying to guess the best answer to something. So let's take a look at the code behind gradient descent. And before we open up the code, let's just do real quick gradient descent. Let's say we have a curve like this. And most common is that this is going to represent your error. Oops. Error. There we go. Error. Hard to read there. And I want to make the error as low as possible. And so when I'm looking at it is I want to find this line here, which is the minimum value. So we're looking for the minimum. And it does that by sampling there. And then based on this, it guesses it might be someplace here. And it goes, hey, this is still going down. It goes here, and then goes back over here, and then goes a little bit closer. And it's just playing a high-low until it gets to that spot, that bottom spot. And so we want to minimize the error. On the flip note, you could also want to be maximizing something. You want to get the best output of it. That's simply minus the value. So if you're looking for where the peak is, this is the same as a negative for where the valley is. I'm looking for that valley. That's all that is, and this is a way of finding it. So the cool thing is all the heavy lifting's done. I actually ended up putting together one of these a while back when I didn't know about Sidekick and I was just starting. Boy, it's a long while back. And is playing high-low. How do you play high-low, not get stuck in the valleys, figure out these curves and things like that? Well, you do that, and the back end is all the calculus and differential equations to calculate this out. The good news is you don't have to do those. So instead, we're going to put together the code. And let's go ahead and see what we can do with that. So, guys in the back put together a nice little piece of code here, which is kind of fun. Some things we're going to note, and this is really important stuff, because when you start doing your data science and digging into your machine learning models, you're going to find these things are stumbling blocks. The first one is current X. Where do we start at? Keep in mind, your model that you're working with is very generic. So whatever you use to minimize it, the first question is, where do we start? And we started at this because the algorithm starts at x equals 3. So we arbitrarily picked 5. Learning rate is how many bars to skip going one way or the other. In fact, I'm going to separate that a little bit because these two are really important. If we're dealing with something like this where we're talking about, well, here's the function we're going to use. Our gradient of our function, 2 times x plus 5, keep it simple. So that's the function we're going to work with. So if I'm dealing with increments of 1,000, 0.1 is going to be a very long time. And if I'm dealing with increments of 0.001, 0.1 is going to skip over my answer. So I won't get a very good answer. And then we look at precision. This tells us when to stop the algorithm. So again, very specific to what you're working on. If you're working with money and you don't convert it into a float value, you might be dealing with 0.01, which is a penny. That might be your precision you're working with. And then, of course, the previous step size, max iterations. We want something to cut out at a certain point. Usually that's built into a lot of minimization functions. And then here's our actual formula we're going to be working with. And then we come in and we go, while previous step size is greater than precision and iters is less than max iters. Say that 10 times fast. We're just saying if we're still greater than our precision level, we still got to keep digging deeper. And then we also don't want to go past 1,000 or whatever this is, 1,000,000 or 10,000 running. That's actually pretty high. We almost never do max iterations more than like 100 or 200. Rare occasions you might go up to 400 or 500 if it's depending on the problem you're working with. So we have our previous equals our current. That way we can track time-wise. The current now equals the current minus the rate times the formula of our previous x. So now we've generated our new version. Previous step size equals the absolute current previous. So we're looking for the change in x. Iters equals iterations plus 1. That's how we know to stop if we get too far. And then we're just going to print the local minimum occurs at x on here. And if we go ahead and run this, you can see right here it gets down to this point and it says, hey, local minimum is minus 3.3222 for this particular series we created. And this is created off of our formula here, lambda x2 times x plus 5. Now, when I'm running this stuff, you'll see this come up a lot in with the sklearn kit. And one of the nice reasons of breaking this down the way we did is I could go over those top pieces. Those top pieces are everything when you start looking at these minimization toolkits and built-in code. And so from, we'll just do, it's actually docs.scipy.org, and we're looking at the scikit. There we go. Optimize, minimize. You can only minimize one value. You have the function that's going in. This function can be very complicated. So we used a very simple function up here. It could be, there's all kinds of things that could be on there. And there's a number of methods to solve this as far as how they shrink down. And your x naught, there's your start value. So your function, your start value, there's all kinds of things that come in here that you can look at, which we're not going to. Optimization automatically creates, constraints, bounds. Some of this it does automatically, but the big thing I want to point out here is you need to have a starting point. You want to start with something that you already know is mostly the answer. If you don't, then it's going to have a heck of a time trying to calculate it out. Or you can write your own little script that does this and does a high-low guessing and tries to find the max value. That brings us to statistics. What this is kind of all about is figuring things out. A lot of vocabulary in statistics. So statistics, well, I guess it's all relative. It's definitely not an EDL class. So a bunch of stuff going on in statistics. Statistics concerns with the collection, organization, analysis, interpretation, and presentation of data. That is a mouthful. So we have from end to end, where does it come from? Is it valid? What does it mean? How do we organize it? How do we analyze it? And then you got to take those analyses and interpret it into something that people can use, kind of reduce it to understandable. And nowadays you have to be able to present it. If you can't present it, then no one else is going to understand what the heck you did. So when we look at the terminologies, there's a lot of terminologies depending on what domain you're working in. So clearly, if you're working in a domain that deals with viruses and T cells and how does, where does it come from, and you're studying the different people, then you're going to have a population. If you are working with mechanical gear, a little bit different. If you're looking for the wobbling statistics to know when to replace a rotor on a machine or something like that, that can be a big deal. We have these huge fans that turn in our sewage processing systems. And so those fans, they start to wobble and hum and do different things that the sensors pick up. At one point, do you replace them instead of waiting for it to break, in which case it costs a lot of money. Instead of replacing a bushing, you're replacing the whole fan unit. An interesting project that came up for our city a while back. So population. All objects or measurements whose properties are being observed. So that's your population, all the objects. It's easy to see it with people because we have our population in large. But in the case of the sewer fans, we're talking about the fan units. That's the population of fans that we're working with. You have a parameter, a metric that is used to represent a population or characteristic. You have your sample, a subset of the population studied. You don't want to do them all because then you don't have if you come up with a conclusion for everyone, you don't have a way of testing it. So you take a sample. Sometimes you don't have a choice. You can only take a sample of what's going on. You can't study the whole population. And a variable, a metric of interest for each person or object in a population. Types of sampling. We have a probabilistic approach, selecting samples from a larger population using a method based on the theory of probability. And we'll go into a little bit more deeper on these. We have random, systematic, stratified. And then you have a non-probabilistic approach, selecting samples based on the subjective judgment of the researcher rather than random selection. It has to do with convenience, trying to reach a quota, or snowball. And they're very biased. That's one of the reasons you'll see this big stamp on it that says biased. So you gotta be very careful on that. So probabilistic sampling. When we talk about a random sampling, we select random size samples from each group or category. So it's as random as you can get. When we talk about systematic sampling, we're selecting random size samples from each group or category with a fixed periodic interval. So we kind of split it up. This would be like a time setup or our different categories. And you might ask your question, well, what is a category or a group? If you look at, I'm going to go back a window. Let's say we're studying economics of an area. We know pretty much that based on their culture and where they came from, they might need to be separated. And so, and when I say separated, I don't mean separated from their place where they live. I mean, as far as the analysis, we want to look at the different groups and make sure they're all represented. So if we had like an 80% of a group that is, say, Hispanic or Indian, and also in that same area, we have 20% who are, let's call our expatriates. They left America and they're nice, and your Caucasian group. We might want to sample a group that is representative of both. So we're talking about stratified sampling, and we're talking about groups. Those are the groups we're talking about. And that brings us to stratified sampling, selecting approximately equal size samples from each group or category. This way we can actually separate the categories and give us an insight into the different cultures and how that might affect them in that area. So you can see these are very, very different, kind of depends on what you're working with as far as your data and what you're studying. And so we can see here, just to go a little bit more, we'd have selecting 25 employees from a company of 250 employees randomly. Don't care anything about them, what groups they're in, which office they're in, nothing. And we might be selecting one employee from every 50 unique employees in a company of 250 employees. And then we have selecting one employee from every branch in the company office. So we have all the different branches. There's our group, or our categories by the branch. And the category could depend on what you're studying. So it has a lot of variation on there. You see this kind of grouping and categorizing is also used to generate a lot of misinformation. So if you only study one group and you say, this is what it is, then everybody assumes that's what it is for everybody. And so you got to be very careful of that, and it's a very unethical thing to kind of do. So types of statistics. When we talk about statistics, we're going to talk about descriptive and inferential statistics. There are so many different terms in statistics to break it up. So we're talking about a particular setup. So we're talking about descriptive and inferential statistics. The base of the word describe is pretty solid. You're describing the data. What does it look like? With inferential statistics, we're going to take that from the small population to a large population. So if you're working with a drug company, you might look at the data and say, these people were helped by this drug. They did 80% better as far as their health, or 80% better survival rate than the people who did not have the drug. So we can infer that that drug will work in the greater populace and will help people. So that's where you get your inferential. So we are predicting how it's going to affect the greater population. So descriptive statistics. It is used to describe the basic features of data and form the basis of quantitative analysis of data. So we have a measure of central tendencies. We have your mean, median, and mode. And then we have a measure of spread, like your range, your interquartile range, your variance, and your standard deviation. And we're going to look at all these a little deeper here in a second. But one of them you can think of is how the data differences, what's the max, min range, all that stuff is your spread. And anything that's just a single number is usually your central tendencies, measure of central tendencies. So we talk about the mean. It is the average of the set of values considered. What is the average outcome of whatever's going on? And then your median separates the higher half and the lower half of data. So where's the center point of all your different data points? So your mean might have a couple really big numbers that skew it so that the average is much higher than if you took those outliers out, where the median would, by separating the high from the low, might give you a much lower number. You might look at it and say, oh, that's odd. Why is the average so much higher than the median? Well, it's because you have some outliers. Or why is it so much lower? And then the mode is the most frequent appearing value. This is really interesting if you're studying economics and how people are doing. You might find that the most common income, like in the U.S., was at one point $24,000 a year, where the average was closer to $80,000. And it's like, wow, what a difference. Well, there's some people who have a lot of money, and so that skews that way up. So the average person is not making that kind of money. And then you look at the median income, and you're like, well, the median income is a little bit closer to the average. So it does create a very interesting way of looking at the data. Again, these are all central tendencies, single numbers you can look at for the whole spread of the data. And we look at the measure of central tendencies. The mean is the average marks of a student in a classroom. So here we have the mean, sum of the marks of the students, total number of students. And as we talked about the median, if we have 0 through 10, and we take half the numbers and put them on one side of the line, half the numbers on the other side of the line, we end up with 5 in the middle. And then the mode. What mark was scored by most of the students in a test? In a simple case where most people scored like an 82% and got certain problems wrong, easy to figure out. Not so easy when you have different areas where, like, you have like the, let's go back to economy. A little bit more difficult to calculate if you have a large group that makes 30,000 and a slightly bigger group that makes 26,000. So what do you put down for the mode? Certainly there's a number of ways to calculate that, and there's actually different variations depending on what you're doing. So now we're looking at a measure of spread, range. What's the difference between the highest and the lowest value? First thing you want to look at, it's we had everybody in the test scored between 60 and 100%. Somebody got 100%, or maybe 60 to 90%. It was so hard that a lot of people could not get 100%. Then you have your interquartile range. Quartiles divide a rank-ordered data set into 4 equal parts. Very common thing to do as part of all the basic packages, whether you're working in data frames with pandas, whether you're working in Scala, whether you're working in R. You'll see this come up where they have range, your min, your max, and then it'll have your interquartile range. How does it look like in each quarter of data? Variance measures how far each number in the set is from the mean and therefore from every other number in the set. So you have like how much turbulence is going on in this data. And then the standard deviation. It is the measure of the variance or the dispersion of a set of values from the mean. And you'll usually see, if I'm doing a graph, I might have the value graphed, and then based on the error, I might graph the standard deviation and the error on the graph as a background, so you can see how far off it is. So standard deviation is used a lot. So measurement of spread. Marks of a student out of 100. We have here from 50 to 63 or 50 to 90. So the range, maximum marks, minimum marks, we have 90 to 45, and the spread of that is 45, 90 minus 45. And then we have the interquartile range using the same marks over there. You can see here where the median is, and then there's the first quarter, the second quarter, and the third quarter based on splitting it apart by those values. And to understand the variance and standard deviation, we first need to find out the mean. So here's our calculating the average there. We end up at approximately 66 for the average. And then we look at that and the variance. Once we know the means, we can do equals the marks minus the mean squared. Why is it squared? Because one, you want to make sure you don't have, like, if you're putting all this stuff together, you end up with an error as far as one's negative, one's positive, one's a little higher, one's a little lower. So you always see the squared value and over the total observations. And so the standard deviation equals the square root of the variance, which is approximately 16. And if you were looking at a predictable model, you would be looking at the deviation based on the error. How much error does it have? And that's, again, really important to know. If your prediction is predicting something, what's the chance of it being way off or just a little bit off? Now that we've looked at the tools as far as some of the basics for doing your statistics and what we're talking about, let's go ahead and pull up a little demo and show you what that looks like in Python code, so you can get some little hands-on here. For that, let's go back into our Jupyter Notebook in Python. Now, almost all of this you can do in NumPy. Last time we worked in NumPy. This time we're going to go ahead and use pandas. And if you remember from pandas on here, this is basically a data frame, rows, columns. Let's just go ahead and do a print df.head and run that. And you can see we have the name Jane, Michael, William, Rosie, Hannah, and their salaries on here. And of course, instead of having to do all those hand calculations and add everything together and divide by the total, we can do something very simple on this, like use the command mean in pandas. And so if I go ahead and do this, print df, pick our column, salary, because we want to find the means of that column. We want to find the means of that column. And we go ahead and print this out, and you can see that the average income on here is 71,000. And let's just go ahead and do this. We'll go ahead and put in means. And if we're going to do that, we also might want to find the median. And the median is very similar, except it actually is just median. We're used to means and average. It's kind of interesting that they use the two different words. There can be, in some computations, slight differences, but for the most part, the means is the average. And then the median, whoops, let's put a median here, df salary, that way it displays a little better. We can see the median is 54,000. So the halfway mark is significantly below the average. Why? Because we have somebody in here who makes $189,000. Darn you, Rosie, for throwing off our numbers. But that's something you'd want to notice. This is the difference between these is huge, and so is what is the meaning behind that when you're studying a populace and looking at the different data coming in. And of course, we also want to find out, hey, what's the most common income that people make in this little tiny sample? And so we'll go ahead and do the mode. And you can see here with the mode, it's at 50,000. So this is very telling that most people are making 50,000. The middle point is at 54,000, so half the people are making more than that. What that tells me is that if the most common income is below the median, then there's a lot of high salaries going up, but there's some really low salaries in there. And so this trend, which is very common in statistics, when you're analyzing the economy and different people's income, is pretty common. And the bigger difference between these is also very important when we're studying statistics. And when you hear someone just say, hey, the average income was, you might start asking questions at that point. Why aren't you talking about the median income? Why aren't you talking about the mode, the most common income? What are you hiding? And if you're doing these analyses, you should be looking at these saying, hey, why are these discrepancies? Why are these so different? And of course, with any analysis, it's important to find out the minimum and the maximum. So we'll go ahead. It's just simply dot min will pull up your minimum, and then dot max pulls up the maximum. Pretty straightforward on as far as translating it and knowing what your lowest value and what your highest value is here, which you'll use to generate like a spread later on. And real quick on mode, note that it puts mode 0. Like I said, there's a couple different ways you can compute the mode. Although the standard one's pretty good. We can of course do the range, which is your max minus your min. So now we have a range of 149,000 between the upper end and the lower end. And you might want to be looking up the individual values on all of these. But it turns out there is a describe feature in pandas. And so in pandas, we can actually do df salary describe. And if we do this, you can see we have that there's 7 setups. Here's our mean, our standard deviation, which we didn't compute yet, which should just be a .std. And you got to be a little careful because when it computes it, it looks for axes and things like that. We have our minimum value, and here's our quartiles, our maximum value, and then of course the name salary. So these are the basic statistics. You can pull them up and just describe. This is a dictionary, so I could actually do something like in here I could actually go count and run, and now it just prints the count. So because this is a dictionary, you can pull any one of these values out of here. It's kind of a quick and dirty way to pull all the different information and then split it up depending on what you need. Now, if I just walked in and gave you this information in a meeting, at some point you would just kind of fall asleep. That's what I would do anyway. So we want to go ahead and see about graphing it here. And we'll go ahead and put it into a histogram and plot that graph on it of the salaries. And let's just go ahead and put that in here. So we do our matplot inline. Remember, that's a Jupyter's Notebook thing. A lot of the new version of the matplot library does it automatically, but just in case, I always put it in there. Import matplot library pyplot as PLT. That's my plotting. And then we have our data frame. I guess I really don't need to respell the data frame. Maybe we could just remind ourselves what's in it. So we'll go ahead and just print df. That way we still have it. And then we have our salary df salary, salary.plot history title, salary distribution, color gray, plot AXV line, salary the mean value. So we're going to take the mean value, color violet, line style dash. This is just all making it pretty. What color, dash line, line width of 2, that kind of thing. And the median. And let's go ahead and run this just so you can see what we're talking about. And so up here, we are taking on our plot. So here's the data. Here's our data frame printed out so you can see it with the salaries. And we're looking at the salary distribution. And just look at this, the way the salary is distributed. you have our, in this case we did, let's see, we had red for the median. We have violet for our average or mean. And you can just see how it really, I mean, here's our outlier. Here's our person who makes a lot of money. Here's the average, and here's the median. And so as you look at this, you can say, wow, based on the average, it really doesn't tell you much about what people are really taking home. All it does is tell you how much money is in this, you know, what the average salary is. So some of the things you want to take away in addition to this is that it's very easy to plot an AX V line. These are these up and down lines for your markers. And as you display the data, I mean, you can add all kinds of things to this and get really complicated. Keeping it simple is pretty straightforward. I look at this and I can see we have a major outlier out here. We can definitely do a histogram and stuff like that. But, you know, picture's worth 1,000 words. What you really want to make sure you take away is that we can do a basic describe, which pulls all this information out, and we can print any of the individual information from the describe, because this is a dictionary. And so if we want to go ahead and look up the mean value, we can also do describe mean. So if you're doing a lot of statistics, being able to, it doesn't have the print on there, so it's only going to print the last one, which happens to be the mean. You can very easily reference any one of these. And then you can also, if you're doing something a little bit more complicated and you don't need just the basics, you can come through and pull any one of the individual references from the pandas on here. So now we've had a chance to describe our data. Let's get into inferential statistics. Inferential statistics allows you to make predictions or inferences from data. And you can see here we have a nice little picture of movie ratings, and if we took this group of people and said, hey, how many people like the movie, dislike it, can't say, and then you ask just a random person who comes out of the movie who hasn't been in this study, you can infer that 55% chance of saying liked, 35% chance of saying disliked, or a 10 or 11% chance of can't say. So that's real basics of what we're talking about, is you're going to infer that the next person is going to follow these statistics. So let's look at point estimation. It is a process of finding an approximate value for a population's parameter, like mean or average, from random samples of the population. Let's take an example of testing vaccines for COVID-19. Vaccines and flu bugs, all of that, it's a pretty big thing of how do you test these out and make sure they're going to work on the populace. A group of people are chosen from the population. Medical trials are performed. Results are generalized for the whole population. So here's our small group up here where we've selected them. We run medical trials on them, and then the results work for the population. You know, nice diagram with the arrows going back and forth and the very scary COVID virus in the middle of one. And let's take a look at the applications of inferential statistics. Very central is what they call hypotheses testing, and the confidence interval, which go with that. And then as we get into probability, we get into our binomial theorem, our normal distribution, and central limit theorem. Hypothesis testing. Hypothesis testing is used to measure the plausibility of a hypothesis, assumption, by using sample data. Now, when we talk about theorems, theory, hypothesis, keep in mind that if you are in a philosophy class, theory is the same as hypothesis, where theorem is a scientific statement that is something that has been proven, although it is always up for debate, because in science we always want to make sure things are up to debate. So a hypothesis is the same as a philosophical class calling a theory, where theory in science is not the same. Theory in science says this has been well proven. Gravity is a theory. So if you want to debate the theory of gravity, try jumping up and down. If you want to have a theory about why the economy is collapsing in your area, that is a philosophical debate. Very important. I've heard people mix those up, and it is a pet peeve of mine. When we talk about hypotheses testing, the steps involved in hypotheses testing is first we formulate a hypothesis. We figure out the right test to test our hypothesis. We execute the test, and we make a decision. And so when you're talking about hypothesis, you're usually trying to disprove it. If you can't disprove it and it works for all the facts, then you might call that a theorem at some point. So in a use case, let's consider an example. We have 4 students who are given a task to clean a room every day. Sounds like working with my kids. They decided to distribute the job of cleaning the room among themselves. They did so by making 4 chits, which has their names on it, and the name that gets picked up has to do the cleaning for that day. Rob took the opportunity to make chits and wrote everyone's name on it. So here's our 4 people: Nick, Rob, Imlia, and Summer. Now, Rick, Imlia, and Summer are asking us to decide whether Rob has done some mischief in preparing the chits, i.e., whether Rob has written his name on one of the chit. For that, we will find out the probability of Rob getting the cleaning job on first day, second day, third day, and so on till 12 days. The probability of Rob getting the job decreases every day, i.e., his turn never comes up, then definitely he has done some mischief while making the chits. So the probability of Rob not doing work on day 1 is 3 out of 4. There's a 0.75 chance that he didn't do work. 2 days, 3/4 times 3/4 equals 0.56. 3 days, you have 3/4, 3/4, 3/4, which equals 0.42. When you get to day 12, it's 0.032, which is less than 0.05. Remember this 0.05. That comes up a lot when we're talking about certain values, when we're looking at statistics. Rob is cheating as he wasn't chosen for 12 consecutive days. That's a very high probability when on day 12 he still hasn't gotten the job cleaning the room. So we come up to our important terminologies. We have null hypothesis, a general statement that states that there is no relationship between 2 measured phenomena or no association among the groups. Alternative hypothesis. Contrary to the null hypothesis, it states whenever something is happening, a new theory is preferred instead of an old one. And so the 2 hypotheses go hand in hand. So your null, this is always interesting in when we're talking about data science and the math behind it, it's about proving that the things have no correlation. Null hypothesis says these 2 have 0 relation to each other. Where the alternative hypothesis says, hey, we found a relation, this is what it is. We have p-value. The p-value is the probability of finding the observed or more extreme results when the null hypothesis of a study question is true. And the t-value. It is simply the calculated difference represented in units of standard error. The greater the magnitude of t, the greater the evidence against the null hypothesis. And you can look at the t-value as being specific to the test you're doing, where the p-value is derived from your t-value, and you're looking for what they call the 5% or the 0.05, showing that it has a high correlation. So digging in deeper, let's assume that a new drug is developed with the goal of lowering the blood pressure more than the existing drug. And this is a good one because the null value here isn't that you don't have any drug. The null value here is that it's better than the existing drug. The new drug doesn't lower the blood pressure more than the existing drug. Now, if we get that, that says our null hypothesis is correct. There is no correlation, and the new drug is not doing its job. The alternative hypothesis, the new drug does significantly lower the blood pressure more than the existing drug. Yay, we got a new drug out there. And that's our alternative hypothesis, or the H1 or HA. And we look at the p-value, results from the evidence like medical trials showing positive results which will reject the null hypothesis. And again, they're looking for a 0.05 or 5%. And the t-value, comparing all the positive test results and finding means of different samples in order to test hypothesis. So this is specific to the test. What percentage of increase did they have? And this leads us to the confidence intervals. A confidence interval is a range of values we are sure our true values of observations lie in. Let's say you asked a dog owner around you and asked them, how many cans of food do you buy for your per year for your dog? Through calculations, you got to know that on an average, around 95% of the people bought around 200 to 300 cans of food. Hence, we can say that we have a confidence interval of 2-300, where 95% of our values lie in that data spread. And the graph really helps a lot, so you can start seeing what you're looking at here, where you have the 95% you have your peak. In this case, it's a normal distribution, so you have the nice bell curve equal on both sides. It's not asymmetrical. And 95% of all the values lie within a very small range, and then you have your outliers, the 2.5% going each way. So we touched upon hypothesis, and we're going to move into probability. So you have your hypothesis. Once you've generated your hypothesis, we want to know the probability of something occurring. Probability is a measure of the likelihood of an event to occur. Any event can be predicted with total certainty and can only be predicted as a likelihood of its occurrence. So any event cannot be predicted with total certainty. It can only be predicted as a likelihood of its occurrence. Score prediction, how good you're going to do in whatever sport you're in, weather prediction, stock prediction. If you've studied physics and chaos theory, even the location of the chair you're sitting on has a probability that it might move 3 feet over. Granted, that probability is 1 in I think we calculated it as under 1 in trillions upon trillions. So it's the better the probability, the more likely it's going to happen. There are some things that have such a low probability that we don't see them. So we talk about a random variable. Random variable is a variable whose possible values are numerical outcomes of a random phenomena. So we have the coin toss. How many heads will occur in the series of 20 coin flips? Probably, on average they're 10, but you really can't know because it's very random. How many times a red ball is picked from a bag of balls, if there's equal number of red balls and blue balls and green balls in there. How many times the sum of digits on 2 dice result are 5 each? There's how often you're going to roll 2 5s on your pair of dice. So in a use case, let's consider the example of rolling 2 dice. We have a random variable outcome equals y. You can take values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a random variable and a combination of dice. And instead of looking at how many times both dice will roll 5, let's go ahead and look at total sum of 5. And you have, as far as your random variables, you can have a 1, 4 equals 5, 4, 1, 2, 3, 3, 2. So 4 of those rolls can be 4. If you look at all the different options you have, 4 of those random rolls can be a 5. And if we look at the total number, which happens to be 36 different options, you can see that we have 4 out of 36 chance every time you roll the dice that you're going to roll a total of 5. You're going to have an outcome of 5. And we'll look a little deeper as to what that means. But you could think of that at what point, if someone never rolls a 5 or they always roll a 5, can you say, hey, that person's probably cheating? We'll look a little closer at the math behind that. But let's just consider this as one of the cases is rolling 2 dice and gambling. There's also a binomial distribution. It is the probability of getting success or failure as an outcome in an experiment or trial that is repeated multiple times. And the key is bi, meaning 2, binomial. So passing or failing an exam, winning or losing a game, and getting either head or tails. So if you ever see binomial distribution, it's based on a true-false kind of setup. You win or lose. Let's consider a use case, and let's consider the game of football between 2 clubs, Barcelona and Dortmund. The teams will have to play a total of 4 matches, and we have to find out the chances of Barcelona winning the series. So we look at the total games, and we're looking at 5 different games or matches. Let's say that the winning chance for Barcelona is 75% or 0.75. That means at each game, they have a 75% chance that they're going to win that game. And losing chances are 25% or 0.25. Clearly 0.75 plus 0.25 equals 1. So that accounts for 100% of the game. Probability for getting K wins in N matches is calculated. And we're talking so if you have 5 games and you want to know if I play, how many wins in those 5 games should I get? What's a percentage on those? And the probability for getting K wins in N matches is calculated by Px equals K equals NCK, P to the K, Q to the N minus K. Here, P is the probability of success and Q is the probability of failure. And so we can do total games of N equals 5, where K equals 0, 1, 2, 3, 4, 5. P, which is the chance of winning, is 0.75. Q, the chance of losing, equals 1 minus P, which equals 1 minus 0.075, which equals 0.25. The probability that Barcelona will lose all of the matches can then just plug in the numbers and we end up with a 0.0009765,625. So a very small chance they're going to lose all their matches. And we can plug in the value for 2 matches. Probability that Barcelona will win at least 2 matches is 0.0878. And of course we can go on to the probability that Barcelona will win 3 matches, the 0.26, and of course 4 matches, and so on. And it's always nice to take this information and let's find the cumulative discrete probabilities for each of the outcomes. Where Barcelona has won 3 or more matches, x equals 3, x equals 4, x equals 5. And we end up with the p equals 0.264 plus 0.395 plus 237, which equals 0.89. In reality, the probability of Barcelona winning the series is much higher than 0.75. And it's always nice to put out a nice graph so you can actually see the number of wins to the probability and how that pans out with our binomial case. Continuing in our important terminology, location. The location of the center of the graph depends on the mean value. And this is some very important things. So much of the data we look at, and when you start looking at probabilities, almost always has a normalized look, like the graph in the middle. But you do have left skewed, where the data is skewed off to the left, and you have more stuff happening off to the left, and you have right skewed data. And so when this comes up and these probabilities come up where they're skewed, it's really important to take a closer look at that. Mostly you end up with a normalized set of data, but you got to also be aware that sometimes it's a skewed data. And then the height. Height of the slope inversely depends upon the standard deviation. So you can see down here the standard deviation is really large. It kind of squishes it out. And if the standard deviation is small, then most of your data is going to hit right there in the middle. You're going to have a nice peak. And so being aware of this, that you might have a probability that fits certain data, but it has a lot of outliers. So if you have a really high standard deviation, if you're doing stock market analysis, this means your predictions are probably not going to make you much money. Where if you have a very small deviation, you might be right on target and set to become a millionaire. Which leads us to the z-score. Z-score tells you how far from the mean a data point is. It is measured in terms of standard deviations from the mean. Around 68% of the results are found between 1 standard deviation. Around 95% of the results are found between 2 standard deviations. And you read the symbols. Of course, they love to throw some Greek letters in there. We have mu minus 2 sigma. Mu is just a quick way. It's a kind of funky U. It just means the mean. And then the sigma is the standard deviation. And that's the O with the little arrow off to the right, or the little waggly tail going up, the O with a line on it. So mu minus 2 sigma is your 95% of the results are found between 2 standard deviations. Central limit theorem. This goes back to the skew. If you remember, we were looking at the skew values on this previous slide. Have left skewed, normalized, and right skewed. When we're talking about it being skewed or not skewed, the distribution of the sample means will be approximately normally distributed, evenly distributed, not skewed, if you take large random samples from the population with the mean, mu, and the standard deviation, sigma, with replacement. And you can see here, of course, we have our mu minus 2 sigma and the spread down here, the mean, the median, and the mode. And so when you're talking about very large populations, these numbers should come together and you shouldn't have a skewed value. If you do, that's a flag that something's wrong. That's why this is so important to be aware of what's going on with your data, where your samples are coming from, and the math behind it. And if we're going to do all this, we got to jump into conditional probability. The conditional probability of an event A is a probability that the event will occur given the knowledge that an event B has already occurred. And you'll see this as Bayes' theorem, B-A-Y-E-S, Bayes. And this is read, I mean, you have these funky looking little P brackets, A, B. This is the probability of A being true while B is already true. And you have the probability of B being true when A is already true, so P, B of A. The probability of A being true divided by the probability of B being true. And we talk about Bayes' theorem, which occurred back in the 1800s when he discovered this. This is such an important formula, and it's not, if you actually do the math, you could just kind of do xy equals jk, and then you divide them out, and you're going to see the same math, but it works with probabilities, which makes it really nice. And so if you have you might have 8 or 9 different studies going on in different areas. Different people have done the studies, they brought them together. If we look at today's COVID virus, the virus spread, certainly the studies done in China versus the studies the way they're done in the US, that data is different in each of those studies. But if you can find a place where it overlaps, where they're studying the same thing together, you can then compute the changes that you need to make in one study to make them equal. And this is also true if you have a study of one group and you want to find out more about it. So this formula is very powerful, and it really has to do with the data collection part of the math and data science, and understanding where your data is coming from and how you're going to combine different studies in different groups. And we'll go ahead and go into a use case. Let's find out the chance of a person getting lung disease due to smoking. And this is kind of interesting the way they word this. Let's say that according to medical report provided by the hospital, states that around 10% of all patients they treated suffered lung disease. So we have kind of a generic medical report. They further found out by a survey that 15% of the patients that visit them smoke. So we have 10% that are lung disease, and 15% of the patients smoke. And finally, 5% of the people continued smoke even when they had lung disease. Not the brightest choice, but it is an addiction, so it can be really difficult to kick. And so we can look at the probability of A, prior probability of 10% people having lung disease. And then probability B, probability that a patient smokes is 15%. And the probability of B, if B then A, the probability of a patient smokes even though they have lung disease is 5%. And probability of A is B, probability that the patient will have lung disease if they smoke. And then when you put the formulas together, you get a nice solution here. You get the probability of A of B, probability that the patient will have lung disease if they smoke. And you can just plug the numbers right in, and we get a 3.33% chance. Hence, there is a 3.33% chance that a person who smokes will get a lung disease. So we're going to pull up a little Python code. Always my favorite. Roll up the sleeves. Keep in mind, we're going to be doing this kind of like the back end way, so that you can see what's going on. And then later on, we're going to create, we'll get into another demo which shows you some of the tools that are already pre-built for this. Let's start by creating a set. So we're going to create a set with curly braces. This means that our set has only unique values. So you have a list, you have your tuples, which can never change, and then you have, in this case, the set. So 4, 7, you can't create a 4, 7, comma 4. It'll delete the 4 out. So it's only unique values. And if you use dictionaries, quick reminder, this should look familiar because it is a dictionary where you have a value, and that value is assigned to, or that key is assigned to a value. So you could have a key value set up as a dictionary. So it's like a dictionary without the value. It's just the keys, and they all have to be unique. And if we run this, we have a set of 4, 7. We can also take a list, a regular setup, and I'm going to go ahead and just throw in another number in here, 4, and run it. And you can see here, if I take my list 1, 2, 3, 4, 4, and I convert it to a set, and here it is, my set from list equals set, my list. The result is 1, 2, 3, 4. So it just deletes that last 4 right out of there. And with the sets, you can also go in there and print, here is my set, 3 is in the set, and then if you do 3 in my set, that's going to be a logic function. And 1 in my set, 6 is not in the set, and so forth. If we run this, we get 3 is in the set true, 1 is in the set false, because 3, 5, 7 is another 1. 6 is in the set, 6 is not in the set, so not in my set. You can also use this with a list. We could have just used 3, 5, 7, and it would have the same response on there. Is 3 in? Usually you do if 3 is in, but 3 in my set still works on just a regular list. And we'll go ahead and do a little iteration. We're going to do kind of the dice one. Remember 1, 2, 3, 4, 5, 6. And so we're going to bring in an iteration tool and import product as product. And I'll show you what that means in just a second. So we have our 2 dice. We have dice A, and it's going to be a set of values. You can only have 1 value for each one. That's why they put it in a set. And if you remember from range, it is up to 7. So this is going to be 1, 2, 3, 4, 5, 6. It will not include the 7. And the same thing for our dice B. And then what we're going to do is we're going to create a list, which is the product of A and B. So what's A plus B? And if we go ahead and run this, it'll print that out, and you'll see, in this case, when they say product, because it's an iteration tool, we're talking about creating a tuple of the 2. So we've now created a tuple of all possible outcomes of the dice, where dice A is 1, 2, 3, 1 to 6, and dice B is 1 to 6. And you can see 1 to 1, 1 to 2, 1 to 3, and so forth. You remember we had a slide on this earlier, where we talked about all the different outcomes of a dice. We can play around with this a little bit. We can do in dice equals 2, dice faces 1, 2, 3, 4, 5, 6. Another way of doing what we did before, and then we can create an event space where we have a set, which is the product of the dice faces, repeat equals in dice. And we'll go ahead and just run this. And you can see here, it just again puts it through all the different possible variables we can have. And then if we wanted to take the same set on here and print them all out like we had before, we can just go through for outcome and event space, outcome and equals. So the event space is creating a sequence, and as you can see here, when we print it out, it stacks them versus going through and putting them in a nice line. And we'll go ahead and do something. Let's go print. Since we have the end printing with a comma, that just means it's not going to hit the return going down to the next line. And we'll go ahead and do the length of our event space. That'll be an important variable we're going to want to know in a minute. And of course, if I get carried away with my typing of length, we'll print it twice and it'll give me an error. So we have 36 different possible variations here. And we might want to calculate something like, what about the multiple of 3? What if we want to have the probability of the multiple of 3 in our setup? And so we can put together the code for the outcome and event space of x, y equals outcome. If x plus y, remainder 3, so we're going to divide by 3 and look at the remainder, and it equals 0, then it's a favorable outcome. And we're going to pop that outcome on the end there. And we'll turn it into a set. So the favorable outcome equals a set. Not necessary because we know it's not going to be repeating itself, but just in case, we'll go ahead and do that. And if we want to print out the outcome, we can go ahead and see what that looks like. And you can see here, these are all multiples of 3. 1 plus 2 is 3, 5 plus 4 is 9, which divided by 3 is 3, and so forth. And just like we looked up the length of the one before, let's go ahead and print the length of our F outcome, so we can see what that looks like. There we go. And of course, I did forget to add the print in the middle because we're looping through and putting an end on the setup on there. So we're going to put the print in there. And if I run this, you can see we end up with 12. So we have 36 total options. We have 12 that are multiple that add up to a multiple of 3. And we can easily compute the probability of this by simply taking the length of our favorable outcome over the length of the event space. And if we print it out, let me put that in there, probability last line, so we can just type it in. We end up with a 0.3333 chance. That's roughly a third. And we might want to make this look nice. So let's go ahead and put in another line there. The probability of getting the sum, which is a multiple of 3, is 0.3333. We can compute the same thing for 5 dice. And if we do this for 5 dice and go ahead and run it, you can see we just have a huge amount of choices. So it just goes on and on down here. And we can look at the length of the event space. And we have over 7,776 choices. That's a lot of choices. And if we want to ask the question like we did above, what is the sum, where the sum is a multiple of 5 but not a multiple of 3, we can go through all of these different options, and then you can see here D1, D2, D3, D4, D5 equals the outcome. And if you add these all together and the division by 5 does not have a remainder of 0, but the remainder is also of a division by 3 is not equal to 0. So the multiple of 5 is equal to 0, but the multiple of 3 is not. We can just append that on here, and then we can look at that favorable outcome. We'll go ahead and set that, and we'll just take a look at this. What's our length of our favorable outcome? It's always good to see what we're working with. And so we have 904 out of 776. And then, of course, we can just do a simple division to get the probability on here. What's the probability that we're going to roll a multiple of 5 when you add them together, but not a multiple of 3? And so we're just going to divide those two numbers, and you can see here we get 0.116255, or 11.62%. And so you can really have a nice visual that this is not really complicated math right here on probabilities. It's just how many options do you have, and how many of those are you possibly going to be able to come up with the solution you're looking for. And this leads us to a confusion matrix. A confusion matrix is a table which is used to describe the performance of a classification model on a set of test data for which the true values are known. And so you'll see on the left we have the predicted and the actual. And we have a negative, false negative, positive, true positive, and then we have false positive and true negative. And you can think of this as your predicted model. What does that mean? That means if you divided your data and you used 2/3 of it to create the model, you might then test it against an actual case for the last third to see how well it comes out. How many times was it true positive versus false positive? It gave a false positive response. And you can imagine in medical situations, this is a pretty big deal. You don't want to give a false positive. So you might adjust your model accordingly so you don't have a false positive. Say with a COVID virus test, it'd be better to have a false negative and they go back and get retested than to have 30% false positives where then the test is pretty much invalid. So in a use case like cancer prediction, let's consider an example where a cancer prediction model is put to the test for its accuracy and precision. Actual result of a person's medical report is compared with the prediction made by the machine learning model. And so you can see here, here's our actual predicted, whether they have cancer or not. You know, cancer, a big one. You don't want to have a false positive. A false negative. In other words, you don't want to have it tell you that you don't have cancer when you do. So that would be something you'd really be looking for in this particular domain. You don't want a false negative. And this is, again, you've created a model. You have hundreds of people or thousands of pieces of data that come in. There's a real famous case study where they have the imagery and all the measurements they take. And there's about 36 different measurements they take. And then if you run a basic model, you want to know just how accurate it is. How many negative results do you have that are either telling people they have cancer that don't, or telling people that don't have cancer that they do. And then we can take these numbers and we can feed them into our accuracy, our precision, and our recall. So accuracy, precision, and recall. Accuracy metric to measure how accurately the results are predicted. And this is your total true, where you got the right results, you add them together, the true positive, the true negative, over all the results. So what percentage of them were accurate versus what were wrong. When we talk about precision, is a metric to measure how many of the correctly predicted cases are actually turned out to be positive. So we have a precision on true positive. Again, if you're talking about like COVID testing with the viruses, you really want this to be a high number. You want this true that to be the center point, where you might have the opposite if you're dealing with cancer, where you want no false negatives. So this is your metric on here. Precision is your test positive, true positive plus false positive. And then your recall, how many of the actual positive cases we were able to predict correctly with our model. So test positive is the test positive plus the false negative on there. And we'll want to go ahead and do a demo on the naive Bayes classifier. Before I get too far into naive Bayes classifier, because we're going to pull it from the sklearn or the scikit, let's go ahead. Kind of an interesting page here for classifiers. When you go into the sklearn kit, there's a lot of ways to do classification. And I'll just zoom up in here so you can see some of the titles. There's everything from the nearest neighbor, linear, but we're going to be focusing on the naive Bayes over here. And this is just a sample data set that they put together, and you can see how some of these have a very different output. The naive Bayes, remember, is set up as probably the most simplified calculator or set of predictions out there. And so what we've been talking about with the true-false and stuff like that, where there's a belief that there is a independent assumption between the features, where the features are very assumed to have some kind of connection, then we can go ahead and use that for the prediction. And so that's what we're using as a naive Bayes classifier versus many of the other classifiers that are out there. For this, we're going to use the social network ads. It's a little data set on here. And let me go ahead and just open that up, the file. Here we go. It has user ID, gender, age, estimated salary, purchased. And so we have, you can see the user ID, male, 19, estimated salary, 19,000, and purchased 0. So it's either going to make a purchase or not. So look at that last one, 0, 1. We should be thinking of binomials. We should be thinking of simple naive Bayes classifier kind of setup. So if we close this out, we're going to go ahead and import our NumPy as NP. We're going to nice to have a good visual of our data, so we'll put in our matplot library. Here's our pandas, our data frame. And then we're going to go ahead and import the data set. And the data set's going to be, we're going to read it from the social network ads.csv. Then we're going to print the head just so you can see it again, even though I showed you it in the file. And x equals the data set iLocation. 2, 3 values, and y is going to be the 4, column 4. Let me just run this so it's a little easier to go over that. You can see right here we're going to be looking at 0, 1, 2 is age and estimated salary, so 2, 3. And that's what iLocation just means, that we're looking at the number versus a regular location. Regular location, you'd actually say age and estimated salary. And then column 4 is, did they make a purchase? They purchased something. So those are the 3 columns we're going to be looking at when we do this. And we've gone ahead and imported these and imported the data. So now our data set is all set with this information in it. And we'll need to go ahead and split the data up. So we need from the sklearn model selection, we can import train test split. This does a nice job. We can set the random state so it randomly picks the data. And we're just going to take 25% of it's going to go into the test, our X test and our Y test, and the 75% will go to X train and Y train. That way, once we create our model, we can then have data to see just how accurate or how well it has performed with our prediction. The next step in pre-processing our data is to go ahead and do feature scaling. Now, a lot of this will start to look familiar. If you've done a number of the other modules and setup, you should start noticing that we bring in our data, we take a look at what we're working with, we go ahead and split it up into training and testing. In this case, we're going to go ahead and scale it. Scale it means we're putting it between a value of -1 and 1, or someplace in the middle ground there. This way, if you have any huge you don't have this huge setup. If we go back up to here where salary is 20,000 versus age 35. Well, there's a good chance with a lot of the back-end math that 20,000 will skew the results, and the estimated salary will have a higher impact than the age, instead of balancing them out and letting the calculations weigh them properly. And finally, we get to actually create our naive Bayes model. And then we're going to go ahead and import the Gaussian naive Bayes. And the Gaussian is the most basic one. That's what we're looking at now. It turns out, though, if you go to the Simplilearn kit, they have a number of different ones you can pull in there. There's Bernoulli, I've never used that one. Categorical, complement, and here's our Gaussian. So there's a number of different options you can look at. Gaussian, when you come to the naive Bayes, is the most commonly used. So we're talking about the naive Bayes. That's usually what people are talking about when they're pulling this in. And one of the nice things about the Gaussian, if you go to their website, to sklearn, the naive Bayes Gaussian, there's a lot of cool features. One of them is you can do partial fit on here. That means if you have a huge amount of data, you don't have to process it all at once. You can batch it into the Gaussian NB model. And there's many other different things you can do with it as far as fitting the data and how you manipulate it. We're just doing the basics. So we're going to go ahead and create our classifier. We're going to equal the Gaussian NB. And then we're going to do a fit. We're going to fit our training data and our training solution. So X train, Y train. And we'll go ahead and run this. It's going to tell us that it ran the code right there. And now we have our trained classifier model. So the next step is we need to go ahead and run a prediction. We're going to do our Y predict equals the classifier.predict X test. So here we fit the data, and now we're going to go ahead and predict. And now we get to our confusion matrix. So from the sklearn metrics, you can import your confusion matrix. Just as saves you from doing all the simple math, it does it all for you. And then we'll go ahead and create our confusion metrics with the Y test and the Y predict. So we have our actual and we have our predicted value. And you can see from here, this is the chart we looked at. Here's predicted, so true positive, false negative, true negative. And if we go ahead and run this, there we have it, 65, 3, 7, 25. And in this particular prediction, we had 65 were predicted the truth as far as a purchase. They're going to make a purchase, and we guessed 3 wrong. And then we had 25 we predicted would not purchase, and 7 of them did. So there's our confusion matrix. At this point, if you were with your shareholders or a board meeting, you would start to hear some snoozing if they were looking at the numbers. And you say, hey, here's my confusion matrix. So let's go ahead and visualize the results. We're going to pull from the matplot library colors, import listed color map. And this is actually, my machine's going to throw an error because this is being, because of the way the setup is. I have a newer version on here than when they put together the demo. And we need our X set and our Y set, which is our X train and Y train. And then we'll create our X1, X2. And we'll put that into a grid, and we set our X set minimum stop and our X set max stop. And if you come all the way over here, we're going to step 0.01. This is going to give us a nice line, is what that's doing. And then we're going to plot the contour, plot the X limit, plot the Y limit, and put the scatter plot in there. And let's go ahead and run this. To be honest, when I'm doing these graphs, there's so many different ways to do that. There's so many different ways to put this code together. To show you what we're doing, it's a lot easier to pull up the graph and then go back up and explain it. So the first thing we want to note here when we're looking at the data is this is the training set. And so we have those who didn't make a purchase. We've drawn a nice area for that. That's defined by the naive Bayes setup. And then we have those who did make a purchase, the green. And you can see that some of the green dots fall into the red area and some of the red dots fall into the green. So even our training set isn't going to be 100%. We couldn't do that. And so when we're looking at our different data coming down, we can kind of arrange our x1, x2, so we have a nice plot going on, and then we're going to create the contour. That's that nice line that's drawn down the middle on here with the red-green. That's what this is doing right here with the reshape. And notice that we had to do the dot t. If you remember from NumPy, if you did the NumPy module, you end up with pairs, x1, x2, x1, x2, next row, and so forth. You have to flip it so it's all one row. You have all your x1s and all your x2s. So this is what we're kind of looking for right here on this setup. And then the scatter plot is, of course, your scattered data across there. We're just going through all the points. That puts these nice little dots onto our setup on here. And we have our estimated salary and our age. And then, of course, the dots are, did they make a purchase or not? And just a quick note, this is kind of funny. You can see up here where it says x set, y set equals x train, y train, which seems kind of a little weird to do. This is because this is probably originally a definition. So it's its own module that could be called over and over again. And which is really a good way to do it, because the next thing we're going to want to do is do the exact same thing, but we're going to visualize the test set results. That way we can see what happened with our test group, our 25%. And you can see down here we have the test set, and if you look at the two graphs next to each other, this one obviously has 75% of the data, so it's going to show a lot more. This is only 25% of the data. You can see that there's a number that are kind of on the edge as to whether they could guess by age and income they're going to make a purchase or not. But that said, it still is pretty clear. It's pretty good as far as how much the estimate is and how good it does. Now, graphs are really effective for showing people what's going on, but you also need to have the numbers. And so we're going to do from sklearn, we're going to import metrics, and then we're going to print our metrics classification report from the y-test and the y-predict. And you can see here we have precision. Precision of zeros is 90. There's our recall, 0.96. We have an F1 score and a support. And we have our precision, the recall on getting it right. And then we can do our accuracy, the macro average, and the weighted average. So you can see that it pulls in pretty good as far as how accurate it is. You could say it's going to be about 90% is going to guess correctly that they're not going to purchase. And we had an 89% chance that they are going to purchase. And then the other numbers as you get down have a little bit different meaning, but it's pretty straightforward on here. Here's our accuracy, and here's our micro average and the weighted average and everything else you might need. And if you forgot the exact definition of accuracy, it is the true positive, true negative over all of the different setups. Precision is your true positive over all positives, true and false. And recall is a true positive over true positive plus false negative. And we can just real quick flip back there so you can see those numbers on here. Here's our precision, here's our recall, and here's our accuracy on this.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science, because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In our meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She is a curious soul who asks a lot of whys, one of the many traits of a good data scientist. Now, she gears up for data acquisition to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In her project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and dashboards. And then finally, she deploys and maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Well, that's how Emma completes the data science project. We have seen the daily routine of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques, along with genomic data, provides a deeper understanding of genetic issues in reaction to particular drugs and diseases. Logistic companies like DHL, FedEx have discovered the best routes to ship, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, machine learning engineer, deep learning engineer, data engineer, and of course, data scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data needs you.
Picture this, you're shopping online and suddenly you see a product that feels like it was made just for you. How did they know? It's not by chance, it's data science. Data science helps businesses understand what you like, predict what you need next, and improve the way we shop and use technology. And here's the best part. Data science isn't just about watching Netflix. It's one of the fastest growing careers in the world right now. In fact, the US Bureau of Labor Statistics says that data science jobs are expected to grow 36% by 2033, way faster than most of the other jobs. Companies everywhere are using data to make smarter decisions. That means the demand for data scientists is huge. And let's talk about the salary. You're probably wondering, how much can I earn actually? Well, for entry-level position, data scientists in the US are earning around $152,000 per year right now. And by 2025, some can make as much as $230,000. And in India, starting salaries range from 50,000 rupees to 1 lakh per month, and the experienced professionals can earn more than 5 lakh rupees per month. That's impressive, right? But the best part is, as a data scientist, you won't just stop here. The skills you develop in this role, like machine learning, data visualization, and statistics, are highly transferable and crucial for moving into AI roles. So whether it's becoming an AI engineer or an AI specialist, the foundation you build in data science will help you level up and pursue exciting, high-paying opportunities in the AI field. Now, if you're thinking, this sounds great, but where do I even start? Well, that's exactly what the professional certificate course in data science from IIT Kanpur and Simplilearn is designed to do. It will get you started and make sure you're ready for this booming industry. In this 11-month live online interactive program, you will learn the skills you need to become a data science professional. No more theory, no more fluff. You get hands-on projects, live classes, and mentorship from IIT Kanpur faculty, plus real-world industry expert who will help you build your skills. So this course comes with exciting, amazing features that makes learning even more impactful. 8 times higher interaction in live online classes with industry expert. Regular live online classes conducted by experienced professionals who bring real-world knowledge into every session. You'll also get to master 13 plus key skills including generative AI, prompt engineering, ChatGPT, explainable AI, conversational AI, NLP, and many more. These are the skills that top companies use every day, and you'll gain hands-on experience with 14 plus industry tools like Python, SQL, Tableau, DALL-E 2, Midjourney, TensorFlow, and more. And by the end of this course, you will be ready to tackle real-world challenges using these powerful tools and techniques. But we are not just talking about textbook and theory. You'll work on 25 plus real-world projects, giving you hands-on experience with the tools and skills you'll use in the industry. For example, our first project would be about sales analysis. You'll use Python to analyze a clothing company fourth quarter sales data across Australian states, helping the company make informed decisions. The next project would be about employee performance analysis, where you learn how to build machine learning models to understand the factors influencing employees' turnover. Our third project would be about e-commerce, which will help Amazon improve its recommendation engine to offer better recommendation to customers. Upon successful completion, you'll receive a program certificate directly issued by the ENI City Academy IIT Kanpur within 45 days of completing your cohort. This prestigious certificate will help you boost your resume and show potential employers that you have mastered the skills needed to succeed. You'll also benefit from masterclasses delivered by distinguished IIT Kanpur faculty who bring their deep expertise in this course. Plus, you will be exposed to trending tools like ChatGPT, GenAI, and prompt engineering. Now, if you're wondering who will be teaching all of this, then the IIT Kanpur faculty is here for you. These experts have been in this field for years and have worked with the top companies. You'll also get masterclasses from them, and they will guide you through the learning process. You're not just learning from a textbook, you are learning from the people who have been there and done that. And the best part is, once you have learned the skills, Simplilearn's Career Assistance team will help you take to the next step, which will help you to build a killer resume, show you how to stand out top recruiters, and even give you access to mock interviews. Plus, you will also gain access to exclusive networking events and hackathons to connect with industry professionals. Along with Simplilearn's Job Assistant, you'll also get access to IIT Kanpur's Career Services, helping you connect with top recruiters and land interviews with leading tech companies. So upon finishing this course, you'll be ready for top data science roles like data scientist, machine learning engineer, AI specialist, and business analyst. The good news is top companies like Amazon, EY, Fidelity Investment, Johnson & Johnson, Vodafone, Accenture, Infosys, and Nvidia is looking for professionals just like you. And with salaries in the US hitting around $230,000 plus and in India reaching up to 5 lakh per month, your career outlook looks great. So what will you be actually learning in this course? So here's a sneak peek of the syllabus which you'll be learning in this course, which is the foundation in Python, SQL, and mathematics, core data science like machine learning, data visualization, NLP, special topics like GenAI, ChatGPT, prompt engineering, and you'll also work on industry projects which we have already mentioned before. You'll also have the option to choose electives like data storytelling with Power BI and business analytics with Excel to tailor your learning experience and focus on the areas that interest you the most. So don't wait, hurry up and enroll now and find the course link in the description box below and in the pinned comments.
Have you ever wondered how your favorite online store seems to know exactly what you are looking for? Every time you browse, add to cart, or wishlist an item, you are leaving clues about your style, favorite colors, brands, and even shopping times. Data scientists jump in, analyze these patterns, and create a super personalized shopping experience. Suddenly, the store is showing you just the right pieces at just the right time, almost like it's reading your mind. That's data science, turning your clicks into a shopping spree crafted just for you. Hello everyone, welcome back to Simplilearn's YouTube channel. If you're already a data science enthusiast or just got curious about this exciting field, you're in the right place. Today in this video, I am diving into 10 essential steps to help you become the next in-demand data scientist and land that dream job. No more waiting, let's dive right in and get you on the path to your future in data science. So let's see the 10 essential steps to become the next data scientist in demand. Step number 1 is programming languages. Starting with Python is a great move because it's simple, versatile, and widely used in data science. Python's straightforward syntax makes it beginner-friendly, helping you grasp programming basics quickly and dive into data science libraries like Pandas, NumPy, and Matplotlib with ease. Adding R to your skill set is valuable because it excels at statistical analysis and data visualization, two essential parts of data science. You can be comfortable with Python and R within a month or two. So, moving on to the next step, that is version control system. Learning a version control system like Git is essential because it allows you to track, manage, and collaborate and code effectively. With Git, you can save different versions of your work, making it easy to backtrack if something goes wrong or to experiment without losing progress. This is especially useful when working with complex data science projects where you might try out different models of analysis techniques. 1 or 2 weeks of practice along with Python and R is good to get started. Just a quick info guys, if you're really interested, Simplilearn's Data Science with Python course is designed to help you master Python programming and essential data science skills through hands-on projects and real-world applications. With 60 plus hours of blended learning, live expert sessions, and lifetime access to course materials, you will gain practical experience in data wrangling, visualization, data analysis, and more. This course is ideal for both beginners and professionals looking to advance their careers in data science. Get ready to dive into industry-relevant projects, enhance your Python skills, and prepare for exciting data roles with Simplilearn's specialized training. Do check for the course link in the description box below and pinned comments. Now moving on to the third step, that is data structures and algorithms. Learning data structures and algorithms is crucial for becoming a data scientist because they provide the foundation for efficient data handling and problem solving. Data structures like arrays, stacks, queues, and trees help you store and organize data in ways that make it easier and faster to access, process, and analyze. Algorithms, on the other hand, give you strategies to perform tasks like searching, sorting, and optimizing data operations, which are essential for handling large data sets. While many candidates struggle with DAC, mastering it gives you an edge, helping you stand out in the interviews and shine as a skilled data scientist capable of tackling the toughest data problems. Spend about 2 months in this, you will get in the shape for sure. Now moving on to the step number 4, that is SQL. Learning SQL is essential for data scientists because it enables you to access, manage, and manipulate data directly within databases where most real-world data resides. With SQL, you can create new tables, alter existing ones, delete unnecessary records, and run queries to filter, sort, and aggregate data. These abilities allow you to retrieve, clean, and organize data effectively, core skills needed for any data science role. It's easy and you don't have to spend more than a month to have a deep understanding of it. Now moving on to the fifth step, that is mathematics and statistics. Mathematics and statistics are essential for data science because they form the backbone of data analysis, model building, and interpretation. Topics like linear algebra, calculus, probability, and statistics gives data scientists the tools to understand data patterns, perform accurate analysis, and make data-driven decisions. Mastering these areas enables you to build robust models, validate results, and tackle complex problems confidently, making you a well-rounded and skilled data scientist. Make sure you spend 2 months to grasp these topics. Now moving on to the step number 6, that is data pre-processing and visualization. Learning data pre-processing and visualization is essential for a data scientist because these skills make you data accurate, insightful, and easy to understand. Python libraries like NumPy and Pandas are crucial for manipulating and creating data, enabling you to handle missing values, filter out noise, and prepare data for analysis. Once the data is ready, visualization lets you uncover patterns and communicate results effectively. Libraries like Matplotlib and Seaborn help create clear, impactful visuals, allowing you to interpret trends and convey insights in a way that's easily understood by others. Together with these tools, make data pre-processing and visualization fundamentals for effective data science. If you have a solid foundation on Python and mathematics, you will get a good understanding of data pre-processing and visualization in a month or two. Now moving on to the 7th step, that is machine learning fundamentals. Machine learning fundamentals involve understanding how algorithms enable computers to learn from data and make predictions on decisions without explicit programming. The two main categories are supervised learning and unsupervised learning. In supervised learning, models are trained on labeled data to make predictions, while in unsupervised learning, models find patterns in unlabeled data. Popular tools like TensorFlow, PyTorch help build and train complex models, especially for deep learning, while scikit-learn is essential used for simpler machine learning algorithms and data pre-processing. These tools make it easier to implement machine learning fundamentals effectively and build intelligent data-driven decisions. Dedicate about 3 months to understand the core of machine learning. Now coming to the next step, that is deep learning. Deep learning is a subset of machine learning that focuses on algorithms inspired by the structures of the human brain called neural networks. Deep learning uses neural networks with multiple layers, often dozens or hundreds, to learn complex patterns from large data sets. Specialized types like convolutional neural networks, that is CNNs, are great for image processing, while recurrent neural networks RNNs are used for sequence data like text or time series. Essential tools like TensorFlow, PyTorch make building, training, and deploying deep learning models more accessible, allowing you to create powerful AI solutions across various domains. I think it will take about 2 months to have a good hold on deep learning concepts and how to implement them. Now moving on to the 9th step, that is specializations. Once you have grasped the deep learning, it's like reaching a new level as a data scientist. Just as doctors specialize in areas in nephrology and cardiology, data scientists often choose to specialize in fields like natural language processing or computer vision. Natural language processing focuses on teaching machines to understand and generate human language, enabling applications like chatbots, sentiment analysis, and language translation. It's about making computers read, write, and even interpret human emotions through text or speech. Computer vision, on the other hand, is all about enabling machines to see and interpret images or videos. This field powers innovations like facial recognition, object detection, and autonomous driving. Now, you don't need to learn both. You can choose what interests you the most. Now, spend 1 to 2 months diving deep into one of these areas. Now moving on to the last but not the least step, that is big data. Big data refers to extremely large volumes of data generated rapidly from sources like social media and sensors. For data scientists, learning to handle big data is crucial, as it requires specialized tools like Hadoop and Spark to analyze and extract insights effectively. With companies relying on data-driven decisions, big data skills make you a highly in-demand professional in the field. Focus for about 2 months and you will be able to spot trends and patterns from datasets very easily.
Once you are ready, it's time to build a killer resume packed with projects that showcase your new skills. Start applying to jobs on platforms like Naukri and Indeed and supercharge your LinkedIn. Connect with data scientists, see what skills they are mastering, and learn from their journeys as well. Keep sharpening your own skills, and when the time comes, you will be ready to crush those interviews and land your dream data scientist role in 2025.
Step by step, we will go through all of this, and we'll make sure that we learn everything and we bring everything together towards the end, right? Without further ado, let me just straight away deep dive to business, right? To learn data science, right? And with this data science, there is also something which is prefixed, which is applied data science. And suffix for this is with Python. Right? Applied data science with Python, right? So there are two key concepts which are going to be a part of this course. The first one is the knowledge about data science, that what data science is. And then because we are doing an applied course, right? We are doing an applied course. I will try to tie up these concepts, which we will understand in data science, with a tool, right? Which is Python for you, right? We already know about 65% of Python, right? Which is the fundamental Python. And now we will be moving to the next step, to advanced Python, right? And using Python, right? Leveraging Python, we will be solving a lot of problems of data science, right? Using this. Okay. So the first few sessions, right? The first few sessions will be about making you abreast with Python, what Python is, right? What and what packages do we have? How do they work in reality, right? And all those things. And then we will be coupling it up with data science concepts. And then finally, towards the end of the session, in the last few classes, we will be doing, we will be taking a real data set. And on that data set, we will be applying all these concepts, right? To understand the data better, and we will be drawing inferences from that to convert that into information to take actionable insights. Using that actionable insights, taking a better decision, right? We'll do all of that in the actual way. Okay. So now, guys, if you understand this, then the next point of contention is data science, right? One of the most famous keywords on the planet right now, right? One of the most famous keywords in the planet right now. Do you think that these two things, okay, let me put it different way. What do you think that can be the possible explanation about this term data science? You know data, you know science. What do you think is going to follow in these sessions? What is data science to you as per these two words? Okay, so this is people made up of two words, right? Data and science, right? So what we are trying to do is we are trying to understand data, right? We are trying to understand data, right? And then do something to it, right? Understanding its science, understanding the nature, the behavior of this data, and converting it in something called as information, right? Do we know difference between data and information? Data is something which is completely raw, okay? It is completely raw. It has no meaning, right? It has no meaning, isn't it? For example, I give you the stats of some player, like suppose say Dhoni. I give you stats of Mahendra Singh Dhoni, right? That what were his scores, what is his name, what is his age, and you know, all those things. Now everything is there, right? But we don't know what to do about it, right? Do you think the score of Dhoni has any context, people? It has any context? No, right? But when I deep down, when I go and deep dive about it, right? What is the first thing you find out of scores? What is the first thing you find out of scores? You try to find the average of score, isn't it? That in last 10 innings, right? In last 10 innings, before this also, you need something which is called as a problem statement, isn't it? Now, for example, the problem statement is selectors wants to understand that whether Mahendra Singh Dhoni should be picked up. So there's a problem now, right? Selectors want to see that whether Dhoni is fit for the next tournament or not. So what we will do, we will now try to take the mean of the scores, right? For last 10 innings. And if the score is suppose X, we will try to compare this with Y. What is Y? Y is a reference, right? Y is a reference that we want to compare it against. Now, when you are doing this comparisons, when you are applying these techniques to this score, this is now slowly becoming information, right? And at the end of the day, once you have the strike rate, once you have the mean score of Dhoni, once you have his age, once you have his fitness score, all those things will now help you to take this particular decision, because now what you have is called as information, right? Because this has context, right? This has meaning, and this is usually processed, right? This is usually processed, right? This is usually processed. Now, what did we do? Now, what did we do here? If you will go and read about data science says, it is the art of collecting, right? Cleaning, analyzing, modeling, improving, right? And visualizing, right? Visualizing the data, right? If a person is adept in doing all these things, this person, people, is cumulatively called a data scientist, right? That person is called a data scientist, right? So before going to the definition of data scientist now, I will give you some more examples, right? I'll give you some more examples. Data science people, as I said, is a combination of these things, right? You have to collect the data, right? You have to collect the data, right? And this has a lot of things. Data can be collected from two types. One is primary, and the second one is secondary, right? What is the primary way of collecting data? From your IoT devices, right? From sensors, from your inbuilt machines, right? Then from your surveys, which you float, right? Questionnaires, right? All these things are primary ways. What is the secondary way of collecting data? Purchasing data, right? Using internet data, because you have not generated it. You are just using someone else's data, right? Something like transfer learning. What is transfer learning? Transfer learning is a technique where, suppose I am bank A and you are bank B, right? So bank A has created some model, right? Trained on their data. Now you are going to use the exact same model, right? You're going to use the exact same model, right? Maybe you're not seeing the data, but you are just using the property of data, like mean, median, mode, and a lot of modeling things, which will come, we will learn about them. And you use this model on your particular data, right? So in a way, you did not have enough data to create the model yourself, but you are now using someone else's model to run your data on it, right? So this is called as transfer learning. So this kind of collection is basically secondary data collection. So you can collect the data, right? Then you can perform data analysis, right? You can perform data analysis, right? How will you perform this data analysis? Using complex algorithms, right? Using complex algorithms, right? Some statistics, right? You can use artificial intelligence, right? Artificial intelligence. You can use machine learning, right? Right? You can use all these things for data analysis. Then you can transform the patterns into predictions, right? You can transfer these patterns into predictions, right? Which can be used for business decision making, right? For business decision making. Then you can validate the results, right? And present the results. Right? So this is like a complete life cycle of a data scientist, right? So before going further, let me give you what combinations do you need to have to become a data scientist. The first one is domain knowledge. Right? So what is domain knowledge? First of all, I told you, right, there will be a problem, right? You will be solving a problem. In any project of data science, you'll be trying to solve a problem, right? And the problem will be belonging to a particular domain. Even if you're working for yourself, right? Even if you're an entrepreneur, then also you'll be solving a problem. So this domain knowledge part includes things like understanding. It's a very important diagram. Understanding client requirement, right? Understanding the client requirement, right? Important criterions, right? Important criteria knowledge, right? For example, to give an example, suppose we have created a machine learning model, okay? Understanding the data, we have created a machine learning model whose accuracy is 90%, right? Is 90% a good accuracy? Yeah, fairly decent accuracy. Yes. Suppose you have to predict sales, right? You're selling something. Suppose you're selling clothes and you want to predict what will be the sales for the next week. When you use this model, whatever the output model gives you, what is going to be the accuracy of your output using this model? How much accuracy? 90%. But my question is, model is 90%. But my question to you is that if 90% accuracy is on sales data, a person like me will be very, very happy. Okay, very, very happy. I'll be probably dancing, right? But if you try to apply the same model, right, for a medical diagnosis case, will you be interested in getting operated in such a hospital or an institution where the accuracy is coming as 90%? Domain knowledge, right? Domain knowledge. We need to understand what are the exact requirements. We need to understand what are the exact expectations, right? And we need to know how much do we need to pivot, right? So the first thing in data science is these accuracies and everything are subjective, right? They are subjective. So for that, you need domain knowledge. Domain knowledge part, very important, guys. Very important, these three things, which I'm going to tell. Second part is people, the game changer, right? The second part is computer science. Now, if I take you back in history, okay, if I take you back in history in 1980s or somewhere, then how many of you think that data science is a new concept? How many of you think that data science is a new concept? I hope you all know it's not a new concept. Everyone knows that. Yep. It has been happening for ages. Just like you guys will be shocked if you already don't know. AI was coined in the year 1956. 1956 at the University of Dartmouth, AI was coined by Paul McCarthy, right? And we saw the boom of AI in the year 2010, right? Such a long journey. Same case with data science, because people back in the day, data science was called as data mining. Everyone heard about it? Data mining, knowledge databases. Yeah, we used to mine the data. Now, what were the problems? What were the hiccups of data mining? The hiccups for data mining was that we were doing everything manually, right? Now, if I give you 100 points, can you calculate the mean? Or let's say, if I give you 2 points to multiply, 2 multiplied by 3, how much time will you take? 2 seconds. Yep. How much time a computer will take? 2 seconds. If I give you to multiply 2489 multiplied by 200, how much time will you take to calculate this? Say 5 seconds. How much time computer will take? 2 seconds. Now, if I give you to multiply 2489 into 1954386, How much time will you take to calculate this manually? Maybe say 1 minute, 80 seconds, 1 minute. How much time a computer will take? Still 2 seconds, right? Still 2 seconds, right? And if I give you to calculate this over 200 times, you will take 200 minutes, right? Using parallel computing, computer will still take about 3 to 5 seconds, right? So are you understanding the power of computer? Do you understand this concept in this relationship? What was happening back then? What computer science did, people, was it revolutionized the way data mining was happening. And that thing now is called as, that thing now is called as data science, in which computer science is one of the most important contributors. So this is just one reason. Now, manually, right? Manually, if I give you, say, 1 million rows of data, right? 1 million rows of data, right? So how many pages will you need to store this data? Suppose your notebook is like this, right? These boxes, and here you are storing the data, 1 million. So maybe you can buy n number of notebooks. But now, do you think it's as easy in storing something in computer? Because back in the day, people, we had memory issues, isn't it? Memory constraints. So there is something called as Murray's law, right? Which says as the advancement in microprocessors will increase, the price of microprocessor will decrease, right? So this is what is happening right now. Back in 1980s, if I show you, right, guys, right? Yeah, 2.5 kg exactly, right? It was size of a fridge, hard disk, but now it fits in your palm, right? So this was enabled, the storage techniques, right? The processing techniques, the infrastructure, right? Things like big data. What kind of data do you think we will be dealing with, people, in data science? You all know the term, very famous term, the kind of data, big data, right? Everyone knows about big data. What is big data? Yes, a data which is fast, right? It has velocity, veracity, variety, right? So this kind of data needs to be stored. This kind of data needs to be processed. So which thing brought all these things into data science? It was given to us by computer science, right? So computer science, people, included things like database management, right? Data validation, right? Data infrastructure, right? Data infrastructure, right? Then we had languages, computer languages, which is Python right now for us, right? Again, do you think when you do this thing manually, right? Suppose you do this thing manually, how easy do you think it will become using something like Python or any other computer language to create complex models? How easy it will be to do that? To create the complexity in models, right? Where you can capture the non-linear nature. Isn't it, people? Isn't it? For example, let me tell you this. 2, 4, 6, 8, 10, dash. What do you think is the next number, guys? 12. If I tell you to define this to me in, okay, leave that. What do you think is going to be the next number here? What is the next number? 11. Next number? 25. Perfect. Now, guys, if I ask you to write these numbers, right, the way you predicted them, can you give me a function? F of x is equal to, what is the f of x here? It's 2x, right? It's 2x. F of x is equal to 2x. If I tell you to create a function, it will be f of x is equal to 2x. What will be the function here, guys? F of x will be equal to x plus 1. Yeah, x plus 1. Yeah. And here f of x will be equal to x square. Yeah. Now, the last example, right? Last example. What is the next number here? I don't want the number, I want the function. I want this so that I can generalize. Isn't it? How did you reach this figure? How many of you think it's not possible to determine this? How many of you think it is not possible to determine this? Yeah. How many of you think? What if I just change this question and ask you, how many of you think it is not possible to determine this manually? Same response, but now I say, how many of you think it is not possible to determine this with computers? Will your answer still remain no? Do you think I cannot approximate this function using computers? We have something called as deep neural networks, and they are called as universal function approximators, right? So this is the problem, people. This is the problem, right? I will show this to you when the time comes, right? I will remember this example and I will show this to you. But now what I'm trying to tell you is the things which seemed impossible manually was solved by what? It was solved by computers. The distribution of this is like this. Can you figure it out yourself? No, right? We cannot, isn't it? We cannot do that. So this kind of approximation will be given by what? It will be only given by machines, right? And this is, people, what data science is all about, right? It is what computer science did inside data science, right? I hope this is clear. I'm assuming a lot of you will be going for interviews and everything after this course, right? So this will be a very, very important thing for you to know, right? Often it is asked why data science is having computer science in it, right? The reason is this, okay? So this is the role of computer science inside data science. Now, people, the third thing, the third circle, which is one of the most parts, is maths and stats, right? Mathematics, statistics, which was optimization, right? Optimization of your models, right? Design of model, right? Now, guys, if you look carefully, in order to approximate this, what will you be playing with? You will be playing with a lot of data. You will be playing with a lot of mathematical concepts and statistical concepts, isn't it? What do you call this? This is maths, right? This is statistics and mathematics. Finding mean, median, mode, standard deviations, probability, statistics, all these will lead to this kind of result, isn't it? So this becomes the third wheel of this particular of this particular diagram, and this point of intersection, right? The sweet point of intersection is basically data science. Yeah, is particularly data science, right? So now, people, this point, okay, this point is basically representing data engineering, right? Data engineering, right? Data engineering is, people, the part of data science which enables us to capture the correct data, right? How the data will flow, how the data will be stored, how the data will be cleaned, right? All this is done by whom? It is done by data engineering. Just because, so am I right, guys? You will go for interviews, right, after this, and try to fetch yourself jobs in this domain, data science, AI, ML, if my understanding is correct. Is that the aim? Yes. So now, guys, there will be three types of companies. Or let's say, to simplify it, let's say two types. One is small and the other one is big, right? So in a small organization, if you become a part of small organization and you are the data scientist there, you can be involved in all of these things, right? All of these things. Possible, right? Your bosses and your management will expect you to construct all these flows, right? No computer science. You should know maths and stats, and you should have the domain knowledge. and you will be asked to do all of this. But if you are going to become a part of a big organization, usually all these roles are fragmented. All of these roles are fragmented, right? There is a separate data infrastructure team. There's a separate data governance team. Now, guys, when you go on to collect the data, can you collect any sensitive data about? Is it possible? Ethically, it's not right, and legally also it's not right. My question to you is, who will look after this compliance? Whose responsibility indeed it is to look after this compliance? Data scientist. So this is about fragmentation. If you are part of a big organization, this thing will be taken by someone else, right? But if you are a part of a small organization, you will be expected to do this all by yourself. If you are part of a big organization, then do you think you need to have this domain knowledge? The answer is no. Why? Because there will be separate set of people who are called as what? Who are called as business analyst. Have you heard about this position, people? Business analyst. What is a business analyst role? It is basically a technical translator, right? Who knows technical, who knows domain. And that person goes and talks to the client in a layman language, convert it into technical requirement, coupled with the domain knowledge, and give you the document. This is basically a medical engineering problem. So we need this, and you need to fulfill this criteria. But again, if you're part of a small organization, who needs to take care of that? Who needs to make sure that you know everything about a domain? You yourself, right? You yourself, right? Then people, this area usually represents whom? This area represents research and analysis. Why? Because we have people who have domain knowledge, and we have people who are knowledge of math stats. Have you heard about a position called as actuary in the world? Actuarial science. Actuaries are people who are basically dealing with domains which are very, very heavily data intrinsic, right? For example, finance domain, right? Finance is all about numbers. So there we go, actuarial science, and we have math, stats, optimization, model development, all of those things happening there. We are also at this point of time, people belonging to which section? Research and data analysis, right? And then people, there is the third intersection, right? There is the third intersection, which is this part, and this people is called as machine learning, right? Machine learning. Why machine learning? If you can combine the power of maths, stats, right, and you can combine the power of computer science, you will find yourself to be in a position where you can call yourself a machine learning engineer, right? How does a machine learning engineer becomes a data scientist? When they couple it up with the domain expertise, right? So in this course, people, in this course, we will teach you computer science. We will teach you a little bit about math stats, but what we cannot teach you is domain knowledge. Yeah. And making the base of what we are about to do very, very important to understand, right? If you understand this, then half the battle is won, right? So now to answer the question which was posted earlier, there are different things in the world of data science, right? So you can pick and choose anything, or you can do everything by yourself. If you guys are engineers, then I think you can be at this sweet spot going forward in life if you choose a domain for yourself. For example, you choose to be a part of automobile industry. You choose to be a part of medical industry. You choose to be a part of, say, retail industry. You choose to be a part of aeronautics industry, right? You choose to be a part of finance industry, right? So whatever you will choose, this thing will get developed over time, right? This is the most difficult out of these three. Try to give you the example, right? My domain was agricultural industry, right? The agri products. I have worked extensively in agricultural industry, right? So again, for now, in my current role, this is something which I don't have. I have this expertise, I have this expertise. So same will be with you, and you guys will develop this knowledge over the time. Now I will try to give you an example, right? Elections, to make you understand how data science can be used in one particular use case, okay? Maybe we can extend that to a lot of other use cases and examples, right? Talking about election season, right? Talking about the election season, right? we will try to understand how do we use data science, because it is very extensively used in this data science, right? Now, let me talk about the first phase. Let's say this is pre-election phase, right? Right, this is pre-election phase. In this pre-election phase, what do you think will be the tasks with which an agency like Election Commission of India will be doing? The first task can be that they will be doing the voter registration, right? Voter registration and data management, isn't it? Yeah, it will start with that. And what will be the things inside this? The first thing will be data collection, right? First thing will be data collection. So you will collect the data from all the registered voters, right? Maybe it can be their demographic information, where they live, what is their age, what is their gender, right? What is their past polling behavior? Have they turned out previously or not, right? All these details we can collect. Then can we also do data cleaning? Because I've told you, right, that there can be a lot of redundancies. Some person's name can appear twice, right? Some people can be mismatched. Suppose, for example, we have learned this in Python. Raghav, 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 right? Right? All these are what people? This is belonging to the same name, right? This is me. But for a computer, how many Raghavs are there? Different ones, all are different, right? So example like these, right? Some people might have died, they might not be existing anymore, right? So all this part will be taken care where people in the data cleaning process, right? Removing the duplicates, updating the new addresses, right? Correcting the information about every voter, all those things, right? And now, lastly, we can also include a flavor of data analytics, right? What will data analytics include in this? We can analyze the demographic data to identify eligible voters, isn't it? Yeah, people, till now we haven't understood this. Why it is not automated? How will you pick up all the how will you pick up all the details and nuances? Suppose you're filling a form, right? By mistake, you have, suppose you are 25 years of age. Suppose you have written 250. So does that mean I remove this? I remove this entry of yours? Because by mistake you have written your age as 250. Is age 250 possible in our current world? Never, right? So I will have to tell the machine that because this is a mistake, please convert it to 25, isn't it? This is called as imputation. So this is mostly a manual task, not manual, but you have to understand the problem manually and then code it on computer. Suppose someone has written their state as EDLHI, right? And country as IDIN, right? So what is this state referring to? What is this country referring to? The humans are very smart. India, right? We can say this is India. And if this is India, then what is this pointing out to? Delhi? Just because you said, and it's a leading question, I wanted to explain this. Tell me, is it possible to do this automatically? No, right? We have to employ manual rules, right? We have to tell, because who's more intelligent? Humans or machines? Humans, right? Machines are just more optimized, right? So we know through human intelligence that this is pointing to Delhi and this is not EDLHI. So this is data cleaning, right? Lastly, we have data analytics. So do you think people, based on these data points, we can understand that who are the eligible voters and maybe who are not registered yet, maybe who have not voted in the past? Can we do all those analytics and reach out to those peoples and persons? That's the first part. This is just the first part, pre-election phase. Now, moving on to the second part, right? Moving on to the second part. Let's say we say public opinion regarding the polling, right? The polling which is about to happen. The first thing will be you want to collect information about people, right? So can you go out and reach all 1.8 billion people in this country? That what is their likable vote for which party? Is it possible? 1.8 billion. Do you think it's possible for 1 billion? Do you think it's possible for 500 million? Do you think it's possible for 100 million? No, right? So basically, I'm talking about what I have something which is called as a population, right? And if I have to study about this population, which is 1.8 billion people, which is impossible, which you just said, what do I need to do? Should I stop my process? No, right? I will go and collect something which is called a sample, right? We always work in samples, right? Suppose someone says that a Coca-Cola bottle does not contain 500 ml of liquid, which it claims, right? Suppose someone has put this allegation. Possible that Coca-Cola bottles do not have 500 ml liquid, which they promise. Now, there are two ways to deal with this, right? There are two ways to deal with this. Either I go and collect all the bottles of Coca-Cola in the world. Possible? Never, right? So what will I do? I will go and pick up handful of bottles, right? Handful of bottles. So what is that handful of bottles? Those are called as samples. One last thing. Suppose someone says that because of an industry, all the fishes of the lake are dying or they are infected. Is it possible to go and collect and check all the fishes in the pond or lake? No, right? What will we do? We will collect again handful of fishes and we will test them, right? Again, samples. Now, how does the raw data collected? Raw data as in, I hope you understand this. This is no more about population. With this step being told, now you're dealing with samples. So now do you want to ask me how is sample created? Yeah. Now I'm coming to that. Now guys, there are a lot of, second point is how to sample, right? How to sample, right? So we have sampling techniques, people. One is called as probabilistic and one is called as non-probabilistic, right? I will not go in detail right now. I just want to tell you an overview. Probabilistic is, suppose you are manufacturing t-shirts, right? You're manufacturing t-shirts, right? And suppose you created 100 lots of 1,000 t-shirts, right? So this is box 1, box 2, box 3, box 4, up to 100, right? 100 boxes. And in each box, how many t-shirts are there? 1,000, right? Now, suppose you are a quality inspector. You're a quality inspector. Is it possible for you to go over all the 100 lots with all checking all the 1,000 t-shirts one by one? No, right? What will you do? You will sample. Again, you will sample. Now, the most common way of sampling these kind of problems is probabilistic sampling. What is probability? What is the probability of getting heads or tails when you flip the coin? Equally likely, 1 by 2 and 1 by 2. What is the probability of getting 1, 2, 3, 4, 5, 6 on a roll of a dice? 1 by 6. Now, what is the probability of picking any t-shirt from this first lot out of 1,000 t-shirts? 1 by 1,000. Yes. So do you think all the t-shirts have equal probability of being picked up without any bias? If you decide to draw 5 t-shirts, right, from each of this box, right, and suppose say 2 are defective and 3 are not defective, what will you do? Will you accept the lot or reject the lot? We have majority of t-shirts of non-defective, or let's say we will reject the lot. We will reject the lot. We will reject the lot. Let's say we will reject the lot. Okay. Though this is basically subjective as per the company policies, but let's say we reject it. Now, people, my question to you is, what if this entire batch had only 2 defective t-shirts? But now what will happen? The entire batch will be rejected. Yes. Let's say you sampled 1 t-shirt. Let's change the use case. I say you sampled only one t-shirt and that t-shirt was defected. Now you will reject the batch. And that is equally likely case. So this is called as probabilistic sampling, people. And there is no way you can go back. There is no way. You cannot say that, hey, sir, please allow this batch to pass because there is a chance that rest of the t-shirts are not defective. No, it is not the way that happens. It happens randomly. So, right, this is called as random sampling. Right? Random sampling. Now, suppose you are doing a cancer research, right? You're doing a cancer research, right? So for your cancer research, people, what kind of people will you need? People who had cancer in the past, isn't it? To know more about their problem, to know more about their medical condition. So is it possible, people, that in this use case, you can go and pick up any person from the population and ask them questions? No, right? That is not possible. So now, is the probability equally likely or it has changed when you pick the sample? It has changed. Now there is a bias which is introduced that you only want people who had cancer, right? So that kind of sampling, people, is called as non-probabilistic sampling, right? Non-probabilistic sampling. Clear? Now, sampling technique, right? Now, third thing in this same scheme can be, people, what? It can be the data collection, right? Data collection mode, right? That how do you collect the data? You can float a survey on, say, internet. You can go and stand outside a mall or office, isn't it? How will you can probably interview someone, right? Interview someone, right? You can have a group discussion. Yeah, all these techniques. Yes, no, maybe, right? In the same part, public opinion polling, right? Now, guys, so this was a brief introduction, right? And this can be extended to any industry, right? As of now, you can have example in the medical science, right? You can have an example in automobile, right? You can have an example in retail, right? Right? Then you can have example in manufacturing, right? You can have example in education, right? You can have example in sports, right? IPL analysis, cricket analysis, all these sports analysis, right? These are the most famous domains, right? They are the most famous domains. They are not topics, they are domains, right? In which data science is used extensively. So I'm just going to check, guys, in automobiles, there's a biggest example, self-driving cars. Yeah, autonomous driving. How do you think that's possible? Data science, again, like Tesla. Absolutely. Tesla is level 3. We have 5 levels. Level 3 is narrow AI. Level 4 is AGI and level 5 is super AI. We are going to move first, right, with the technical aspect, right, with the technical aspect in our data science course, right? Right, which is based on Python, right, because that is our base language which we have learned so far, right? So in Python, people, we will start and cover 4 of the packages right now. And as we move on to machine learning and other deep learning and everything, you will explore more and more packages. The first package we have to cover will be numpy, right? I'll explain you in detail what numpy is. Then we will cover pandas. Then we will cover matplotlib. And then finally, we will cover something called as Seaborn, right? We will cover something called as Seaborn. So these 4 packages inherently we have to cover in Python to make sure we are able to reduce the time in coding, right? We are able to reduce the time in coding, and using these packages immediately help us in getting the desired results, right? I hope you all remember the concept of modules we have covered in Python. Do you all remember functions and modules? You can use Jupyter Notebook. If your Jupyter Notebook is not installed, you can use something which is called as Google Colab, right? Go to Google, type Colab, right? Let's say you write Colab, right? And then you will see this option. Click on Google Colab and it will allow you to code in Python, right? So we are now going to discuss about the numpy package in Python. Okay, numpy package in Python. So numpy is a fundamental package for data science in Python, right? It is one of the most fundamental packages for practicing data science in Python, right? Why is that? Why is numpy so fundamental? What is so special? Numpy package gives us a new data type for handling data in Python called as ND arrays, right? ND arrays, which stands for n-dimensional arrays, right? N-dimensional arrays, right? This stands for n-dimensional arrays. So till now, we have studied about list, integer, tuples, strings, right? Out of which the data types such as list, tuples have been used to store data, right? Store data, right? And range used for generating new data, which is primarily sequential, right? Now there is one problem, right? There is one problem, and there should be a question. That there should be a question. Why do we need a new data type to work with data science, right? Why do we need this? Yep. So the answer to this question, people, the answer to this question lies in a small explanation, right? Yeah, lies in a small explanation, which is that Python is a high level language, right? Python is a high level language, right? And a high level language is usually very distant from hardware. A high level language is close to hardware or distant from the hardware. Did you not attend the Python programming essentials? What is the type of programming language which is closest to hardware? A low level language. If this is my hardware, yeah, this is my OS, this is my application layer, right? So hard level language, high level languages here, and low level languages here, right? Which is closest. So binary languages, assembly languages, right? All these are closest to the hardware because where is the processing happening? Where is the processing happening of the data? At the hardware, isn't it? Processing of data is happening at hardware. No hurry, actually it is happening at hardware, right? What is processing? Processing is signals of zeros and ones, right? What are zeros and ones? These are electric signals. These are the electric signals, right? Which is basically on and off, right? And it is communicated to the hardware through the help of resistors and microprocessors, right? Isn't it? Right? Why a computer only knows zeros and ones? Because zero is off and one is on, which is the electric current, right? Electric current to activate or deactivate certain things, right? True and false, gates, right? So it is happening at hardware. So now people, if you understand this part, then try to logically connect it to what I'm going to say. When you are studying data science, what kind of data you will be dealing with? Big data, right? And as the name suggests, it will have a lot of volume, right? It will have a lot of volume other than a lot of other things, right? It will be very, very big. And on this large volume of data, you will be doing processing. You will be doing processing. What does processing means? What does processing means? Operations. So where is this operation happening? This is happening in hardware. And for hardware, which is the closest language to hardware? A low level language. But now, people, we have a situation in front of us. What is the situation? That what are we trying to do data science with? What are we trying to do data science with? Python, right? And Python is what? A high level language, isn't it? Yeah. So there's a discrepancy. Yeah, a big one. Because high level language, these are slow in processing, right? These are very slow in processing, right? So for these kind of languages, to handle this kind of data and these kind of operations, yeah, is very difficult, right? So let's keep this part aside if you understand this. Now let's go to the second point, right? When you learned Python, on a scale of 1 to 10, how easy was it? The ease of use of Python? It's relatively a higher number, right? Relatively a higher number. So now guys, when I talk about data science, right? When I talk about data science, okay? Right? When I talk about data science, my thing is that this will be used by masses, right? Will be used by masses, a lot of people, managers, programmers, business analysts, data analysts, possible, right? Who are from non-technical background, who don't know coding, they also can do data science because data science is a general thing, isn't it? Understanding the data. It should not be limited by your capability to understand the technicalities of a very complex language. So for these people, which language is suitable? Which is Python, right? It is easiest to understand. It's a high level language, almost like English. Yeah. So Python is a simple language. So in this part, people, Python fits the bill, right? Which is a bigger thing. In the second part, when we talk about the operations, when we talk about the operations, in this part, there is a problem, right? Python fails, right? Python fails, right? Because it's a high level language. We said that, okay, there is a language called as C, right? Which is a middle level language, right? And C language, people, is used to create OS, operating systems. It is used to create networks, networking applications. It is used to create games, right? All the things which are close to hardware, C is used, right? So C fits this bill, right? C fits this bill. Python said that, okay, if C fits the bill and Python is written in C, written on C, right? It's written on top of C language. Now what happened was Python said, okay, if my intrinsic data types, my intrinsic processing is not suitable for data science, but my high level nature is, let's do one thing. Let's take C language and use its power, right? Use its power that it is very close to hardware, and let's create a new data type, right? Let's create a new data type which is written on top of C and which can integrate with Python seamlessly. And people, this new data type was called as array. And this was given to you by something called as numpy package, right? Numpy package. It defined a new data type, which was array. And along with defining the array, it gave various operations, right? It gave various operations one could perform on arrays, right? One could perform on arrays. It's simple, right? Program, the power of processing lied with C, right? It was lying with C. So we developed a new data type using C on top of Python, and that new data type was called as array. And this array was defined in a new module, which was called as numpy module, which told you how to create the arrays and then how to manipulate those arrays for doing data science. We had options like Java, we had options like C, right? We had options like Fortran to be used for data science, but we chose Python because of its simplicity and the simple syntaxes, so that people from non-programming background could also use Python to do data science, right? Now the limitation was that because it is slow, because of being high level, we needed something which could make it fast, and that was using an external data type which is not internal to Python, and that was array. And this array is defined inside a new module or a library called as numpy, which is numerical Python, right? Numerical Python. Back to the programming, right? Where we have understood, right, about this question, right? So numpy essentially is built on top of C language, which is compatible with Python. It leverages the power of closeness of C with hardware, right? C with hardware, which eventually makes the processing faster in Python, right? So this is what the first part is, right? This is what a first part is, right? Now the second thing is, people, so this is about the performance bit, right? This is the performance bit. The above is about the performance of Python, right? Now coming to the next part, which is the memory efficiency, right? Memory efficiency, right? So arrays created by numpy in Python are less memory exhaustive than lists in Python, right? And I will prove these points later on to you through code, right? In list, right? In list, each item is an object, right? Each item is an object, right? I hope you remember this, guys. Each item is an object, right? And it holds, right? It holds meta information like references and types, right? Etc. Right? A lot of information it holds, right? This makes list consume more memory, right? But arrays in numpy are contiguous, which means that they do not create objects, but rather directly store the data in continuous memory blocks, one after another, right? Also, the arrays are homogeneous in nature, right? You can only store the homogeneous data in array, unlike lists. In list, you could store different data types, right? But in arrays, you cannot, right? You have to store the same kind of data in the array, homogeneous. So it's a contiguous memory block, which is meaning that you can store data in continuity, right? One after another in the memory block. So the access is faster, the memory location and the memory efficiency is very higher, right? As compared to the native data type like lists or tuples in Python. Arrays are basically vectorized operations, right? I'll talk about to you with vectors. What are vectors? Right? They are the vectorized operations, and they are way more convenient to deal with as compared to list in Python. Right? In list, you have to go through a lot of loops, right? We saw that you have to go through the list comprehension, but you will see in Python pandas, in Python numpy, the vectorized operations are very simple, right? They are very simple, right? Again, for all this, I will give you examples, but it will take some time because you have to understand what arrays are first, right? Okay. Then the most important other packages, which are pandas, matplotlib, cbond, sklearn, scipy, all are written on top of numpy package. That's the reason, for this reason, it's called as fundamental package. All the other packages which make your life easier as a data scientist, where you don't have to worry about code, all these packages make our data science journey smooth because we have to worry less about code and more about logic. Yes. So for the understanding of these packages, it's very important that we understand numpy first, and then we move forward, right? Now, then let's get started. So the first step, right? The first step which you have to see, right? The first step which you have to see while using numpy package is basically from where will you import the package, right? From where will you import the package? So to import the package numpy, we write import numpy as np, right? Where np is an alias, right? It's an alias, right? So please do this. Import numpy as np, right? If you don't get any result for this, then you can write pip install numpy, right? Pip install numpy and just execute this, right? When you will execute this, it will give you this message, or it will download this package for you, right? Pip stands for Python index package, right? It is basically like Play Store, App Store, right? Or Windows Store for Python, right? So you are just going to these Play Store, Windows Store, App Store of your Python and asking them to download this for you, right? It is also called as the package manager, right? Pip. If it is done, you can also check the version. You can say np dot underscore underscore version underscore underscore, and it will give you the version of numpy, right? Numpy is an open source package, right? Yeah, that's about it. Yeah, it's an open source package, people, right? Open source package. And if you want to see the code, you can go to GitHub. Go to Google, write the code for numpy, it will show you it on GitHub, right? Done. So let's say okay. So I say we have, okay, before this, let me come to a little bit of theory before I do this with you. So now guys, I said that numpy has arrays as data type, right? And this is written on C, which runs directly on hardware. Also, this numpy array is basically a vector, right? It's basically a vector. Now, what is a vector, people? What is a vector? A vector is a quantity which has sign plus magnitude, right? It has a sign and magnitude. If I say this is a Cartesian space, this is I, this is J, and I say this is 3I and 4J, right? 3I cap, 4J cap. So this is a vector, right? And this is the direction. Guys, if you have studied elementary maths, you would know this. Yes, people, this is a vector. If I draw another like this, then this is another vector. So I will call this, say, 2I and 5J. Yep, this is another vector. And this is the theta, right? This is the direction. This is the direction. And what is the magnitude? 3I, 3 square plus 4 square, which is 9 plus 16, which is 25 under root, which is 5. So the magnitude of vector is 5 and direction is equal to theta. This is a vector quantity. Now, what is this? What is this? This is a scalar. This is a scalar. Yeah. Only magnitude. Isn't it? This is scalar, only magnitude. And then I have 2, 3. Right? This is what? This is a vector. It has 2 dimensions or 1 dimension. Only 1 dimension, right? This is 1 dimension vector. Yep, 1 dimension vector. Now, if I say this 2, 3, 4, 5, what is this called? This is called a matrix, right? This is called a matrix, which is what? Collection of vectors. And this collection of vectors matrix is called as 2-dimensional, right? It is called as 2-dimensional. Now, if you have this, so these are stacked behind each other. This is 1, this is 2, this is 3, right? So we have 3 layers in matrix. So how many dimensions will be this, people? 1 dimension, 2 dimension, and 3 dimension. This is a 3-dimension matrix, right? Or 3-dimension vector, or 3-dimension array. I'll repeat once again. What is a single value? A single value is called as a scalar, right? It only has magnitude. Now, when you have multiple values, right? This is called as a vector. It has a direction, it has a magnitude, and this is single dimension. Now, multiple vectors, right? Like this, or maybe you can say like this, right? Are you understanding why I'm calling it 1 dimension? It can be either this dimension or it can be this dimension. In any dimension you stack 2 vectors, you will get yourself a matrix, right? You will get yourself a matrix, which is now 2 dimensions. It has rows and it has columns, right? Now, if you stack multiple such matrix one after another, right? This becomes a 3-dimensional matrix. And this can go up to how many dimensions, people? How many dimensions this can go up to? It can go up to, this can go up to n dimensions, right? N dimensions, right? So now do we get it? Why do we call it ND arrays? Yeah, n dimension arrays, right? That why are we calling something what? Right? N dimension arrays. We are only capable of viewing 3 dimensions, people. It can go up to 100 dimensions, 500 dimensions, 1000 dimensions, any dimensions. Scalars are least important. Vectors are more important. So now we have multiple dimensions in arrays, namely 0D, 1D, 2D, 3D, and so on till the ND, right? ND arrays, right? Now, let's create our first array, right? Let's create our first array. And this will be a 0-dimension array, right? 0-dimension array. How will you create this? You will say ARR0 is equal to NP dot array, and you will mention what a scalar value is. What is a scalar value? It is a simple value. I say 2, right? NP dot array equal to 2. And when you will now check or print the type of ARR0, it will tell you class numpy ND array, right? It is a 0-dimension array. And if you want to check the dimension, you just have to write ARR0 dot ndim, right? And it shows you that there is 0 dimensions present. So what is this in short? This is a scalar. I have entered a single value, people, 2, 200, 500, whatever you want to enter. And the syntax is np.array. np.array. You are instructing numpy package to fetch the function array on method array and convert this into that particular data type, right? Array 0. And when you check the type is nd array, but what is the dimension of this nd array? This is 0, which is nothing but a scalar, right? We have created this. This is what we have created, right? Now, guys, if I created this list, right? Say lis is equal to, yeah. So this was a list, right? This was a list, and this is what, people? What is this that we have just studied? According to that, what dimension is this list? So what I'm trying to do is, I will create a 1D array with a, or let's say from a list, right? Let me show you how do we do that. Okay. So I say, Hari, read the error. Name ARR not defined. Why? Because you have created array from AAR0. Come on, Hari. Right? I will create a one-dimension array. How will I do that? People, I will say ARR1 is equal to np.array. And can I pass 1D list inside this? Or can I say I can pass LIS inside this? When I do this, people, now see what will happen. ARR1 will be equal to this, right? And if you say, let me say print ARR1, it will be like this. Okay. This is your ARR1.ndim. You will see that it gives you 1, right? This is a one-dimension array, right? One-dimension array. Yes. So for example, when I say scalar, right? When I say scalar, I say 35, right? When I say vector 1D, I say, so these are suppose my marks, right? Now I say 35, 40, 50, right? So now what are these? My marks in 3 subjects. Yeah, marks in 3 subjects. This is my, say, Hindi, this is English, and this is maths, right? Or let's say science, because not everyone has Hindi. Science, English, and maths, right, guys? Now, if I have to create a matrix of 2 dimension, what will I write? So that means this is one student. This is one student, people. Isn't it, guys? Yes, no, maybe. So now in matrix, we will have what? We will have multiple students. Yes, no, maybe. In a matrix, people, we will have multiple students. Suppose this was S1. Now you will have S1, S2, S3, S4, like this. And each student will have their own individual list of marks. So can I say that I'm making a nested list? Can I say that, people? I'm making a nested list. So now let's make it. Okay. From a nested list. Okay. A nested list. So I'll say ARR2 is equal to np.arraylist. I will have to create a list first. LIS2 is equal to, so this is my first bracket. What is this bracket representing? This bigger bracket. Now I will put another bracket inside this and I will write 1, 1, 2, 2, 3, 3. I'll put a comma again, right? A comma. Then I will say 4, 4, 5, 5, 6, 6, comma 7, 7, 8, 8, 9, 9. Right? I'll do this. Right? Now I will say list 2, 2. When you will do this, you will see that an array like this has been created. Right? Like this, ARR2. Right? This has been created. Right? When we check the dimension, it is 2-dimension array. Right? Yep. Marks of 3 different students in 3 different subjects. And this is the same technique you can create a 3-dimension array. How will you create a 3-dimension array, people? If I go here, how will you create a 3-dimension array now? Now, suppose I have data in this, and this is my master list. Okay, this is my master list. In this, I have data, and this can be represented like this. This is my first matrix, isn't it? And this is the vector inside this. V1, V2, V3. Then this can be called as M1. And now to create a 3-dimension setup, how many M1s do you need? You need multiple M1s, isn't it? You need M1, M2, M3, multiple matrix like this, people. Like this, matrix 1, matrix 2, matrix 3. So what will you do? You will have what, people? You will have another yellow, right? And you will have inside this yellow multiple purples, isn't it? Right? Again, like this. Yep. Like this you will have it, people. So can I say, people, can I say that as I am increasing the dimensions, as I am increasing the dimensions, I am putting 0D, right? And okay, again in this V1, do you think you will have multiple scalars, people? Can I say that? Can I say multiple scalars create a vector, multiple vectors create a matrix, and multiple matrix create one 3-dimensional matrix? Can I say that? Let me talk to you about an image, right? Image, right? What is an image made up of, people? What is an image made up of? Pixels? Yes or no? No, not frames. Frames is basically videos. Pixels are creating an image, right? So we have how many pixels here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? Suppose this is one vector, right? This is one vector, and this is one scalar, right? Scalar 1, scalar 2, scalar 3, scalar 4, and this will make vector V1. This is V2, V3, V4, and together, can I call this M1 and call this blue? So for a colored image, how many channels are there, people? How many channels are there? What do we call it? We call it the image as RGB image. That means red, green, Blue. So this is blue part. So similarly, you will have a red part in front of it. Then you will have a green part. And then finally you will have a blue part. Yeah. Are you understanding, guys? Why do we require three-dimensional arrays? Yes. Suppose now you want to make a change at this pixel. So you will go to the third layer, which is the blue layer. Then you will go to the third column. You will go to the third column and third row. And this is how you will reach this pixel. Everyone? Yes, no, maybe? Yes. So this is the reason why we need to create a 3D array, right? To ingest information like this, right? To ingest information like this. So we can create a 3D array also, right? Right? And how did I tell you? How many brackets will I have? Squared brackets? I will have 3 squared brackets. So now this is just one student, right? Now I'll put a comma here, right? I'll put a comma here and I will start. Right? I'll do this. I'll say this list 3, ARR 3, list 3, ARR 3, ARR 3, ARR 3. Right? And now you will see that there is a 3-dimensional array. Right, guys? Right? This is a 3-dimensional array. Yep. Moving on. There are multiple ways to create arrays, right? The first one we have done. So we have done from lists. From list we have done. Then second will be from, we can create a 0 array, right? We can create ones array, right? Then we can create custom array, right? I will show this all to you, right? I'll show this all to you. So let's start with the ones array, sorry, zeros array, right? What do you have to do? You have to write, so let's say 0 underscore ARR 0, okay, a 0 dimension 0 array. So you say np dot zeros, right? And you create a 2, right? A 2, right? And if I say 0 dot endim, right? You will see it is a 1-dimension array, right? It is a 1-dimension array, right? So 2 is by default taken as, so let me just show this to you. It will look like this, right? It is taken as horizontal. What is the dimension of this, guys? A vector. What is the dimension of this vector? No. It's 1. It is basically 2 cross 1, right? 2 comma 1. Sorry, 1 comma 2. My bad. 1 comma 2. Isn't it? Now, what if you had to create a 2 cross 1? What if you had to create a 2 cross 1? Right? So let me just show that to you. So I say, wait. Like this, okay? Now when I do this, I say ARR1 and I say here 2 comma 1, right? I say 2 comma 1. Now you will see, people, what will happen to this. Now, because you have created, right, specified 2 dimensions, right? What will this be converted to now? What will this be converted to? This will be converted to a two-dimension vector. By default, it was this, right? Which was this vector, right? By default, it was this vector, right? What is the dimension of this vector? 1 cross, how many values you put here, right? 1 cross 2 like this. So we call this only one dimension. We call this only one dimension. But now when I will run this one, you will see, yes, 2 cross 1. And now you will see this is 2 dimension, right? You see this is 2 dimension now. Clear, people? Just the orientation has changed, but now you see the bracket, there are 2 brackets now. Because what have you now instructed? You have now instructed Python and rather numpy to create the vector as 2 cross 1. So you have said, give me this 0 and give me this 0 here. So the moment you do this, you are now specifying the rows and columns. Now this 2, 1, right? Let's say this is 2, 1. Now let me create another 2 dimension matrix for you. Let me call this 10, 10, right? So how many rows and columns will it have, people? How many rows and columns will it have? I will say 2, 1, 0. It will have 10 rows and 10 columns like this. You saw this? Yeah, 10 rows and 10 columns, right? By default, it is 1 cross 2 like this. It is a one-dimensional vector and this is a two-dimensional vector. What about a three-dimensional vector? 0 dot 0 underscore ARR3 is equal to NP dot zeros, right? NP dot zeros, right? Should I just write 3, 3, 3 and I should check for this? Yep. You will have a 3 cross 3 vector, 3 cross 3 matrix with 3 matrix stacked behind each other, right? If I say 4, this will be 4. So how do we read this? Number of layers, number of rows, and number of columns. So can you help me with a syntax? Can you help me with a syntax which can create me a 3D matrix of 5 layers, 3 rows, and 3 columns? What will I write? 5 layers, 3 rows, and 3 columns. What will I write? Five, 3, 3. Yeah, you'll get 5 layers, 1, 2, 3, 4, 5, right? Like this. Suppose you have to represent an image with say RGB channel and say 256 and 256 pixels. How will you create this? So I'll say img, right? Image is equal to np dot zeros, and I will say inside this 3 channel 256 cross 256, right? And when you will just run this image, it will be like this, right? It will be like this. This is 1 channel, this is 2 channel, and this is 3 channel. And we understood that numpy is a fundamental package for data science in Python, right? This package gives us a new data type to work with, which is called as n-dimensional arrays, right? Now, what are arrays? What are arrays? Arrays are nothing but vectors, right? Which are stored in a contiguous block of memory, which means they are stored continuously one after another, and they do not get converted into the object, unlike the list, and they are way faster. They are more memory efficient than list. I will prove this start to you today with the help of example, through the help of code, right? So why numpy arrays? Because numpy is a package which is built on top of C language, which is compatible with Python, and C, being a middle level language, interacts directly with the hardware. So whatever operation you run, in a fact that is getting directly executed on the hardware itself, right? That is the reason why the performance is way better when we try to use the n-dimensional arrays. Along with this, these syntaxes, the type of syntaxes we used to type in list, I will show that to you also today with the help of example, are way simpler when you try to do them with ND arrays, right? So arrays are basically vectorized operations, right? And they're also very convenient to deal with as compared to lists and other native data types in Python, right? And the most important part is that in our data science journey, whatever other packages we will use, right? Again, what are packages? They have predefined things stored for you so that you can leverage them and focus less on code and more on logic, right? You need to be aware about the logic more than the knowledge of the code, right? So we have packages for that, which contains methods inside them, which you can use, and without any further calculations, you can work with them directly, right? So that is how we started with numpy, right? And the syntax to import numpy was import numpy as np, where np was an alias, right? You could do pip install numpy if someone did not have access to numpy, if numpy was not coming by default, you can use pip install numpy, which is Python index package, right? And this is like Play Store, App Store, Windows Store for Python. All the packages are stored in pip, and you can call pip, you can ask pip to download that package for you so that you can use that, right? It's basically the package manager. So numpy is an open source, and if you want to see the code, you can go to GitHub and check the code out for yourself, right? In numpy, we have n-dimensional arrays. Now the question arises, people, that why do we need numpy, right? So my answer to this particular question is that when you will deal in data science, right? When you will become a data scientist, you will be dealing with data, right? Now my question is, how will you make the machine ingest the data, right? There has to be a way, right, for you to input the data to the machine, right? To make manipulations to the data, to read the data. So all this is started as the base package of numpy arrays, right? Other than that, it becomes very difficult and cumbersome for us to deal with that. And this provides us a lot of ease and flexibility to deal with such massive amounts of data, which you will see along with me as we will move forward in this particular course. Yeah, perfect. Now, people, let me just pull up the PPTs. This is what we're discussing, people. We start with something which is called as scalar, right? We start with something which is called as scalar, which is a quantity which only has magnitude, right? In NumPy language, this is also called as 0D, right? It is called as 0 dimension. Then, people, we have vector, right? And vector has a constant dimension. It has only one dimension, right? You can interpret it as a row or you can interpret it as a column. It doesn't really matter because this is only one single dimension, right? So usually it will be written as 5 comma blank, right? There will be nothing written in front of it. So this in NumPy terminology and nomenclature is called as one dimension, right? When you move on, then you get combined couple of vectors, you get a shape, and now that is called as a matrix. And in NumPy terminology, it is called as 2 dimension, right? And when you try to stack multiple 2-dimension matrices, one after each other or one before each other, then they become something called as 3-dimensional. And now in my capability, I don't know what 4-dimension looks like, but there is a high possibility that you have n-dimensional data, right? We are dealing with n-dimension data, right? Suppose with this, I also add time, right? At t equal to 1, at t equal to 2, that will serve as the 4th dimension for this data. But how does it look like? I don't really know that, right? Because humans are only capable of visualizing 3 dimensions at max, right? So you can go to n dimensions and hence the name n-dimensional arrays, right? ND arrays. Post this, we moved on to create certain things, and I tried to explain you the data, right? So the data will look to you like this, right? You might have a scalar quantity, which is marks, right? 1 marks, right? Now, if I go on to vectors in 1D, it can be marks of 1 student, right? Marks of 1 student in science, English, and maths, right? 35, 40, and 50 out of say 50, right? 3 subjects. So this will be characterized as a vector, right? What will be the dimension written for this? It will be 3 comma nothing. This will be 0, right? Shape will be 0. For this matrix, suppose we have 1, 2, 3, 4 students, and each student will have 3 marks. Right? Each student will have 3 marks. So what will be the shape of this? We have 4 rows and 3 columns, right? So this will be the shape, right, of this 2D matrix, right? And now if you stack images, right, one behind each other, then it will be like this, right? RGB image, I give you an example. So this has 4 cross 4 pixels. So the shape will be 3 cross 4 cross 4, right? This will be the shape for this particular 3D matrix, right, guys? So this is how you input the data. Just to tell you a little bit more, since generative AI is very popular these days, right? So what if I tell you the fact that the chat GPT, which you use or you might have used, right, has never seen a single word in its lifetime, right? All it sees is numbers, right? Only numbers. How do we see numbers? Suppose I say, my name is Raghav. Raghav is a nice name, right? So these are two data, right? These are two data points. Now, we all know that computers do not understand these, right? Computers do not understand these, right? There is nothing, no understanding for computers to know what text is, right? It only knows 0 and 1. Yes, Dharnika, right? It only knows 0 and 1. So see how we will convert this. So there is something called as vocabulary, right? So vocabulary are nothing but the unique words, right? How many unique words do I have in this? My name is Raghav 4. This is not unique. This is repeating. This is repeating. 5, 6. And this is repeating. So I have 6 words. So now, guys, I will do something called as word to vec, right? Where I will convert these words into vectors. How will I convert them? Look at this. So I will have, suppose this is S1, this is S1, and this is S2, right? So I will represent S1 as, right? I will have a vector of size 6. How? I will say 1, 0, 0, 0, 0, 0, right? 1, 0, 0. How many elements does it have? 6 elements, right? Name will be 0, 1, 0, 0, 0, 0. Is will be 0, 0, 1, 0, 0, 0. And Raghav will be 0, 0, 0, 1, 0, 0. Right? This is S1. My name is Raghav. Now, when it comes to S2, right? When it comes to S2, how will I enter this? S2, 0, 0, 0, 1, 0, 0, Raghav. What is here? 0, 0, 1, 0, 0, 0. What is a 0, 0, 0, 0, 1, 0? A nice is 0, 0, 0, 0, 0, 1. And name will be 0, 1, 0, 0, 0, 0. Right? Now, this will be the vector representation of these two sentences. Just to tell you a fact, GPT-3, right? GPT-3 model, right? GPT-3 or GPT 3.5, they have vocabulary of 30,000 words, right? 30,000 words. And each word, right? Each word has a dimension of 12,500 numbers, right? What do I mean? Suppose I say Raghav. So it will be one word and it will be represented by 11,500 different numbers, right? And like Raghav, there will be 30,000 words in this GPT model, right? 30,000 words in this GPT model, right? And this total number of parameters which get trained in the neural network, which we will learn later on, neural networks, they are almost close to 1.75 billion parameters, right? 1.75 billion parameters. So why I'm telling you all this? Because to showcase to you that what is the importance of vectors, right? In the entire machine learning and data science. Yeah, people. So this is the reason, people. Now my question is, how will you create these vectors? How will you read these vectors, right? The answer is through numpy package, because it is the base package. Clear, people? Yeah, I hope today's class will be interesting for you, because you will know the context. Why are we doing it? Yeah, so I'll try to show that to you, how we convert things to vectors, right? Okay, let me go here now, right? Let me go here. So people, we started using numpy. So I started with the 0-dimension arrays, right? 0-dimension arrays. So 0-dimension is nothing but a scalar. So I created ARR0, which was np.array, and I entered a single element inside this, which is nothing but a scalar. And then I checked the type of ARR0 also, right? And then I checked the dimension also. So the answer was 2. Class was numpy nd array, and the dimension was 0, right? Exactly what I had mentioned in my PPT, right? It will be having a 0 dimension like this, right? Same thing has been proven, right? Because it's a scalar. Now coming on to 1 dimension, right? Coming on to 1 dimension, I create a list which is nothing but a 1-dimension data type, right? Now I create an array which is ARR1 from this particular list, LIS, and then I check the type of print ARR1, check the type of ARR1 and the dimension, right? So when I execute, right, then you will see that it was this numpy array and the dimension was 1, right? Exactly like this. So if I show you something else, say print ARR1 dot shape, you will see it's 4 comma empty, right? And I show it to you here. It will be empty, right? Empty. And this will be comma 1, right? So this means that it has only 4 elements, right? If I increase these elements to say 55, 66, 77, then it will become 7 comma blank, right? Which means it has 7 elements as a vector. Now we create something with a nested list, right? Which is like this. So with the nest, I want 1 bracket which is running outside, right? Then inside this, I have 1, 2, and 3 lists inside 1 list, right? So this is a nested list. This is marks of first student, second student, and the third student, right? So I do this and you see it is this, right? And I will show you the shape also. Right? It will be 3 cross 3, 3 rows and 3 columns, 3 rows and 3 columns, right? Now, similarly, we can also create a the 3D matrix, right? With 2 levels, right? Level 1 and level 2 and 3 cross 3. So the shape will be what, people? Can someone guess the shape? What will be the shape of this? I've shown you here, right? If this is 3, 4, 4, then what will be this? 3 rows and 3 columns, right? So when you will execute, you will get 2, 3, 3, right? 2, 3, 3, right? Right now, people, there are multiple ways, right? There are multiple ways to create arrays, and we should know them because all of these comes very, very handy. Not right now. I don't have enough context to give you right now, but later on, you will see with me or with some other trainer that how these will be used in deep learning specifically, right? They are the key of deep learning algorithms, right? Where we initialize some weights, we initialize some biases, and those initializations are nothing but multi-dimensional numpy arrays, right? Numpy arrays. Okay. Right. For example, suppose I have this. I have to multiply this with some random numbers, right? So how will you generate these random numbers? You will generate them through numpy, and you can generate them in a specific kind of shape, right? Which is 2 cross 3, and then you can multiply them. You can multiply the matrices, and you can get your output for yourself, right? So this is the way they are used. So we saw the first thing from list we have already covered. Then now we are moving on to creating zero arrays, right? So I create a zero array of one dimension, right? Of one dimension, which is 0, 0. They are represented in floats, right? They are represented in floats, 0.0, right? Now you can create a two-dimensional zero array, right? You can create a two-dimensional zero array, which is you have to mention just the shape inside 2 cross 1. So it will have 2 rows and 1 columns, right? 2 rows and 1 columns. The difference here is that these are 1 dimension and these are 2 dimensions, right? You have explicitly mentioned the rows and columns. So you can expand this to 10 cross 10 also. Right? You can expand in 10 cross 10 or 10 cross 6, whatever you feel like yourself, right? It will have 10 rows and 6 columns, right? Now you can also create the 3D arrays, 3D zero arrays, right? Which is 5, 3, 3. What does 5 means? What does 5 means? First element represents the number of layers. So you have 5 layers, right? It's 5 layer deep. Then you have 3 rows and 3 columns, right? So it will look something like this. One, two, one, two, three, four, 5, right? Like this, something like this, right? It will look like this. Stack 1, 2, 3, 1, 2, 3, 1, 2, 3, right? 5, 3, 3. Okay. Yes, the number of matrices, Hari, what I represented, right? Layers, rows, columns, right? Layer, rows, and columns. Clear? So now when you execute this, you will get an arrangement like this. Okay. I tried to show you this thing with another example, right? Which is I created an image of an RGB image of 256 cross 256 pixels, right? Which have all zeros inside them. And this is how it was created, right? 3 layers RGB 256, 256. So this is how the image will look like, right? This is how it will look like. Now you can also create arrays with ones, right? Exactly the same way you created it with zeros. I'll give it to you. I'll give you 5 minutes time to create them. I'll show you one. So I say A1 is equal to NP dot ones, and inside I pass 2. I check A1. So this is a array like this, right? It is an array like this. Now you create 2-dimension and 3-dimension arrays of 1. It is basically as a float. Hari, it's represented as a float, right? It's represented as a float. Okay. Right. Perfect. Right. Also, guys, with this, right? Also with this, you can create the custom arrays, right? You can create the custom arrays, right? How do we create custom arrays, people? How do we create the custom arrays? You have created now zeros. You have created now ones. Now what is left? That you create the custom arrays. Forget about this. I will come to this later on. Right? Let's create custom arrays. Right? So the syntax remains the same. Right? I say cust underscore arr is equal to np dot full. Right? This is the syntax. Np dot full. Right? And you will say 6 cross 6. And suppose you want an array of all fours. Right? This is the dimension 6 cross 6. And this value after comma is basically the value which you want. You execute this and you copy this, paste this, and you will get the arrays of fours for yourself. Right? If you want of 10, you will get of 10. If you want 10.3, you will get 10.3. Right? Anything which you want. If you want case, you will get case. Right? All the examples. So let me just show that to you. Yep, like this. Now, guys, how did we create or how did we use range in Python? Can you use range to generate numbers between 20 to 50? Right, 20 to 50. Can you give me the syntax quickly? How did you do that in range? How do we do that? We said R is equal to range 20 to 51, right? And then I said I in R, print I, right? And this is how I got the numbers, right? So similar to range in Python, we have a range in numpy, right? How do we use a range? I say a range underscore arr is equal to np dot a range, right? And then same syntax, I will say 20 to 51, right? 20 to 51, and that's it. And when I will check my arr range arr, you will see I have generated myself numbers between 20 to 50 and a range in numpy, right? A range in numpy. Yes, if you want a interval, so you can use this, say a range 1, and after comma you pass the third argument, suppose it's 3. So now it will jump 3 times, right? 20, 23, 26, 29, 32, 35, like this, up till 50. Now guys, there is something which is called as linspace, right? What is linspace? It stands for linear spacing, which means between two given numbers, this function will fit the required number of numbers, right? For example, suppose, for example, we need to create an interval from 0 to 1. People, there are infinite numbers I can have between 0 to 1, isn't it? Infinite numbers I can have between 0 to 1. 0.0000000000001, 0.00000010101, right? I can go in the infinite manner, right? Now, for example, you need to create numbers between 0 to 10, right? And you want to create and want to have 10 numbers in it, right? So how will you do this? It's not float, it's about the number theory, right? Between 0 and 1, you have infinite numbers, right? So you say linspace is equal to np dot linspace, right? np dot linspace. You mention from 0 to 10, you want to have 10 numbers, right? And when you will create linspace, you will see that these are the numbers are there which have been created, right? These are the numbers which have been created, right? 9 numbers. Now I say 100 numbers I want. Evenly spaced 100 numbers, right? Evenly spaced 100 numbers. How are they even? You can simply subtract one number from another and the difference for all the numbers will be exactly the same. 0.010101. Subtract any two numbers, it will be 0.010101. Right? Where do we need this? We need this to plot the axes, right? When you will plot graphs, you will need axis. Between this interval, you need 5 values. That works like this. Okay. Suppose you want from 0 to 10, 5 different values, right? You will have 5 different values like this, right? Between the gap of 0.5, right? If I say 1 to 10, you will have values like this, right? Like this. Clear? 100 values like this. Yeah. Clear, guys? How do we use linspace? Suppose you want from 0 to 10, interval from 0 to 10, and 10 will be included, 0 will not be included, right? We'll start from 1. So I go to 1, it will be from 1. Why is 0 not included then? Yeah, 0 is included, right? 0 is also included and 10 is also included. 100 numbers between them, right? Clear? This is what linspace is. Now, guys, now, suppose you, Logeshwaran, linspace is basically used if you want to create n numbers between the range of numbers, right? Between 0 to 1, right? Suppose between 0 to 1, you are trying to plot a graph, okay? And your values are 0 0.2, 0 0.3, 0 0.6, right? And you want to draw a graph. So you will have to mark the axis, right? The x-axis and the y-axis. So you can use linspace there. And what will it do? It will take the range, it will take the interval in between you want to add the equal space numbers. And then the third argument here will be that how many numbers do you want between them. So this syntax tells you that from 0 to 1, give me 100 numbers. How are these numbers? Equally spaced numbers. Equally spaced numbers. Right? So when you will execute this, you will see that there are 100 numbers which have been generated, right? 100 numbers. And all the numbers are equidistant from each other because difference of every single number from the next number is 0.010101. Yep. That's what it does. Right? Now, guys, now suppose we want to generate random numbers, right? You want to generate random numbers, right? Now we are interested in generating random numbers. So we have something called as random dot random, right? What will it do? Random dot random will generate random float numbers between 0 to 1. Random float numbers between 0 to 1. How will this happen? You will say rand underscore rand is equal to np dot random, and inside you will mention what is the dimension that you seek. Suppose I want 6 cross 6. So when you will check this, you will have all numbers for 6 cross 6 dimension, right? 6 cross 6 matrix, right? Now, every time you rerun this, the numbers will change because all of these are random numbers, right? All of these are random numbers. Now I say 100 multiplied by rand underscore rand. You will see all of them, all these numbers will be multiplied by 100, right? All of them in one shot. Now, just like this, we can also create random integers, right? How will we create random integers, guys? I say rand int underscore rand int is equal to np dot random dot rand int, right? And here you will specify that what is the range of numbers you want from. So I say between 20 to 25, I need random numbers and then I want it from in a 3x3 format, right? And now when you will check your random, you will get random numbers generated like this. Okay, random numbers generated like this. Right? If you say 3x3x3, you will get a 3x3x3 matrix. Even if you will only say 3, you will get a 1D. Right, guys? You can change the dimension. So this is the range from which you want to choose the random numbers, and this is the dimension you want this matrix or vector to be in. Now, guys, we'll move on to the next part, which is basically properties. And again, there are a lot of operations. You'll have to see it yourself, right? Properties and attributes of numpy arrays, right? Property and attributes of numpy arrays. Okay. Now, guys, the first one in this scheme of things is shape of array, right? Shape of array. What is shape of array? It tells you the dimensions of the array stored in a tuple, right? For example, I say ARR 0, right? ARR 1, ARR 2, ARR 3, right? And then I say print this dot shape, right? Like this. And you will see that it will give you the shape of each array, right? 0D, 1D, 2D, and 3D, right, people? Shape of the array. Please try it out. We have used it 1 or 2 times, but this is what shape of array actually means. Second is, people, endim, right? Is endim, right? Endim of array, right? It tells you the rank of the array, whether it's 1-dimensional, 2-dimensional, 0-dimensional, 3-dimensional, 4-dimensional. So again, I will do the same thing. Right, I'll say endim, and you will see it will give you 0, 1, 2, 3. 0 dimension, 0 rank, 1 rank, 2 rank, and 3 rank. And it can go all the way up to n rank. Right. Before this, I should have also printed these arrays. Right, these are the arrays. Yep. These are the arrays which we have, and these are the subsequent things, right? Rank of the array. Then, guys, the third thing is the size of array, right? It tells you the number of elements inside. How many elements do we have inside this array? In ARR1, how many elements do we have? 1, 2, 3, 4, 5, 6, 7. How many elements do we have in this 2x2 AR2? 1, 2, 3, 4, 5, 6, 7, 8, 9, which is rows multiplied by columns, 3 multiplied by 3, right? And how many elements do we have in this 3D? Which is 2 multiplied by 3 multiplied by 3, which is 18, right? So now, when you copy this, right, you can use this and say size, right? So it will say 1, 7, 9, 18. Yep. Fourth is people. The D type of array tells you the data type of the array, right? And I've told you we place only homogeneous data in array, right? What will happen if we don't do this? I will show that to you also, right? So we do this, right? And we say D type, and you will see in 64, all of them are integers, right? All of them are integers. That's the reason we are getting in 64, right? Suppose I create a new array, ARR underscore new, right? Let me say het, right? Heterogeneous. And I say it is like np dot array. Let's say like this. Right? Like this. Now, people, when you will check ARR dot D type, you will see it will give you float. Just because of one floating point number inside this entire array, it gets converted to float. Right? Between all the integers, if you put one float, then it will be taking float directly. Right? Now, let me just copy this and let's say heterogeneous 1, and let me add another value which is string and say Raghav, right? And when you will execute this, it will give you U32. U32 here is representing strings, right? It is all called as objects, right? These are all string values, right? So precedence is strings, greatest, then float, and then your integers, right? If you place the heterogeneous data inside the numpy array, right? You only need to put homogeneous data in the array. Now, fifth is the item size of array, right? What is item size? It gives you the byte occupied by each element of an array, right? Because we assume that elements will be homogeneous, it will give you the byte occupied by each element of the array, only one element, okay? So how will it happen? So let's say ARR 0, or let's say ARR 1 dot item size, right? And you will get 8, right? So why 8? Because each data point, right? Each data point is occupying, the result is 8 bytes. Let me put this here. Right, 8 bytes, because each element in ARR1 is occupying 64 bits, which are equivalent to 8 bytes, right? 1 byte is equal to 8 bits. So 64 bits will be equal to 8 bytes, right? That is how it is giving you the result. Now, if you are interested in knowing the entire bytes, right? Entire bytes, then you say n bytes will give you the total bytes occupied by the elements of the array, right? You say print ARR1 dot n bytes, right? And write bytes. It will be 56 bytes, right? Why? Because how many elements do we have in our ARR1? 1, 2, 3, 4, 5, 6, 7, right? 7 8s are 56, right? 56 total bytes are being occupied with by ARR1. Now, guys, the seventh one is as type, right? in array. This will help you change the data type of the array, right? Change the data type of the array. Suppose I have arr1 dot d type, which is so I say print d type, right? This is int64, right? And now what I do is I say print wait, let me give you a structured way. Print arr1, right? Let me say array arr1, right? D type of array. Now arr1 is equal to arr1 dot as type, right? Dot as type. And let's say I want to convert this in np dot, right? np dot int 32, right? I want to convert this in arr int 32, right? When I do this, and now when I will copy these same things, you will see for yourself, right? Now the D type was int 64 and now the D type is int 32, right? If I want, I can do this conversion in float also, float 64, right? And then I will just copy this and I will paste it here, right? And now you will see now the floating point has been activated, right? It has been now activated. We can go till int 8, right? I can go to 16, right? And I can do this. I can go to int 8 also. Yeah, like this. Int 8 also. 64, 32. So first one has to be, yeah, 32 load this. Whatever, right? Like this. Okay. You can convert this. Also, people, this is later on conversion. You can define the data type of the array while creation time also. How would you do that? Suppose you are creating arr11 and you say np dot array, right? And suppose you take it from a list and then you just put a comma and say d type. So what will be the default data type here, people? If I just do this, if I just execute this, what will be the default data type? Int 64 is the default, isn't it? But now suppose I want to change it right here. I say data type is equal to float 32, right? Sorry, float 64. np dot, sorry, my bad. Float 64, right? And I say arr11 and this will be float 64. If you want float 32, it will also become float 32, right? Right here, while you define. Instead of using as type, you can do it right here, right? These things will come in very handy, people, because you will have to save memory. Because when your data becomes very, very big, you will be always in a crunch for memory. Like this, you want integers, then integers will be like this. Random dot randint, like this. Suppose you want to generate 0 to 6, right? And suppose you want to generate, say, 100 numbers, like this, 0 to 6. The scores 1 to 6, like this, randomly, right? Suppose you want to generate 100 scores for 5 different batsmen randomly. It will be like this. Batsman number 1, batsman number 2, batsman number 3, 4, and 5th, right? Yep. Understand the data, guys. Now it's the time to understand the data. Yep. Now, guys, we have methods in numpy arrays, right? Methods in numpy arrays. So what are these methods now? The first method we have to learn is called as reshape, right? Reshape. Yeah, so reshape is you can use this to create a new shape of the array. Very, very powerful, guys. Very powerful. One of the most powerful methods in numpy is the reshape, right? And how do we use reshape? Suppose we have a 1D array of 20 elements, right? Now to reshape it, we need to find the factors, right? Factors of 20. They are what? 1, 20, 4, 5, 2, 10, right? These are the factors. These are the factors. Now see what will I do, right? Now see what will I do. Let me create a, say, random array, right? Random array. I say random underscore arr is equal to np dot random dot randint, right? And let me say I want to create it from 1 to 50, right? And I want it to be having 20 elements, right? So I say random dot arr. So you will have random values inside this, right? Random 20 values. Now see. Now reshape. First, I will reshape in 1 cross 20, right? 1 comma 20. How will I do that? You just have to write uh, print arr, sorry, random dot arr, random underscore arr dot reshape, and you just pass in the dimension. I say 1 comma 20, right? And when you will do this, you will see it is coming now in 1 comma 20 format, right? So let me just also write print right 2D 1 comma 20, right? And now what I'll do is I'll copy this and I will paste this and say 20 comma 1, right? You will see it will be like this 20 comma 1 immediately with reshape, right? Let me copy this. Let me say 2D. I'm still at 2D. Let me say 2 comma 10, right? And you will see this is 2 comma 10. Now I can reshape it in 10 comma 2, right? 10 comma 2, right? Then I can reshape the same thing in 4 comma 5, and I can reshape this in 5 comma 4, right? Like this. Guys, are you able to see the power? One dimension, I'm able to create 2 dimensions. And now I will take it a step further and I will write it in 3 dimensions, right? How will I write it in 3 dimensions? Let me say this 1 comma 2 comma 10, right? This will also be 3 dimensions. 2 comma 2 comma 5. Let me say this. And now you will see I can have this in 3 dimensions, right? Yep. I can also say in 3 dimensions like this. I want to have 5 layers with 2 rows and 2 columns, right? So you will have it like this also, right? So this is how people, we can reshape the array. Very powerful, very, very powerful, right? Very, very powerful, right? And you can take this and say print random dot this, and you can say print dot shape, right? So this was the first one. Yep, like this. Also, people, if you want to visualize, we can also go this route. We can have 10, comma 2, comma 1, right? It will look like this, right? 10 layers, 10 layers you can have, right? 10 layers you can have. Great. Now, second method which we have to learn is called as transpose, right? Transpose method, right? What does that do? It interchanges the dimensions like rows and columns, right? Yes, absolutely, right? Suppose you have a matrix, right, which is 22, 33, 44, 55, 66, 77. Right? This is A. So now when you will A transpose it, right? The dimension right now, the shape right now is 3, comma 2. Now this will become 2, comma 3. And how this will happen? Rows will now become columns and columns will now become rows, right? So let's make column the rows, right? Sorry, columns the rows. It will be 22, 44, 66, 33, 55, 77, right? So people, in transpose, no information is lost. It is just a change in the view, right? Which is happening, right? 22, 44, 66, 33, 55, 77. Why do we need transposition? Suppose we have two matrix. This is 11th class mathematics, right? One has a dimension of n cross m, and the second has dimension of a cross b. If you want to multiply these two matrices, say m1 and m2, right? There needs to be a satisfaction of condition. M should be equal to a, right? M should be equal to a, right? M should be equal to a. This should be equal to this. And the resultant vector, the resultant matrix which you will get will be of n cross b dimension, right? So oftentimes, suppose this is n cross m. This is n cross m, right? M cross n. And you know that m is equal to a. So what will you do? You will transpose this matrix, right? You will transpose this matrix. Then it will become n cross m, and then m can be equivalent to a, right? For example, what I'm saying, we have one matrix which is 2 cross 3, and this matrix is 2 cross 5, right? So can you multiply these matrix, people? Is 3 equal to 2? The answer is no, right? The answer is no. So what will you do? You will just transpose this, and this will become 3 cross 2, and this is 2 cross 5, and now you can multiply this, and the resultant will become 3 cross 5 matrix, right? So for operations like these, we need transposition, right? So how do we transpose it? How do we transpose it? So let's say again, ARR2, right? This is ARR2, and I want to transpose it. So I say ARR2 underscore T is equal to NP dot transpose. Sorry, ARR2 dot transpose, right? And now when you will see ARR2 underscore T, you will see rows and columns have interchanged, right? Rows and columns have interchanged with each other. Or let me give you one more example. If this is not clear, let me pick up this again. Right now I say dot reshape into say 2 cross 10, right? So this is 2 cross 10. And now when you want to transpose this, so I'll say this underscore t is equal to this dot transpose TRANS, and you can check this now and it will be this. Sorry guys. So this is going to be, it will be like this, right? Transposed. And now if you want to see this, this was the original shape, right? Rows and columns have now been interchanged, transposed with each other. Now guys, method, the third method which is there with us is called as flatten, right? It is called as flatten, right? What does flatten do? It reduces the dimension to one dimension, right? Any dimension you have, it reduces it to one dimension. For example, I have this, right? And now when I say this dot underscore f, this will become this dot flatten. And when you will check this up, you will see that it has now become one dimension. No matter how many dimensions you have, it will become one dimension, right? Let me take this again to show you one more example, right? And here I say dot reshape into 5 cross 2 cross 2, right? I do this. My random ARR is this, right? It has 5 layers, 2 rows and 2 columns, right? So now I say this underscore flatten is equal to this dot flatten. And if you will check it now again, you will see it has now flattened it up. Yep. Now, why do we need this? We need this for a lot of statistical operations. We need this to feed the data into the algorithms, right? As we will move forward, you will understand the use of flattening, right? Now, guys, moving on, and as discussed, let me now show you the power of numpy, right? Numpy over lists and other data types, right? I will not take a lot of examples. Just a second, guys. Yeah. Okay. Now, guys, I told you that lists take up much more memory as compared to numpy arrays, right? And I'm going to prove this to you, right? Now, let me create a random sequence of random numbers using range in Python, right? And say I create range of 10,000 numbers, right? Range of 10,000 numbers. So what will this give me? This will give me numbers from 0 to 9999, right? Continuous numbers, right? So this is range. I will use a range in numpy to create a similar series of numbers, right? So let's say array is equal to np dot a range, right? Same thing, Same done by both, right? I've shown you above also. Now, let me import sys library, right? Sys package. And I will use something called as get size of, right? Get size of. What does this do? Get size of. It's a method which calculates the bytes occupied by a single element in vanilla Python. What is vanilla Python? It is the traditional Python, right? Vanilla Python. So let me just show that to you. I'll use this and I will say print. Now guys, if I get size of any random number from this range, right? Any random number. Say I get size of 5, right? And I then multiply that bytes with the length of random, right? With the length of random, this ran, right? Right? With the length of random, do you think I will get the bytes for the entire data structure? What am I saying is, suppose I used range 5. So what will this give me? 0, 1, 2, 3, 4, right? This will be the output. So now I say get size of, say I say 2, right? So suppose 2 is x. And then I multiply this with the length of this series, which is 5. So do you think I will get 5x, which will represent the number of bytes occupied by the entire data type? Anything randomly, any random number. This can be 3, right? Why not, Hari? Why not? All of these are integers. So integers, all of 64 bits, assuming. So if you calculate the size of this, and if you multiply with the total number of numbers, you will get the total size. Isn't it? Huh? Index is in tangent. No. It's not about that. It's about the element, right? Homogeneous elements inside this. I am saying when you use range 5, what is going to be the output? 0, 1, 2, 3, 4, right? Now all these are elements of range, right? All of them are elements of range, right? Now I'm saying if I fetch the size of one element and multiply it with the length of the entire range, will I get the bytes occupied by the entire range? For example, if I do this, right? If I do this, this is 28, right? 28 bytes, people, 28 bytes are occupied by one element of range, right? One element of range, right? Now, if I just, I'm just saying, if I multiply to find how many numbers range has, how many numbers range has equal to 10,000, right? So total memory occupied will be how much? It will be 28 multiplied by 10,000, which will be equal to 28,000. Yeah. And how will you find this? You will say print this multiplied by length of RAM, right? 28,000 bytes. Clear now? Yes. Now this is for the range. Now let me use another thing. So how will you calculate the length of this array? What property and attribute will you use, people? N bytes, right? N bytes will give you total bytes occupied by the elements of the array, right? We will use N bytes here. So I come back down and I say using N bytes for arrays, right? And you will see what the result comes. Print array dot n bytes, right? And I say bytes. Are you ready to see the result? Do you see what has happened? How many bytes this was taking? It was taking 28,000 bytes. How many bytes this is taking? This is taking 80,000 bytes. This was taking 2,80,000. This is taking 80,000. 2 lakh extra bytes of memory is taken by range. RAN is range. Yep. And if I just go to million numbers, right? Million numbers in both. See the difference it becomes, right? This is now 28 million bytes it is taking, and it is taking 8 million bytes. 20 million extra bytes are occupied, right? Now, people, do you believe me? Yep, that NumPys are way more efficient in memory management as compared to the traditional data types of Python. Yes? Okay, that's the first part. Now, second is, people, performance, right? Performance. So what I'm going to do is, I am going to import time, right? It's a module in Python, right? Suppose I say x is equal to range this much, right? Okay. And then I have y is equal to range, say, this to this, right? Both of them will have equal amount of numbers, same numbers, both of them will have, right? This will have, say, 1, 2, 3, 1, 2, 3, 10 million values, 10 million values. This will also have 10 million values, right? Both of them will have 10 million values. Now, what I'm trying to do is I want to add them up, right? Bit by bit, I want to add them up, right? I want to add first element of this to first element of this, second of this to second of this, third of this to third of this, like this. Okay, I want to do this. Now, what I'll do is I will run a counter, right? I will run a counter, which is the start time, right? And this is given by time dot time, right? Which will give you the, this will give you the current time, right? After this, I will run the operation. I will say C is equal to x plus y for x comma y in zip x comma y, right? In zip x comma y, right? Add x plus y bit by bit, element by element for x and y in zip. Zip is a function, right? Which allows you to do this operation sequentially, right? Sequentially, right? Add the elements of x and y element by element, right? Element by element, right? Element by element, right? And then I am going to print, right? So start time will start, and now I will say time dot time, which is now the end time, minus start time. So this will give me the time taken for execution, isn't it, guys? Will give me delta of time, which is equal to time taken for operation, seconds, right? These many seconds will be taken, right? So let me run this, and it takes around, say, 4.3 seconds, right? To do this, right? 4.3 seconds. Now, guys, see what happens. You had to write this complex syntax in the traditional Python. Now, let me show this on arrays, right? What will happen on arrays? I will say A is equal to np dot arrange, right? And inside arrange, I will pass the same values what I've taken above, right? And I will say B is equal to np dot arrange and I will pass the same values inside, right? Exactly the same. Now, what I'll do is I will say same thing, right? Just I will change the execution of C, will now simply become people A plus B. What is simple? This or this? This or this? 2, right? Do you see the power? If not, I will show this to you again, right, later on, and let me run this. And you see the difference. Now let me just increase a couple of zeros, right? A couple of zeros. 2 zeros I am increasing in both the use cases. It is going on and on, right? Let's see how much time it will take to add, say, 2 million, 1 billion numbers. 1 billion numbers I have asked my system to add, and I want to see how much time it takes. Running. Yeah, kernel has died. Kernel has died, people. I'll have to restart, right? I will have to import numpy as np. So let me just remove 1 0 from both. It is taking 4 seconds, removing 1 0 from here also, right? And when I do this, it takes 1 second. Do you see, guys? What is the difference in performance also, right? For both of these, yep. And if you didn't understand this, let me give you an example. Range 5, this is 5 to 10, right? And this is basically adding elements, right? 5, 7, 9, 11, 13, right? So this will be, what will be the output of this? This will be 0, 1, 2, 3, 4. And this will be output what? 5, 6, 7, 8, 9, right? So 0 plus 5, 5, 6 plus 1, 7, 7 plus 2, 9, 8 plus 3, 11, 9 plus 4, 13. And the same thing, if I do here, then what will happen? I say 5, and 10, right? And I say C is equal to A plus B, and I say C. Same thing you get here, right? We can move on, right? The next bit, guys, which we have to understand, is called as the indexing in numpy arrays, right? Indexing in numpy arrays, right? How do we index the elements, right? How do we index the elements? Indexing in numpy arrays, right? Indexing in numpy arrays. So again, you know indexing from basic Python. So let's start with 1D. For 1D arrays, right? I will use ARR1. Yeah, this is ARR1 now, right? This is ARR1. Okay. Now, people, what I want to do is, I want to fetch, right? I want to fetch, right? You can slice and dice. Let's say dice 33, right? So again, as per our normal indexing of list, what is 33? What is the index of 33, people? 2. So you will say the same thing, print, right? ARR1 squared bracket 2, and you will get 33 for yourself, right? If you wish to slice, same thing, right? 33 to say 66. What is the index? 33 is 2, 2, which one? 3, 4, 5, and 6, right? You will write 3 to 6, not 5, hurry. 5 is not included, remember? Say print ARR 1, 2 is to 6, and you will get 33, 44, 55, 66. Right? Simple indexing. Please try it out. Please try it out. And if you want, you can have this code also. You can write this code. You will always have clarity that why do we use it. Moving on, people, moving on. Let's see indexing in a 2D array, right? And before I explain this to you, let me take you here, right? So a 2D array will be what? Right? This is a 2D array. It has 3 rows and 3 columns, right? Rows, columns. So now for rows, indexing will start from 0. So if you have to fetch this particular row, right? So what will be the index? It will be row 0. If you have to fetch this particular row, the index will be 1. And if you have to fetch this particular row, the index will be 2. Similarly for column, if you have to fetch this particular column, right? You will have column is equal to 0. This particular column equal to 1. This particular column equal to 2, right? Indexing will start from -1 again, right? 0, 1, 2. So let me just show that to you, right? Let's say I call ARR2. This is my ARR2. Now, indexing first row, right? How will I do that? I will say print ARR2 and I will write how? How will I write this? I will write row 0, right? Row 0. So what will this give me? This will give me this, right? The syntax is row space column, right? So now if you just pass 1, it will give you only rows, right? Row 1, row 2, row 3, right? Similarly, if you want to create it for columns, right? What will you say? Sorry. For columns, it was zero. Column 1, column 2, column 3, right? Right? So what is my column 1? 76, 89, 98. 76, 89, 98, right? And if you want column 2, sorry. If you want column 2, this is the column 2 and this is column 3, right guys? 90, 99, 99. Independently. Now, if I ask you to fetch me a particular element, right? Say I want you to fetch me 78, right? How will you fetch 78? You will say print ARR2. What is the row for 78? Which row does it belong to? 0, 1, 2. To which row 78 belongs? 1 row. Which column it belongs to? 0, 1, 2. 1. Hurry, check again whether it belongs to 0 column, first column or second column. Right? And you will get, sorry, 0, 1. So this is 2. Right? 78. Right? Second row, first column. Right? Second row, first column. How to define it as in? Right? This is your matrix, right? Now, what are the index positions for this? This row is 0 row, first row, second row. This is your 0th column, first column, second column. Yeah. Yes, no, maybe. Are we understanding this? This much is clear. The indexing of rows and columns. Now, if you have two, so the syntax is, say this is matrix A. So you will say A, in this A matrix, you will write row, comma, column, right? Suppose I want to access only 0th row. So there will be no column. So what will you get? Row number 0, right? Row number 0, and you will just put it like this, or you can put a comma and put colon. Colon means what? Take everything. So I want all three columns together, 0 row and all three columns. So this will be your, let me show that to you. Right? See this? 0th row and all the columns. So what will be your answer? 76, 88, 90, right? Then if you want to access the second row, 89, 90, 99, 89, 90, 99, 1 and like this. Clear? Now similarly for columns, what will happen? You will take all the rows, comma, which column do you want? If you say 2, what will be the result for this? What numbers will you get for this? Colon, comma, 2. You will get 33, 66, 99. Now, coming to the element, right? Suppose now you want to fetch 55, right? So what will you write? You will write which row does it belong? Follow this syntax. It belongs to the first row. Which column does it belong to? First column. So what will you get? 55. Come to this example. Now you want 78 in this particular array or matrix, right? Where is 78? Which row does it belong to? Is it first row? Check carefully. 0th row, first row, second row. Yeah. So I put 2 here. Now which column does it belong to? First column, second column, sorry, 0th column, first column, second column. Belongs to the first column. So I put 1 here. So when you put this syntax, you will get 78. Clear? Now, the third thing is slicing through the array, right? Now, for this, I want 90, 99, 78, 99. That means what? I want this, this, and this. Let me take you to the PPT first. Now, what I'm asking you to fetch me? I'm asking you to fetch me these 4 numbers, right? These 4 numbers. So here, what will you write? Which rows are included in this, people? Which rows are included in this? Row 1 to all, right? 1 to all. Yep. Not 2, 1 to all, right? And you leave everything like this. If you have the last row, you leave it empty after the colon, comma. Which columns do you want for this? 1 and 2, right? And when these will intersect, you will get this area, you will get this shaded area, green shaded area. So I will say, I need from column 1 to all the columns, right? So what will this fetch you? What will this fetch you? This will fetch you 44, 55, 66, and 77, 88, 99, right? What will this fetch you? This will fetch you 22, 55, 88, 33, 66, 99. What are the commonalities between both of these? Access. Both of these slices, what are the commonalities? It is only this much, right? 55, 66, 88, 99, right? So do you think you will get your result? Yeah, let's check it here, right? I say print ARR2, right? And this I say, I need row 1 to empty, and then column 1 empty, and you will get 90, 99, 78, 90. Indexing. Yeah. Now guys, let's check it for 3 dimensions, right? 3D. I say ARR 3, right? This is my ARR 3, right? So let me just put an example here. Suppose my arrays are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9. Right? This is my first. Then behind this, I have another matrix, which is 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, 6, 6, 6, 7, 7, 7, 8, 8, 8, 9, 9, 9. Right? And in my third one, I have 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, 5, 6, 6, 6, 6, 7, 8, 8, 8, 8, 9, 9, 9. Is it qualifying for a 3D array? Can you access anything on this particular array if given a chance separately, like this one? Now, people, if you want to move between layers, right? If you want to move between layers, do you think I have told you one particular access, which is what? Which is the layers. So what number will be given to this layer? Layer number 0, layer number 1, and layer number 2. So now, if you have to access this 555, which layer you will go to first? You will go to first layer. Then which row will you go to? You will go to first row and first column. So if you pass this syntax, what will you get? You will get 555. Right? Problem solved. The only bottleneck was the layers part, and you have additional parameter or argument for this layer. So if I come back to my example, and if you have to access this 555, right? How will you do that? I say print ARR2, ARR3, right? And this I say, and in this I say what? I have to access this 555. Which layer number is this? This is layer number 0, right? This is layer number 0, and this is layer number 1. So I say layer number 1. Which row is this? In this particular layer, it is layer number, sorry, it is row number 1 and column number 1. And when you do this, you will get 5 by 5. Right? If you want 999, what you will do? You will change this to 2, 2. Right? If you want 777, or let's say if you want 98, what will you do? For 98, layer number 0, row number 2, column number 0. And you will get this 98. Clear, guys? Yep. Layer, row, column. In the same way, you will slice it. Right? You will slice it. Yep. Right? I'll write the syntax so that you don't get confused. It is array, squared bracket, layer, row, column. Right? Layer, row, column. Right? This is the syntax. Perfect. Right? Great. We can also perform some operations, right? Plus, minus, multiplication, division between two arrays very, very easily, right? It should not pose any problem to us, right? We can do all the operations which we want to, right? Between two arrays, right? For example, right? You have, right? Operations on arrays. So let's say, let's see as a list, right? List. So we have list is equal to 1, 2, 3, 4, 5, right? Now suppose you want to square each element of the list, right? What will you do? You will say sq_l is equal to x to the power of 2 for x in L, right? And then you will say print sq underscore L, and you will get the squared of list, right? Original list, squared list. Now, in array, what will happen? Suppose I say A1 is equal to np dot array and L. I create the same array out of this list. I say print original array, right? I say A1, right? This is my original array, same as this. Now, I want to square it. Square the elements of arrays. Very, very simple. Nothing you require. You just say sq underscore A1 is equal to sq underscore A1 is equal to A1 to the power of 2, right? A1 to the power of 2, right? And then you print the right, you get the squared array. Suppose you want to find the mean of the mean of numbers using list, right? So what will you do? You will say mean is equal to sum of L, right? List divided by length of list, right? And you will get the mean, right? Which is 3 for this one, right? This original list. Now, let me show you in arrays, right? How will you do this? You will say mean is equal to np dot mean, and you will just pass A1, right? And when you will check mean, you will get 3.2, right? Nothing like this, direct, right? Direct like this, right? I've already showed you add, I've already showed you square, and then I believe you can understand that what all operations are possible using the arrays, right? Leveraging the power of arrays, right? Also, guys, in the arrays, right? In the arrays, what you can do is you can perform some string operations, right? Very powerful string operations, right? So, for example, let's say I have I have a array, right? I have an array of names of people, right? So I say names is equal to np dot array, right? And I say Raghav. Then I say Dinesh, right? And then I say Madhu, right? These three names I have, right? So you can check the names. They will be like in the array, right? And the data type will be U6, which is a representation of strings, right? Now, guys, suppose you want to capitalize. You wish to capitalize the names, right, of people. What will you do? You will say print me np dot char, right? Np dot char dot capitalize, right? Capitalize. And inside this, you will pass names, and you will see all the names have been capitalized, right? You see this? R has been capitalized, D has been capitalized, M has been capitalized, right? You can convert them into upper if you want. Print np dot char dot upper names, and you will have all of them in caps lock. You can say print np dot char dot lower. You will have them in lower, right? You can put the title, right? Suppose I say title, title is equal to np dot array, and I say Raghav Goyal, right? Then I say Dinesh Senapati, right? And I say Madhu Verma, right? I say these three things. Now, if I say print np dot char dot title, right? And I say title, you will see that all the words will be in capitalized mode. Raghav Goyal, D and S of Dinesh Senapati, M and B of Madhu Verma are now capitalized. I can also replace something if I wish to. Suppose I want to replace Madhu with say Surbhi, right? I will say print, right? np dot char dot replace, right? And you will say where you want to replace. I say title, and in this I want to replace Madhu with Surbhi, right? And you will say it will be Surbhi underscore Surbhi Varma, right? Madhu has been replaced with Surbhi, right? Right? If you want to calculate the characters of strings, right? You can do that. Print np dot char dot str underscore length of titles, and you will get 11 characters are there in here, 15 are there here, and 11 are here in this particular thing. Right? You can do much more powerful things also. Let me show you one complex function. Right? Suppose I have f name is equal to np dot array, right? And we have Raghav, Dinesh, Madhu, right? And we have L underscore name array, Goel, Ganapati, Verma, right? We have these two things. Now I can create a new array, full underscore name, by simply, right? By simply saying np dot char dot add, right? And I say f name, right? Comma L underscore name, right? Plus yep, repeat full name. Yeah, Raghav Goel. I just was trying to add a space in between. Anyway, right? We can do that. Right? You can also people search in arrays, right? Very powerful again. Search in arrays using where, right? Right? You can say suppose A2 is equal to np dot array, right? And I say 1 1 2 2 3 3 4 4 5 5 6 6, right? And now you have to say A is equal to np dot where, right? And in this you say A2 greater than 20, right? And when you will check A, It's giving me the index. Why is it giving me the index? Why is it giving me the index? Does it always return index? One more thing is you can find an letter, right? Through a letter. You can find an element through a letter. Guys, these are all some tricks which you should know because you will be dealing with data and you need to pull data, right? You need to pull data a lot, right? Based on conditions and based on things. Suppose you want to find out the names which have G in them, right? Or RA in them. So how will you do this? I will say print, right? And I will say np.char dot find, right? And I will say find this inside full underscore names, right? And find me RA, right? RA. True, false, false. Right? It returns true because it has found it here, right? So I don't want to tell you indexing through this, but anyway, you should know this. Just assume this that I am telling you to write this, okay? Because this is much easier when we will go to pandas, right? Just write it as a syntax, okay? Greater than equal to 0. I hope this is clear.
So let's start with the data science interview questions and answers. And the number one problem we would be facing is real world problem solving. And the question one is handling missing data in predictive modeling. So imagine you have given a data set where 30% of the data for a key predictive variable is missing. This variable is crucial for a predictive model. How would you handle this situation to ensure the integrity and performance of a model? And please describe your approach step by step. So starting with the answer, you can start with handling missing data set is a common challenge in data science, and it's important to address it carefully to maintain the accuracy of your model. And here's how you could approach this situation. The number one point could be identify the missing data. So first you need to understand where the missing values are in your data set. You can do this by using a simple code in Python with libraries like pandas. For example, you can use the data.isNull.sum function that will show you the count of missing values in each column. Then you can analyze the pattern, determine if there's a pattern to the missing data. Is it random or is it missing for a reason? This can affect your approach. If the data is missing at random, the methods you use might be different than if the data is missing systematically. So choosing a method for imputation. Let's see the next method, that is choosing a method for imputation. So if the missing data is numeric, you might replace missing values with the mean or median of that column. This is simple and effective, but can be used primarily when the data is missing completely at random. Then comes model-based imputation. Sometimes you can use other variables in the data to predict missing values using a regression model. This can be more accurate, but is also more complex. Then we'll use the k-nearest neighbors KN algorithm. But before that, we have a code snippet here that could be used for the implementation of imputation. You could use Python or R. And now moving on, we'll see the k-nearest neighbors algorithm. So this method predicts the missing values based on how closely related the data points are to each other. So after imputation, it's crucial to check how your changes have affected the overall dataset and model performance. Sometimes filling in too many missing values can introduce bias. And then we have visualization. To help understand before and after the imputation, you could visualize the distribution of the variable using histograms or box plots. This helps in seeing how the imputation has changed the statistical properties of the data. And by following these steps, you can handle missing data thoughtfully and maintain the integrity of your predictive model. Now moving to the question number 2, that is based on evaluating model overfitting. So the question is, you have developed a predictive model, but you suspect it might be overfitting the training data. How would you test and address the issue? Please explain your steps and the techniques you would use. So you could start the answer by explaining what is overfitting. So overfitting is a common problem where model performs well on training data but poorly on unseen data. indicating it's too closely fitted to the training data's specific details and noise. So now we'll see a step-by-step guide on how to address this. The number one step is cross-validation. So one effective way to test for overfitting is by using cross-validation technique. Cross-validation involves splitting your training data into multiple smaller sets, that is faults, and then training a model on some of these sets and validating it on the others. So this helps you understand if the model's good performance is consistent across different subsets of data. For example, in Python, you can use the cross_value_score function from sklearn.model_selection. So this is the code, and this is the code snippet of Python that you can use for the cross validation. And here we are importing from sklearn, that is the module, and we are importing cross_val_score. And here we have used the cross_val_score function, and then we have printed the average cross validation score. And the next step we will do is running cross validation model. So this is your predictive model that you have already built using scikit-learn. And here's the X train. These are the X input features of your training data, and Y train, these are the output labels of training data. So we are running cross validation model here. This is your predictive model that you have already built using scikit-learn. So X train here, that means these are the input features of your training data. And Y train here means these are the output labels of training data. And CV equal to 5. This parameter tells the function to split the data into 5 parts, that is faults, and the model is trained on 4 of these parts, and the remaining part is used for testing. So this process rotates until each part has been used for testing once. And the printing results, that is score.mean. So this calculates the average of the scores obtained from each cross validation fault. This average score gives you an idea of how well your model is likely to perform on unseen data. A consistent score across different faults suggests your model is generalizing well rather than overfitting to the training data. So now moving to the next point, that is training versus validation error. So plot the training and validation errors as a function of training epochs or complexity of the model. A model that overfits will show a low error on training data and a high error on validation data as it trains further. Then we have pruning the model. If you confirm that the model is overfitting, consider simplifying it. This might mean reducing the number of parameters by selecting fewer features, using regularization techniques like lasso or ridge, or choosing a less complex model. After this step, we will move to regularization technique step. So these techniques add a penalty to the loss function used to train the model, which can discourage complex models that overfit. Then we have common methods that include L1, that is lasso, and L2, ridge regularization. And here's how you can add L2 regularization in Python. So this is the code snippet here. And what we have done here is we are creating the ridge model, and we have applied alpha equal to 1.0. So this parameter controls the strength of the regularization. A higher alpha value increases the regularization effect, which helps reduce model complexity and combat overfitting. The alpha value can be tuned to find the optimal balance between bias and variance. And now coming for the fitting the model. So model.fit, and in that we have X train and Y train that trains the ridge model on the training data. It adjusts the weight of the feature in X train to predict the Y train while also considering the regularization term. This helps prevent the model from fitting too closely to the noisy aspects of the training data. And then we are re-evaluating the model. After making adjustments, it's important to re-evaluate the model again using the same cross-validation technique to see if the issue of overfitting has improved. And then we have visualization. To help illustrate overfitting, you could create a plot showing the training and validation errors over the number of epochs or model complexity. So by using these techniques, you can identify if a model is overfitting and take steps to correct it, ensuring it performs well not only on the training data but also on new unseen data. So now moving to the next question, that is question number 3, and it is based on real-time data stream processing. And the question is, you are tasked with building a model to predict stock prices in real time. The data comes in every second and you need to update your predictions accordingly. Describe how you would set up your system to handle this type of data effectively, and what tools and techniques would you use and why. So you could start answering this question with handling real-time data. So handling real-time data, especially for something as volatile and fast-paced as stock prices, requires a robust system that can process and analyze data quickly and accurately. So here's how you could approach this. We will set up such a system and we will have some steps. So starting with the steps. So the first step is choosing the right tools. The right tool would be Apache Kafka. So this is a popular tool for handling real-time data that streams because it allows you to publish and subscribe to streams of records, that is data, and it can handle high throughput with low latency. Kafka acts as a buffer and manages the flow of data, ensuring that your system doesn't get overwhelmed. And you can also use Apache Spark. Especially Spark streaming is excellent for processing the data. It can process data in real time and perform complex operations like windowing, grouping data into chunks of a specified time period, and aggregating, that is summarizing data. So you can modify it and perform the predicting of stock prices. And then the step is data processing pipeline. And the first step comes here is ingestion. Data first enters the system, typically through Kafka, which collects data sent from the stock market. And then we do the processing. So Spark streaming takes over here. Here you can apply transformations and run your predictive models on the data. For example, you might calculate moving averages or other indicators that feed into your stock price prediction model. And then comes the output. Finally, the predictions are outputted. This could be to a dashboard for traders, an automated trading system, or even stored for further analysis. And then we develop the model. Now comes the model development. You would likely use a machine learning model that can update quickly and incorporate new data as it arrives. Models such as ARIMA for time series forecasting or more complex machine learning models like recurrent neural networks (RNNs) can be suitable. The model should be retrained or fine-tuned periodically with new data to ensure it stays accurate. Now we'll come to scalability and reliability. So ensure your system can scale as data volume increases. This might mean adding more servers or optimizing your data processing code. Implement monitoring to catch any issues early, like delays in data processing or model performance drops. And now we'll see the step, that is visualization and monitoring. Consider setting up a real-time dashboard that shows key metrics like prediction accuracy and processing time. This helps in quickly spotting when something goes wrong. By setting up your system with these tools and strategies, you can effectively handle the challenge of predicting stock prices in real time. So now we will move to the next question, that is question number 4, and this will be based on scalable data analytics. So we have covered 2 questions that were a bit code-based questions, and now we'll see other questions that would be based on scalable data analytics, or they might be on different areas. And with the 13th question, we will start again with the coding ones. So moving with the question 4, that is based on scalable data analytics. And the question is, given a scenario where your organization suddenly needs to scale its data analysis capabilities due to an influx of data that would be 10 times the normal volume, how would you handle this situation to ensure your data analytics processes remain efficient and accurate? What technologies would you consider and what steps would you take? So you can start answering this question with, handling a sudden increase in data volume requires a strategic approach to scaling your analytics infrastructure without compromising on efficiency or accuracy. So we'll see some steps from that you could effectively manage this scenario. That you would start answering the interviewer that we can start by evaluating the current infrastructure's ability to handle increased loads. This includes assessing your databases, servers, and analytical tools to identify potential bottlenecks or limitations. Then you could move to next step, that would be choosing scalable technologies. To manage the increased data volume, consider leveraging cloud-based solutions such as Amazon Web Services, Google Cloud Platform, or Microsoft Azure. These platforms offer scalable resources which can be adjusted accordingly to the data load, ensuring you only pay for what you use. Integrate big data technologies like Apache Hadoop for distributed storage and Apache Spark for fast data processing. These tools are designed to handle massive volumes of data efficiently and can scale up to meet standard increased demands. Now we'll move to the next step, that would be optimizing data processing. So implement data partitioning and indexing strategies to improve the efficiency of data queries. This will help in managing large data sets by breaking them into smaller, manageable chunks and speeding up search operations. And use real-time data processing frameworks like Apache Kafka or Apache Flink, which can handle high throughput and provide timely insights from large data streams. And the next step would be automation and monitoring. Automate routine data processing tasks to reduce the manual effort and speed up the analysis. This can be done through scripting or using workflow automation tools. Set up comprehensive monitoring systems to track the performance of your data processes. Tools like Prometheus for system monitoring and Grafana for analytics and monitoring dashboards are useful here. They help ensure that the system is running smoothly and alert you to potential issues before they become critical. And the next step will be regular evaluation and scaling. Continuously evaluate the performance of analytics infrastructure. As your data grows, keep adjusting and scaling your resources to maintain optimal performance. Plan for periodic reviews of your technology stack and infrastructure to ensure they remain aligned with your data needs and organizational goals. By following these steps, you can ensure that your data analytics processes are prepared to handle sudden surges in data volume effectively, maintaining the integrity and speed of insights. So this was all for the question 4. Now moving to the question 5, and this is based on integrating machine learning models into production. And the question is, you have developed a machine learning model that performs well in testing environment. Now you need to integrate it into your production environment where it will be used in real-time applications. What steps would you take to ensure the successful deployment and operations of the model in production? So we'll start answering this by successfully deploying a machine learning model into production involves several critical steps to ensure it performs as well in real-time operations as it does in testing. So you would have a clear pathway to make the interviewer understand. We will start with the pathway with the first step, that would be model validation. So before moving anything into production, revalidate your model's performance using a separate validation dataset. This helps confirm that the model generalizes well to new, unseen data. The next step will be preparing the production environment. Ensure that the production environment is ready to handle the model. This includes setting up the necessary hardware and software, ensuring that it can handle the expected load, and that all dependencies are correctly installed and configured. Then the next step comes, that is model wrapping. Wrap your model in an API, that is application programming interface, making it accessible to other parts of your software infrastructure. Frameworks like Flask for Python can be used to create a simple web server that listens for data inputs and provides model outputs. Then comes the next step, that is deployment strategies. Consider using containerization tools like Docker, which can help encapsulate your model and its environment, ensuring that it works uniformly across different development and production settings. And then we'll use deployment strategies like blue-green deployment or canary releases to minimize downtime and reduce the risk of introducing a faulty model into production. And then comes the next step, that is monitoring and logging. Implement logging and monitoring to track the model's performance and health in real time. Tools like Prometheus for monitoring and ELK, Elasticsearch, Logstash, Kibana for logging help in quickly identifying and diagnosing issues in production. And then comes the next step, that is performance tuning. Monitor the model's performance over time. If the model's performance degrades, or if new data shows different patterns, you may need to retrain or fine-tune the model to maintain accuracy. And after this step, there's a step for feedback loop. Set a feedback loop where predictions and outcomes can be compared. This feedback is crucial for continuously improving the model and catching any drift in data or changes in external conditions that affect the model. And after this comes a last step, that is legal and compliance checks. Ensure all the data used by the model in production complies with privacy laws and regulations. This is crucial for maintaining trust and legality, especially when handling sensitive information. So by carefully planning and executing these steps, you can smoothly transition your machine learning model from a testing environment to a fully functional component of a production system. So this was all about the question number 5. Now moving to the question number 6, that would be based on data-driven decision making. And the question is, your company wants to shift towards more data-driven decision making. You have been tasked with developing a strategy to implement this. What steps would you take to ensure that the data at all levels of the organization is utilized effectively to make informed decisions? And what challenges might you face and how would you address them? So you can start answering this by implementing a data-driven decision-making strategy that will require a comprehensive approach to ensure that reliable data is accessible and effectively used across all levels of the organization. And now we can develop and deploy this strategy, and similarly you could tell this strategy to the interviewer. So the number 1 step will be assessing current data infrastructure. Start by evaluating the existing data infrastructure to understand what data is available, how it is stored, and how it is currently used. This assessment will help identify gaps in data collection, storage, and access that need to be addressed. Now we'll move to the next step, that is developing a data governance framework. Implement a data governance framework that defines who can access data, how it can be used, and who is responsible for maintaining its quality. This framework ensures data integrity and security, which are critical for making reliable decisions. Now we'll move to the next step, that is training and empowerment. So train employees at all levels on the importance of data-driven decision making and provide them with the tools and knowledge necessary to analyze and interpret data. This might include training sessions, workshops, and ongoing support to ensure everyone can use data effectively. Now moving to the next step, that is implementing analytical tools. So deploy user-friendly analytical tools that can integrate seamlessly into the daily workflows of employees. Tools like Tableau, Microsoft Power BI, or even advanced Excel techniques can provide powerful data analysis capabilities without requiring extensive technical knowledge. After this, we'll move to the step that would be creating a centralized data platform. Develop a centralized data platform where all organizational data can be accessed and analyzed. This platform should be scalable and secure, providing a single source of truth for the organization. And then we have the promoting a data-driven culture. So foster a culture that values data-driven decision making. Encourage experimentation and learning from data-driven initiatives. Celebrate successes and learn from failures to continually improve the use of data-driven in decision making. And there would be some challenges and solutions for that. So one major challenge we know here is resistance to change, as some employees may prefer traditional decision-making methods. So address this by demonstrating the tangible benefits of data-driven decisions through pilot projects and success stories. So data silos can also hinder effective data use, promote cross-department collaboration, and integrate disparate data sources to overcome this challenge. After that, you can monitor and do continuous improvement. So by systematically implementing these steps, you can transform your organization into one that leverages data at all levels to make informed and effective decisions. And after answering in these steps, you could make the interviewer have a truth and a faith in you that you could make these models. Now move to the next question, that is question number 7, and that is based on handling large data set. And the question is, your project involves analyzing extremely large data sets, potentially exceeding terabytes in size. What strategies would you use to manage and analyze such large data sets effectively? Describe the tools and techniques you might employ. And you could start this with answering that working with large data sets, especially those in terabyte range, presents unique challenges in terms of storage, processing, and analysis. So we'll have a structured approach to handle these challenges effectively. We'll start with the data storage, that would be use distributed file systems. Consider using a distributed file systems like Hadoop Distributed File System, HDFS, or Amazon S3. These systems are designed to store vast amounts of data across many servers, offering high availability and fault tolerance. And then comes the next step, that is data processing. Leverage big data processing frameworks. Tools like Apache Spark are ideal for processing large data sets because they handle distributed computing effectively. Spark can perform data processing tasks much faster than traditional disk-based processing due to its in-memory computing capabilities. And next we could start with efficient data sampling. So there are many sampling techniques that we can use. So when the data set is too large to handle, even with powerful tools, consider using data sampling techniques to reduce the size to a manageable level without losing significant insights. Ensure that the sample represents the whole data set accurately. And then comes optimization of data queries. Indexing and partitioning. Optimize your data queries by implementing indexing and partitioning. This can drastically reduce the time it takes to perform queries by limiting the amounts of data scanned. And then we can do scalable analytics. And then we'll move to the next step, that is scalable analytics. And in that we could start with the parallel computing. Use parallel computing capabilities of frameworks like Spark or Dask to analyze data across multiple nodes. This helps in scaling up your analytics operations to handle large data sets effectively. And now we'll move to the cloud-based analytical tools. So consider using cloud services like Google BigQuery or AWS Redshift, which are designed to handle massive data sets and complex analytics with ease. And after this step, we'll move to data cleaning and pre-processing. Here we will automate pre-processing tasks. We'll use automated tools to clean and pre-process data. This includes handling missing values, normalizing data, and removing duplicates, which can be particularly challenging with large data set. And after this step, we'll move to the step that will visualize large data set. So we'll use specialized tools. That tools could be Tableau or Power BI that can handle large data set by aggregating data and using efficient back-end technologies. For more detailed exploration, tools like Plotly or Bouquet can be used as they offer capabilities to interactively visualize large volumes of data. And after that, there would be step for regular maintenance and updates that could be continuously monitoring the data quality. As new data comes in, you can continuously monitor its quality. And after this step, you could integrate all these strategies and tools into your workflow, and you can effectively manage and extract valuable insights from extremely large datasets, thereby supporting robust data-driven decision making. And you could answer the whole strategy to the interviewer. Now moving to the question number 8, that is based on optimizing machine learning models. And the question is, during model development, you have noticed that your machine learning model is underperforming. What steps would you take to diagnose the problem and optimize the model's performance? What techniques and tools would you use? So you can answer this by starting with the optimizing. And optimizing a machine learning model that is underperforming involves several steps to diagnose and improve its accuracy and efficiency. And here we will have structured approach to tackle this issue. And you could start this with the number 1 step, that is diagnosing the problem. Evaluate model metrics. Start by thoroughly evaluating the performance metrics of a model. For classification task, look at accuracy, precision, recall, and the F1 score. For regression task, consider R squared, mean squared error, that is MSE, and mean absolute error, that is MA. And then you can move to the next step. That is, use plots like ROC curves for classification models and residual plots for regression to visually assess where the model is going wrong. After that, we'll move to the next step, that is data quality and quantity check. Inspect the data. That is, sometimes the quality and quantity of data can be the root cause of poor model performance. Ensure the data is clean, well pre-processed, and sufficient. Look for issues like missing values, outliers, or imbalanced classes. And after this, we'll move to the feature engineering step, that would be experiment with creating new features or transforming existing ones to provide better predictive power. And then we have the next step, that is model tuning and configuration. After feature engineering, we'll move to the next step, that is model tuning and configuration. So hyperparameter tuning. Use techniques like grid search or random search to find the optimal settings for your model's parameters. Tools like scikit-learn's grid search CV or randomized search CV can automate this process. And there's a cross-validation that would implement cross-validation to ensure that the model's performance is consistent across different subsets of the dataset. And then we have the next step, that is trying different models. So experiment with algorithms here. If initial models are underperforming, try different algorithms that might be better suited for the problem. For instance, if you started with linear regression and it's not performing well, consider more complex models like random forest or gradient boosting machines. And after this, we have ensemble methods that we can use techniques like bagging, boosting, or stacking to combine the predictions of multiple models to improve overall performance. After this step, we have feature selection that includes reduce dimensionality. Use techniques like principal component analysis, that is PCA, to reduce the number of features, which might help in improving model performance by removing noise and redundancy. And then we have select important features. So use model-based technique to identify and keep only the most important features that impact the outcome. And then comes the last step, that is regular updates and retraining. So here you can monitor and update, that could be continuously monitoring the model's performance over time. As new data becomes available, update and retrain the model to adapt to any changes in underlying patterns. And after that, you could have a consultation and collaboration work with the other teams. And by methodically addressing each of these areas, you can diagnose why your machine learning model is underperforming and can take steps to optimize its accuracy and efficiency. So this was all about question number 8. So let's start with the question number 9. And this is based on handling unstructured data. So the question is, you are given a large amount of unstructured data, including text, images, and videos. What strategies would you use to manage and analyze this type of data effectively? Describe the tools and techniques you might employ. So you can start answering this question by describing that dealing with unstructured data can be challenging due to its lack of predefined format or structure. However, with the right strategies and tools, you can effectively manage and analyze it to extract valuable insights, and there will be an approach how you can do that. So we will discuss the approach here, and starting with the steps. So the number 1 step will be data categorization and organization. So the number 1 step in this step will be sorting and tagging. We will begin by categorizing the data into types, that will be text, images, or videos. Use tagging to add metadata, which helps in organizing the data and makes it easier to access and analyze later. After that, particularly for text data, we'll use natural language processing, NLP. We will employ NLP techniques to extract useful information from text. Tools like NLTK, Spacey, or even more advanced models like BERT can help you perform tasks such as sentiment analysis, entity recognition, and topic modeling. After that, we will do text indexing. We can use Elasticsearch or Apache Solr to index large volumes of text. These tools provide powerful search capabilities and can handle complex queries efficiently. And after that, we'll move to image data. And to structure image data, we'll use image processing. We'll use libraries like OpenCV for basic image processing tasks such as filtering and transformations. For more advanced image analysis, consider deep learning models using frameworks like TensorFlow or PyTorch. And then we'll feature extraction. Apply techniques to extract features from images, such as edges, textures, or key points, which can be used for further analysis or machine learning. And then we'll come to video data. And here we'll do video processing, and we'll use the tools like FMPEG that can be used for basic video processing tasks such as format conversion or extracting frames. For analyzing video content, look at machine learning models that can classify or recognize activities in the video. And after this, we'll move to temporal analysis. For videos, temporal components are important. Techniques like sequence modeling or recurrent neural networks, RNNs, can be useful to analyze sequences of frames for activities or events. And then we'll move to data storage and management. Here we'll use the given volume and complexity of unstructured data and use big data platforms like Hadoop or cloud services like AWS S3 for storage. These platforms can scale up to handle large data sizes and provide the necessary infrastructure to store and retrieve unstructured data efficiently. And then we have visualization and reporting. Custom dashboards that we'll create here. We will develop custom dashboards using tools like Tableau or Power BI, which can integrate different data types and provide a unified view of the analyzed data. And after that, we will do data summarization. Tools that provide summarization capabilities can help in considering large volumes of unstructured data into more manageable and interpretable forms. And after that, we'll leverage these strategies and tools and can effectively manage, analyze, and derive insights from unstructured data, which can be crucial for making informed decisions in various applications. And this is the path that you can explore and explain to the interviewer if this question has been asked. Now moving to the question number 10, and that will be based on scaling AI solutions in enterprise. And the question is, your company wants to scale its AI operations from a few initial pilot projects to enterprise-wide implementation. What are the key considerations and steps you would take to ensure the successful scaling of AI solutions across the organization? And what challenges might you face and how would you address them? So you can start answering this question with the scaling AI solutions. You could answer him that scaling AI solutions across an enterprise requires careful planning and strategic implementation to ensure success and alignment with business objectives. And there should be a strategic approach to implement this. So starting with the approach, and the number one step will be strategic alignment. So identify business objectives. Start by identifying the business objectives that the AI solutions are intended to support. This ensures that the AI initiatives are aligned with the company's strategic goals and can demonstrate clear business value. And then comes the stakeholder engagement. So engage stakeholders from various departments early in the process to gather input and build support. This helps in understanding diverse needs and ensures broader acceptance of the AI solutions. And after that comes the infrastructure and technology. So there's an option that is assess and upgrade infrastructure. Evaluate whether your current IT infrastructure can support the expanded use of AI. You might need to upgrade hardware, invest in cloud solutions, or adopt technologies that facilitate AI processing and data handling. And after that, we have standardization of tools. Standardize the tools and platforms used for AI development to ensure compatibility and ease of maintenance across the organizations. And after that, we'll move to data management. So robust data governance, that is to implement a strong data governance framework to manage enterprise data effectively. This includes policies for data quality, security, and compliance, especially important when scaling AI solutions that rely on vast amounts of data. And after that, we will come to data accessibility. So ensure that data is accessible across the organization, but also secure against unauthorized access. This involves setting up secure data lakes or warehouses that centralize data while allowing controlled access. And then we come to the next step, that is talent and training. So build AI competency, that is develop in-house AI expertise through training programs and hiring. So this builds the necessary skills within the organization to develop, manage, and scale AI solutions. And after that, you can also perform cross-functional AI teams. that could be forming cross-functional teams that include data scientists, IT professionals, and domain experts. So this fosters collaboration and ensures that AI solutions are developed with a comprehensive understanding. And after forming these collaborative teams, we'll move to scalable deployment models. So pilot test and phased rollout. Before a full-scale rollout, conduct pilot tests to gauge the AI solution effectiveness and integration capabilities. Based on feedback, adjust, and then gradually deploy the solutions across the organization. And then we have modular and flexible design. So design AI systems to be modular and scalable, allowing for adjustments and expansions as needs. And then we'll monitor and do the continuous improvement. So there will be performance metrics that would establish metrics to regularly assess the performance of AI systems. We will monitor these systems to ensure they met expected outcomes and adapt as necessary. And after that, we have next step, that is addressing challenges. So there could be cultural resistance, that there could be employees that would be resisting to the changes, but we have to address this through continuous education and by showcasing successful AI use cases within the organizations. And by carefully considering these aspects and methodically implementing steps, you can successfully scale AI solutions across your enterprise, driving significant business value and innovation. And that's all for question number 10. Now we'll move to question number 11, and that is based on ethical considerations in data science. So the question is, in your data science projects, how do you ensure that ethical considerations are addressed? Describe the steps you take to identify and mitigate ethical risk in your projects. What frameworks or guidelines do you follow? So you could start answering this question with ethical considerations, that they're crucial in data science to ensure that the solutions and analyses do not advertently cause harm or bias. Here's how you can ensure that. So there are some steps and we will discuss those steps, starting with the number 1, that is educate on ethical standards. So stay informed about the ethical standards in data science, such as fairness, accountability, transparency, and privacy. Organizations like the Data Science Association and the ACM have codes of ethics that we refer to as guidelines. And then we have ethical risk assessment. Identify potential ethical issues. That would be at the beginning of each project, conduct a thorough assessment to identify any potential ethical risk, such as biases in data or impact on vulnerable groups. This involves reviewing the source of data, the methodologies used for data collection, and the intended use of the data analytics results. And then we have stakeholder analysis. Engage with stakeholders to understand the diverse perspectives and potential impact of the project. This helps in identifying ethical issues that may not be apparent from a purely technical standpoint. And then we'll move to mitigation strategies. Implementing bias mitigation techniques, we will use statistical and machine learning techniques to detect and mitigate biases in data. This might involve techniques like resampling, reweighing, or using algorithms designed to be fair. And then we have privacy preserving methods. Employ methods such as data anonymization, encryption, or differential privacy to protect individual privacy when analyzing sensitive data. Then we have other methods, that is transparency and explainability. There we have model explainability, and after that coming to documentation and reporting. So we have to maintain thorough documentation of data sources, model decisions, and methodologies. And then we have continuous monitoring and feedback. There you have to monitor outcomes and the feedback mechanisms should be applied. And then we have the panels, that is collaboration and advisory panels. There we have ethical review boards. So for complex projects, setting up or consulting with an ethical review board can provide oversight and diverse perspectives on the ethical implications of project methodologies. So by proactively addressing ethical considerations through these steps, you can ensure that your data science projects uphold high ethical standards and positively contribute to society while minimizing harm. So this was all about question 11. Now moving to question number 12, that is based on time series forecasting for business decisions. So the question number 12 is, you are tasked with forecasting monthly sales for a retail company using time series data from the past 5 years. What steps would you take to prepare and analyze this data to make accurate forecast? What specific tools or techniques would you use and why? So we can start answering this by time series forecasting. And we could address them that it's a powerful tool for predicting future events based on past data, especially in business context like retail sales. So we will have a structured approach here, and we'll start with data collection and cleaning. First, we will gather data and ensure that you have collected all relevant data, including monthly sale figures from the past 5 years, and also considering including external factors that might affect sales, such as economic indicators, holidays, and promotional activities. And then we'll proceed to clean data. We'll check for and handle any inconsistencies or missing values. And then we have data visualization. Here we'll plot the data. We'll use plotting libraries like matplotlib or seaborn in Python to visualize the data. This will help in identifying patterns, trends, and seasonality. And then we have decomposition of data. So there's a seasonal decomposition, and we'll use statistical techniques to decompose the data into trend, seasonally, and residuals. So this can be accomplished with tools like the seasonal decompose function from the stats models library in Python. And we'll understand these components separately and can improve the accuracy of our forecast. And then the next step is model selection and forecasting. So there are two models, that is ARIMA and SARIMA models. So we have to choose appropriate forecasting models based on data's characteristics. For instance, ARIMA, that is autoregressive integrated moving average. It is effective for non-season data, while SARIMA, that is seasonal ARIMA, that is suitable for data with seasonal patterns. And after choosing the model, we'll move to cross-validation. We'll implement time series specific cross-validation techniques like time-based splitting to evaluate model performance. And this will ensure your model generalizes well on unseen data. And then we have model fitting and diagnostics. We will fit the model, that is by using the Synimax class from stat models that will fit your model to the data. And then we will carefully select parameters based on AIC, that is Archaic Information Criterion, that scores or thorough grid research technique. And then we can do the diagnostics and forecast and validation. And after forecast validation, we'll move to iterative improvement. So there's a feedback loop that should be mandatory, and there should be a regular update for the model with new sales data and refining the model as needed. So this continuous improvement cycle helps adapt to changing patterns in sales data. And by following these steps and using these tools, you can create robust forecasts that help the retail company plan better and make informed decisions. So this was all about question number 12. Now moving to question number 13, that is based on customer segmentation using machine learning. So the question is, you are given a data set containing demographic and purchasing behavior data for a group of customers. Your task is to segment these customers into distinct groups based on similarities in their purchasing behavior and demographics. So what steps would you take to perform this segmentation, and can you provide a sample Python code snippet to illustrate the initial stages of data handling and model application? So we can start this by explaining customer segmentation, that it's a powerful approach to tailor marketing strategies and improve customer service by identifying distinct groups based on their behavior and characteristics. And here also we have a detailed approach for this task. So we'll start with number one step, that would be data exploration and pre-processing. So there will be initial exploration, that is beginning by examining the data set to understand the features available such as age, income, purchase frequency, etc. Then we'll look for missing values or anomalies and decide how to handle them. That could be using imputation. And then we'll move to feature engineering. We will create new features that might be useful for segmentation, such as customer lifetime value or average transaction amount. We'll also use normalization, that is normalize the data to ensure that one feature doesn't disproportionately influence the model due to its scale. We'll use standard scaling or min-max scaling as appropriate. So then we'll come to the next step, that is choosing the segmentation technique. And here we have k-means clustering. So this is a popular method for customer segmentation. Here we will decide on the number of clusters by using techniques like the elbow method or silhouette analysis to determine the optimal cluster count. And then we have model implementation. And in that we will use data preparation, and we'll prepare the data by selecting the relevant features and applying any final transformations. And then we have model fitting. We'll fit the k-means clustering model to the data and evaluate and interpret analyzing clusters. And after analyzing clusters, we'll move to the next step, that is strategic insights. We'll provide actionable insights based on cluster characteristics such as targeted marketing strategies for each segment. And then we have iterative refinement, that is feedback incorporation, and we'll use business feedback to refine the segmentation. If additional data becomes available, incorporate it to enhance the model. And now we'll see the sample Python code. So for this, first we'll import the libraries and modules. As you can see on the screen, we have imported pandas, random forest classifier, train test split, standard scalar, classification report. And after that, we'll load the data. And for that, we have used the pandas. to read the data, that is read underscore SSV. And after that, we are processing the data, that is data pre-processing. We are handling missing values and using the forward fill or FIL to fill missing values in the data set. And then we are featuring scaling, that is normalizing the selected features, that is feature 1, feature 2 and feature 3 using standard scaler. And then we'll move to the next step, that is data splitting. We'll split the data set into training and testing sets. So that test size equal to 0.2 parameters specifies that 20% of the data will be used for testing. And then we'll train the model. We'll initialize and train a random forest classifier with 100 trees and a random state for reproducibility. And then we'll evaluate the model. We'll make predictions on the test set, that is x underscore test, using the trained model, and print a classification report showing precision, recall, F1 score and support for each class. So this code demonstrates the process of loading, pre-processing, training and evaluating a machine learning model, that is random forest classifier, for predicting equipment failures in a manufacturing plant. The use of techniques such as data pre-processing and splitting along with the random forest classifier highlights a standard flow for building predictive maintenance models. So this was all about the question number 13. So now moving to the question number 14, that is based on predictive customer churn. And the question is, you are tasked with developing a model to predict which customers are likely to churn from a subscription service. So what steps will you take to build this model, and can you provide a sample Python code to illustrate the data preparation and model training process? So we'll start answering this question about depicting what is predicting customer churn. So predicting customer churn is crucial for businesses to implement retention strategies proactively. And we'll have a detailed approach for building a predictive model for this purpose, starting with data collection and exploration. And in this, we will collect data. And after that, we will perform the exploratory data analysis, that is EDA. We'll perform an initial analysis to understand patterns and trends. And then we have feature engineering. We will create new features and derive new features that might influence churn, such as change in usage pattern or service upgrades. And then we'll handle the missing values if we found any. And then we'll encode categorical variables. We'll use techniques like one-hot encoding or label encoding for categorical variables. And then we have scale features to normalize or standardize numerical features to ensure they contribute equally to the model's performance. And then we'll select the model, that is, we'll choose the appropriate model and start with for the knowing handling binary classification task. That could be with logistic regression, random forest or gradient boosting machines. And after selecting the model, we'll train the model and evaluate it. So fit your model on the training data, and after that evaluate the model using appropriate metrics like accuracy, precision, recall, F1 score and ROC to gauge its performance. And then we'll optimize the model using hyperparameter tuning. We'll optimize the model parameter using grid search or random search to improve performance. And then we have feature importance, that is analyze and rank features by their importance in predicting churn to refine the model further. And then the last step is deployment and monitoring. We'll deploy the model. Once validated, deploy the model into a production environment where it can predict real-time churn. So after deploying the model, regularly monitor the model to ensure it remains effective over time as new data comes in. So now we'll see the sample Python code for this example. So starting with the importing of libraries, we will import pandas, numpy, scikit-learn, sklearn, tensorflow, and the tensorflow keras and callbacks. And after importing the modules, we'll start with data loading. We'll load the dataset from a CSV file named equipment_data.csv, and that too with the pandas data frame. And after that, we'll do the data pre-processing. We'll handle missing values, and for that we'll use forward fill to fill missing values in the dataset. And then we have feature scaling that will normalize the selected features, that is feature 1, feature 2, feature 3 using standard scaler. And after that, we'll use the data splitting. We'll split the dataset into training and testing sets, and the test size will be equal to 0.2. And this parameter specifies that 20% of the data will be used for testing. And after that, we'll start with building the model. First, we'll see sequential model that initializes a sequential model technique. And then we have dense layers that adds 2 dense layers with 64 units and ReLU activation function. Then we have dropout layers that adds 2 dropout layers with a dropout rate of 0.5 to reduce overfitting. After that, we'll do the model compilation. We'll compile the model using the Adam optimizer and binary cross entropy, loss function for binary classification. And there will be an early stopping that will define an early stopping callback to stop training when the validation loss metric has stopped improving after 3 epochs. And after training the model, we will evaluate the model and evaluating the model on the test data and print the loss and accuracy metrics. So this code demonstrates the process of loading, pre-processing, building, compiling, training, and evaluating a deep learning model using TensorFlow and Keras for predicting equipment failures in a manufacturing plant. So the use of techniques such as data pre-processing, dropout, regularization, and early stopping helps in building a robust deep learning model for predictive maintenance. So that's all with question number 14. Now I'll start with question number 15, that is based on deep learning and NLP. And your question is, you are tasked with developing a sentiment analysis model using deep learning to understand customer opinions from reviews. So what steps would you take to build this model, and can you provide a sample Python code snippet to illustrate how you would pre-process data and train a simple deep learning model? So we'll start answering this with sentiment analysis. That sentiment analysis using deep learning allows businesses to gauge customer sentiment from text data like reviews or comments effectively. And we'll have a detailed approach for building a sentiment analysis model. We'll start with data collection and cleaning. We will collect the data, gather a substantial data set of text reviews and their associated sentiments, typically labeled as positive, negative, or neutral. And then we'll clean the data, pre-process the data by removing noise such as HTML tags, special characters, and stop words. And we'll normalize the text by converting it to lowercase. And then we have text pre-processing. We'll convert text into tokens, words, or phrases. And then we have vectorization that transforms tokens into numerical format using techniques like word embeddings or TF-IDF, that is term frequency in verse document frequency. And then we'll use the padding. And then we have the option of model selection. We'll choose a model architecture based on a basic approach and use a RNN or more advanced architecture like LSTM, that is long short term memory, or GRU, that is gated recurrent units, which are effective for sequence data like text. And then we have model training. We'll compile the model, define the model architecture, and compile it with the loss function suited for classification like categorical, cross entropy, and an optimizer like Adam. And then we'll train the model, we'll fit the model on our pre-processed data. We'll evaluate and optimize it. Evaluating model performance, here use the metrics such as accuracy, precision, recall, and F1 score to assess the model. And then we have hyperparameter tuning. We'll optimize the model by adjusting parameters like learning rate, number of layers, and units per layer. And then coming to deployment. We'll deploy the model and integrate the model into the existing review processing pipeline so it can automatically classify new reviews. So let's see the sample Python code, and we'll have a basic approach for that. Here we'll import NumPy, TensorFlow, sequential, embedding LSTM, dense dropout. So embedding converts positive integers, that is indexes, into dense vectors of fixed size. And LSTM, that is long short term memory layer, that is used for learning dependencies in sequence data. And then we have dense, that is a regularly dense connected NN layer. And then we will import pad underscore sequences. And after that we have the data set and the sample text data representing customer reviews that will store in variable text. And then we have labels that has binary labels indicating sentiment, 1 for positive, 0 for negative. And now we'll start with the pre-processing of data. Here we have declared that tokenizer. We will initialize a tokenizer that will help only the top 1000 most frequent words. And then we have fit underscore on underscore text, that is update the internal vocabulary based on the list of text. It essentially creates a dictionary of word to index pairs. And then we have text to sequences that will transform each text in text to a sequence of integers. And then we have pad sequences that will ensure all sequences have the same length by padding shorter sequences with zeros up to the maximum length. And then we'll start building the model. Here we have sequential model that will set up a linear stack of layers. And then we have embedding layer that will map each word index to an embedding vector of size 64. So the input length is set to 10, that is the length of the input sequences. Then we'll start with LSTM layers. So 2 LSTM layers are added. The first one returns sequences to allow the next LSTM layer to process these sequences. And after that we have the dropout layer that applies dropout with a rate of 0.5 of the first LSTM layer to reduce overfitting. And after that we'll come to dense layer that has output of a single scalar that represents the predicted sentiment and using sigmoid activation to output a probability. And now we'll start with model compilation and training. So we'll configure the model for training and we'll use binary cross entropy as the loss function that is suitable for binary classification, and the Adam optimizer and tracks constantly accuracy as a metric. And then we have the fit that trains the model for a specified number of epochs, that is iterations or the entire data set. And then we'll predict the model, that is after training the model can predict the sentiment of the reviews in the data set. This is useful for checking how the model performs on the training data itself. So this breakdown explains each step of the coding process, detailing how the data is prepared and how the model is configured. And then we'll compile it and use for training and prediction. So its detailed explanation should help in understanding how to implement a simple LSTM model for sentiment analysis in TensorFlow. Now moving to the question number 16. So let's start with question number 16, that is based on anomaly detection in transaction data. So the question is, you are tasked with identifying unusual transactions in a company's financial data that might suggest fraudulent activity. So what steps would you take to develop an anomaly detection model, and can you provide a sample Python code snippet to illustrate how you would preprocess the data and apply an anomaly detection technique? So we'll start answering this with anomaly detection technique. That is, anomaly detection is essential for preventing fraud by identifying transactions that deviate significantly from typical patterns. And now we'll see the structured approach to building an anomaly detection model for transaction data. We'll start with data collection and cleaning, and we'll collect all the compiling transaction data, which should include details like transaction amount, time, user ID, and transaction type. Then we'll move to feature engineering and develop features that capture the essence of transactions, such as time of day and the day of the week. And then we have data normalization. We'll use scaling techniques such as min-max scaling or standardization to ensure that the model is perfectly normalized. And then we have choosing the anomaly detection technique. So here we have to choose the technique which is effective for high dimensional data sets and works for isolating anomalies instead of profiling normal data points. After choosing the anomaly technique, we'll train anomaly identification. We'll fit the chosen model to the data, and the anomalies that would have been chosen will be those transactions that the model identifies. And after this, we come to the last step, that is review and action. Here we have manual review, that is transactions flagged as potential anomalies should be reviewed manually to confirm fraudulent activity. And then we have continuous improvement. That is, we can regularly update the model with the new data and feedback from the review process to improve accuracy. And now moving to the prediction, that is after training the model, we can predict the sentiment of the reviews in the dataset. And this is useful for checking how the model performs on the training data itself. Now we'll see the Python code to see how you can set up this model for anomaly detection. We'll start by importing the libraries and module, and after that we'll load and prepare data. That is, we'll load transaction data from a CSV file into the pandas data frame. And after that, we'll convert the transaction time column to date time format, which allows the extraction of additional time-based features. And after that, we'll perform feature engineering that will extract the hour of the day from the transaction time column. This feature can be important as transactions occurring at unusual hours may be indicative of fraud. And then we'll move to the normalization of data. This will apply standard scaling to the amount and hour of the day feature. This normalization process involves subtracting the mean and dividing by the standard deviation for each feature, ensuring that the feature contribute equally to the analysis and improving the performance of many machine learning algorithms. And after that, we'll start with anomaly detection with isolation forest. That's a technique. We'll initialize an isolation forest model with 100 trees, that is n estimators equal to 100, setting the proportions of outliers, that is contamination, to 1% of the data. So this parameter is crucial as it influences the threshold of marking an observation as an anomaly. Then we'll fit the model to the scaled amount and hour of the day data and predict the anomaly status for each transaction. And then we'll start with filter and display anomalies. We'll filter out transactions identified as anomalies, that is anomaly equal to -1. We'll display these transactions which can be reviewed manually to determine if they represent actual fraudulent activity. So this code snippet provides a systematic approach to detecting anomalies in transaction data, leveraging the isolation forest algorithm's ability to handle complex and high-dimensional dataset effectively. So the pre-processing steps ensure that the data is appropriately formatted and normalized for optional model performance. So this was all about question number 16. Now moving to question number 17, and that is based on integrating machine learning models into web applications. And your question is, you have developed a machine learning model to predict real estate prices based on various features like location, size, and amenities. How would you integrate this model into a web application to allow users to get real-time price predictions? Can you provide a sample Python code snippet to illustrate how you would prepare the model for integration and handle user requests? So starting with the approach, that is integrating a machine learning model into a web application, this will involve several steps to ensure the model is accessible and perform well in a live environment. So here's how you can approach this task. We could divide into steps, and we'll start with number 1 step, that is model preparation. We'll finalize and save the model. So once your model is trained and validated, save it using a format that can be easily loaded into a web application. So Python's pickle module or TensorFlow's save model format are commonly used for this purpose. Then we can use web application backend setup. For this, select a suitable web framework. So Flask is popularly known for its simplicity and effectiveness in integrating Python-based machine learning models. And after that, we'll develop the API. After developing the API within your Flask app, that you can receive user inputs for model features, load the model, make prediction, and return the result. And after this, we'll develop the UI. We'll design a user-friendly interface. We'll create a simple and intuitive UI that lets users input the feature like location, size, and submit them for prediction. And after that, we'll move to the deployment phase. We'll use a cloud platform like Heroku, AWS, or Google Cloud to deploy your Flask application. And then we have the maintenance and updates. We'll monitor and update regularly for the performance and use the model as needed based on user feedback. So now moving to the Python code and see how this model can be created. So here we'll start importing the libraries and module, and we are using Flask, Pickle, and JSONify. And we will start with app initialization. We'll initialize a new Flask web application. That would be a special variable which gives Python files a unique name to differentiate between them when they are imported into other scripts. And after that, we'll load the model. So loading a pre-trained machine learning model from the file system. So this model is assumed to be saved in the same directory as this script. So the model is loaded in RB mode, which stands for read binary. And after that, we'll move to API route and prediction function. So we will define an API endpoint at predict that listens for post request. This is the URL that the front end of the web application will call to send data to the backend. And after that, we'll start with predicting the function. And here we have extract features that retrieves data sent into the JSON format from the post request. That is request.get_JSON, and the force we have set it as true here, and forcefully formats the request data into JSON, ensuring compatibility. And then we'll extract the relevant features, that is location, size, and amenities from the JSON object and store them in a list as expected by the model. And after preparing the features, we'll make the prediction. We'll use the loaded model to make a prediction based on the provided feature. And then we have the return prediction method. Here we will convert the prediction result into JSON format using JSONify and send it back to the client, and this will ensure that the response can be easily handled by the client application. So this was all about the question number 17. Now moving to the question number 18, that is based on analyzing. And now we'll move to the question number 18, that is based on analyzing geospatial data. And your question is, you are tasked with analyzing geospatial data to help a city improve its public transportation system. The data includes GPS coordinates of bus stops, ridership numbers, and traffic patterns. What steps would you take to analyze this data, and can you provide a sample Python code snippet to illustrate how you might visualize bus stop location and ridership? So you can start answering this question that geospatial data analysis can provide critical insights into how effectively a public transportation system serves its city and guide improvements. And there's a detailed approach for this, and we can start with data preparation. And in this, we will do data collection and data cleaning. And after this step, we will move to the next step, that is exploratory data analysis. And in this, we will have statistical summary, we will generate descriptive statistics, and then we have correlation analysis. And after moving that, we have geospatial visualization, that is mapping bus stop. We'll plot the locations of bus stop on a map to visually assess their distribution across the city. And after that, we have heat maps that will create ridership data to identify hotspots and areas with potential service gaps. And after geospatial visualization, we'll move with spatial analysis. We have proximity analysis that will analyze the proximity of bus stop to key areas like commercial centers or residential areas. And now moving to the fifth step, that is optimization and recommendation. So we'll have a route optimization that will suggest modifications to route based on traffic patterns and ridership demand. And the policy recommendations that will provide actionable recommendations for improving bus frequencies. Now moving to the sample Python code where we can define this model and use it accordingly. And here we will start importing the libraries and modules, and here we will start with importing GeoPandas and matplotlib.pyplot. And after importing, we'll start with data loading. So we will declare a variable bus underscore stops and load the bus stops data from a shapefile. So shapefiles are popular geospatial vector data formats for geographic information system software. And then we have the ridership that will load ridership data from a CSV file which includes columns for longitude, latitude, and ridership levels. And after that, we'll create geodata frame that will convert the ridership data frame into a geodata frame. And this step involves creating a geometry column from the longitude and latitude columns. And then we have the plotting one. Here we will plot the graphs that would be figures and axes and create a figure for the single subplot with a specified size that is 10 cross 10 inches. And then we have city underscore map.plot. It is assumed that there is a base map of the city loaded as a geodata frame named city map. This is plotted first with the light gray color to serve as a background for the other layers. So this was all about question number 18. Now moving to question number 19, that is based on predictive maintenance using machine learning. And your question is, you are tasked with developing a predictive maintenance system for a manufacturing plant that relies heavily on automated machinery. So the data available includes machine operational parameters, maintenance history, and failure incidents. What steps would you take to develop a predictive model, and can you provide a sample Python code? So you can start with predictive maintenance that is essential in manufacturing as it helps prevent equipment failures, reducing downtime and maintenance cost. And here you would have a detailed approach or predictive model for this, starting with data collection and integration. Then you can do EDA, that is exploratory data analysis, and then we can perform feature engineering and then move to data pre-processing tasks, and then the selection model and training. And after that, we have model evaluation and deployment technique that we can do for the model using appropriate metrics such as precision, recall, and F1 score. So this was all about question number 19. So now move to question number 20, that is based on personalization using machine learning. And your question is, you are tasked with developing a machine learning model to personalize content recommendations for users on a media streaming platform. The data available includes user demographic details, viewing history, and ratings. So what steps would you take to build a model for personalized recommendations? And can you provide a sample Python code for that? So you can start answering this with creating a personalized recommendation systems. This would be essential for engaging users by providing content that is relevant to their interest. And there will be a systematic approach or personalized content recommendation. We'll start with data collection and integration. And after that, we'll perform EDA, that is exploratory data analysis. And then we have feature engineering. In this, we'll interact features, and the temporal features will include time-based features to capture trends and seasonality in viewing behavior. And then we'll select the model, that is by collaborative filtering and hybrid models. And then we'll train the model and validation and implement and monitor them. And after that, we'll deploy the model, integrate the recommendation system.
Now with that, we have come to the end of our full course. If you have any doubts or questions, you can ask them in the comment section below. Our team of experts will reply you as soon as possible. Thank you and keep learning with Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.